Yes.
Alright, cool. So first of all, thanks everyone for being here so early. My name is Giovanni Guizzo. I'm a research fellow at University College London, and today I'm co-hosting and co-organizing the SBST workshop with my colleague, Dr. Sebastiano Panicella.
As European University of Applied Science, and it has been a great pleasure so far.
Yeah, it was great so far. Very, very good organization. Thanks, Sebastiano, for all the help. And yeah, this is SBST 2022. I hope everyone has a great workshop. We have many things planned out for today. And yeah, let me go to the next slide. Oh yeah, so it's 9:15 a.m. CEST time. So all the times from the schedule are European summertime. Okay. You can access our website SBST 2022 GitHub.io and see our program there and other information as well. And please go to our Twitter, share, like, smash that retweet button, and engage in all social media, because this gives us visibility and this gives the presenters more questions. So yeah. So this year SBST 2022 is fully virtual. It's co-hosted, co-located with ICSI 2022, which is happening in Pittsburgh. We are using Meetspace for the main virtualization, and also for people who are not registered, they can access Twitch TV. We're live sharing this. We are live sharing the workshop there. So if you have students who have not registered for the workshop, you can tell them to go there, twitch.tv/KOXP. As I said, Twitter as well. Please go there, give us your like button and your retweet. Also, I would like to start by saying thanks to our sponsor, Google. The Google Open Source Security Group provided us with cloud credits for the 2 competition experiments. As you can imagine, running dozens of tools for cybersecurity testing and Java testing, many repetitions, is very expensive and takes a lot of time. So the Google Cloud sponsor was detrimental, it was fundamental for the execution of our 2 competitions. So thank you, Google. And the general format of the workshop is basically you have to access Meetspace. It's kind of like a Zoom call meeting. So if you turn on your video and turn on your microphone, you're gonna be on stream. You're gonna be on the recording. So when your time comes to present the paper, please turn on your video, turn on your microphone, and you're gonna be automatically in. And also, if you have questions during the presentations, okay, not during the presentations, after the presentations, during the question and answers, if you prefer to ask them yourself, we encourage you to do so, because it's a workshop. We want everyone to socialize, to talk to each other, and yeah, that will be great. And as I said, for the non-registered participants, feel free to join our Twitch stream. If you have questions, put it on Twitch stream, in the Twitch stream chat. I'll read them here live. And everything is going to be recorded and uploaded to YouTube later on, so you can have access to the content afterwards. This is our schedule. As I said, everything is on the European summertime. We're starting with the opening. Then we have a great keynote by Paolo Tonela about deep learning testing. Then I have a short break. Then a great tutorial by Rahul Gopinath on learning and refining input grammars for effective fuzzing, which is a recurring theme this year, and I guess you're gonna know why during SBST versus fuzzing discussion panel with these great names. This is a great discussion panel. Probably the one of the reasons we got a lot of registrants this year, but this panel is going to be great. So please stay tuned. We also have two paper sessions of 2 papers each. This year we have 2 short papers and 2 full papers, and then at the end we're gonna have the tool competition. We are expected to end at 6:15 p.m. So yeah, if everything goes well, if we have more discussion, of course, we can have some socializing afterwards. We can talk to each other. We're gonna try to also use the socialize function on your left, on your left part of your screen. There is a socialize button. During the breaks, you feel free to talk to everyone. Join a socializing room and try like a random networking feature here. I don't know how exactly it works, but there is a random networking. I think you join randomly other researchers in SBST in a video chat to talk and get to know each other, get to know your community. So great! This is a great platform, by the way. And yeah, I think that's it.
So it's a great pleasure to introduce the keynote from Paolo Tonela. He's currently full professor at the Faculty of Informatics at Software Institute, University of Svizzera Italiana in Lugano. If you look backward, he has been known for a lot of school research from Fondazione Bruno Kemmer in Trenton, Italy, and he has been the recipient of important research in software testing. Look backward, we have the most influential paper on web-based testing for in ICSE, and very recently in ICST, the National Conference on Software Testing, and it is been also recently granted for the IRC starting advanced grant, one of the most prestigious grants as a main applicant. Is been doing a lot of research on software testing. One of the work that we know and is very related to search-based software testing. This workshop we are running today is the work on ISTA, which was about the testing of or evolutionary testing of classes, which was for us a sort of a milestone for what is test case generation for Java classes. Of course, going forward or looking at the research going today is focused on machine learning based testing or the buildability of machine learning based systems, automated testing for cyber-physical system, and of course the generic open problem of the testing oracle. So in this talk, deep learning testing, Paolo will try to tease you a bit with the challenges that are today of deep learning system and describe how they are different from system we have seen or have been testing in the past research. So thank you to have you here, Paolo. And maybe you can start sharing your camera and your screen with your presentation. And we are very excited to see you present this interesting talk, which I think will be quite well linked for the tutorial and follow-up panels. So we're really looking forward to it.
So thanks, Sebastiano, for the nice introduction. It's a pleasure for me to be here. So thanks for inviting me. Let me just fix a little problem I had with the screen sharing because apparently I have to grant some permission through the Mac preferences.
Intentionally, no problem.
Any hint where I should do that? Well, let me try to press again the button, allow. No, maybe now it works. So you should see my screen now, right?
Yes, we see it.
Okay, very good. Great. So good morning, good afternoon, everyone. The title of my talk is Deep Learning Testing, and as mentioned by Sebastiano, What I'm presenting today is part of the results that were achieved in the pre-crime ERC project. It's a project devoted to testing unexpected execution conditions for general software, but in particular for software where unexpectedness is pretty important. And as I will try to convince you, this is the case definitely of deep learning systems and deep neural networks. So let me try to start with a brief introduction to deep neural networks. For those of you who are not familiar, but also to stress the differences with respect to traditional software. So a deep neural network is an arrangement of so-called neurons or artificial neurons, and these are computational units that are inspired to the biological neuron, which conceptually performs a very simple computation. It takes a number of inputs. Here you can see an arrangement of neurons. So if we pick one, this receives a bunch of inputs from neurons that are arranged in the previous layer. And that the computation done by each individual neuron is just a weighted sum of the inputs plus the application of typically a nonlinear function that produces the output, which is propagated then to the next layers. And this weighted sum is computed through a matrix of weights, which is the most important trainable parameter or set of parameters of a neural network. And actually, training a neural network amounts to exactly that, to finding optimal values for these parameters such that some loss, some error is minimized. So this, in a nutshell, is how a neural network operates. And in order to be able to train these parameters, what you need is typically a training set. You typically want also a validation set, which is used to test the generalization capabilities of the network. And then you come to the testing phase and you want to know how it performs. So great. So this is the idea of this computational model. It has been around for a lot of years. If we look at the implementation in terms of code, it's pretty simple, and I would say boring. It's a straight line, straight sequence of lines of code that create a model. Here is a sequential model. It creates layers, so it adds layers and layers, and then it compiles the model with some optimizer, and then it fits the data. So it computes the weights by fitting the data. So from the point of view of software development, it's pretty boring. But it's also pretty different from what we're used to. First of all, there is no control logic. So let's take the problem of a self-driving car. Let's assume the car has an input, an image from a camera, and has to predict a single output. Here, this neuron represents the single output that we are predicting, which is the steering angle of the car. While the input, here you see a number of inputs, not all of them. Each input is a pixel from the image. Good. So if we want to do this kind of prediction, then we will not implement any control logic such that if the curve is bending to the left, then increase the angle by that amount. You don't have anything like that. You just learn the association between the pixels in the image and the output from the training set. So there is basically no control logic. Everything is data-driven. Second important feature is that we don't have any notion of correctness. We will come back to this later. Neural network make predictions that have some error. It has some error in the training set and some residual error in the validation and in the test set, and they never have zero error. Zero error does not make much sense in domains such as image processing, where the input space is very complex. So it's even impossible to define the expected output for all the possible inputs. So we don't have this Boolean notion of correctness. Instead, we have a statistical notion that is the notion of accuracy. So what is the proportion of images that are classified correctly, or mean squared error? What is on average the squared error in the steering angle prediction? And many things in the training process are non-deterministic. So at testing time, at prediction time, a neural network is completely deterministic. So if we give it an image, it produces always the same steering angle for the same image. But at training time, the initialization of the weights is typically non-deterministic, and many optimizers that are used, like stochastic gradient, to compute the weights are also non-deterministic. So this means that if you train twice the same model, the same architecture, you get slightly different networks and models that behave slightly differently on the same test set. And this is pretty unique of neural networks. So why are we interested in neural networks? Well, because it's a recent success story. So in many research areas that were dominated by statistical techniques or other modeling techniques, deep neural networks have become the state of the art. They basically outperformed any other computational model. So if we take the example of natural language processing, then if we look at the past, we had many approaches based on hidden Markov chains that were sort of successful, but nowadays, if you wanna do machine translation or language modeling or dependency parsing or semantic row labeling, the best way to do it is by using a neural network to do it, which outperforms any hidden Markov model. And the same happened in computer vision. Kalman filters and all the kinds of filters developed in that field are outperformed by the neural networks in many tasks like image segmentation, object detection. Speech recognition is another example. Speech to text is nowadays done by neural networks. And programming, that's an interesting application area because we have seen very recently neural networks like Copilot that take a line of text that describes what we want to do and generate code, compilable code that most of the time is pretty usable and does the job. So that's another very interesting task where neural networks are becoming successful. And of course, since all these tasks are very complex, they open to the possibility of incredible applications, autonomous vehicles, medicine, and there's a number of areas where they are increasingly used. So deep neural networks have been around actually for many years. Why are they so successful now? And the answer is that they have become deeper, which trivially means they have larger size, they can count on more computational power and bigger data sets. And that is what made the power of the networks increase substantially in recent years. In particular, for software engineers, using a neural network and incorporating it into a system is more and more easy. There are frameworks like TensorFlow Keras or PyTorch that provide very nice and user-friendly interfaces. And whenever a system has to process complex data, so if it has to process natural language or images or has to do classification using feature vectors or predictions, then it makes sense to use a neural network for that task because that's the state of the art, which means that we are increasingly seeing traditional software being integrated and cooperating with neural networks, with components that are deep learning components. At the bottom of this slide, you see one example, which is self-driving car architecture, where we have some input from sensors, which is pre-processed by a standard traditional software component. Then for a couple of tasks like pedestrian recognition and lane keeping, so steering angle prediction, we use neural networks because these are the components that can do better this job. But then the integration is still a traditional software component. So in complex software systems that manipulate complex data, we have deep learning, deep neural network components and traditional software. But as I already mentioned, with a traditional software component, what we can stipulate is a traditional contract, which looks like this. If the input X satisfies the precondition and like it is greater than 0, then the output Y that we get from the computation satisfies another post condition, which is the square, it gives us X. And this is, of course, the contract that a square root function would stipulate with the users of this function. With a deep learning component, it's completely different. The contract looks like this. The mean squared error on the test set is 0.01. So when predicting the steering angle, you have to expect in test mode this amount of error in the prediction. Or If you are solving a classification task like recognizing traffic signs or pedestrians, there's a level of accuracy in the task that is, let's say, promised by the contract, that is stipulated in the contract, but it's not 100%, it's not one. So there is still a 5% probability that there will be a misprediction, a misclassification in the field. And this means that we need different ways to ensure quality and dependability when dealing with contracts that look like these ones and are no more Boolean contracts for which we have a clear, well-defined notion of correctness of the execution. So in recent years, if you look at the last, I would say 10, 15 years in software engineering, software testing conferences, there has been an exponential growth of techniques that deal with deep learning dependability and deep learning testing. And what researchers did was to take the traditional approaches, typically show that they cannot be applied as is. I will give you some examples in a moment to deep learning, to achieve deep learning testing, and they have adapted them. And this covers all the areas of software testing. So from test case generation to adequacy criteria, to mutation testing, to the Oracle problem, to data selection, test prioritization, security testing. Any sub area of software testing that you can imagine has seen one or more attempts to migrate it to deep learning component to see what we have to do when we apply similar notions to deep learning components. So in the rest of my talk, what I will do is I will present you a problem that is well-defined, well-known in traditional software testing, but is not so for deep learning components. Then I will briefly describe some of the solutions that have been presented in the state of the art in recent years, and I will conclude with what I call elephants. So in English, there's a way of saying, which is there's an elephant in the room, which means that there's a problem with something that everybody is aware of, but nobody wants to talk about. And today I will not talk only about solutions. Of course, we made progress, but I think the difficult problems, the difficult bits in this migration from traditional software testing to deep learning testing, the difficult bits, I think they are still there. And today I would like to discuss them with you and to point to them. So let's start with one problem, which is test adequacy. Test adequacy aims at answering a very simple question, which is, I mean, pretty important for developers. Have we tested the system under test enough? And if you take a traditional program like this one that computes the triangle type for a triangle with sides ABC, then we have a set of test cases that tests, I don't know if something is not a triangle because it has a negative side, or if something is isosceles. Then we have this notion of coverage. So the simplest kind of coverage that we can consider in traditional software testing is statement coverage. And if we run these two tests here for this program, we will get this picture of coverage. Basically, 13 statements are executed, but 2 are missing. And the coverage is 87%. And these are the 2 missing statements, the ones that were not exercised by any test case. And of course, we know that we need more test cases because we want to test also what happens when we execute 11 or when we execute 13. So this notion is very well defined, it's very clear what you get if you apply these adequacy criterion and what you have to do to improve adequacy. Great. So let's now try to ask the same questions for deep learning systems. So have we tested the deep learning system enough? Let's take the steering angle predictor for self-driving car. So one possible test is this one. We take an image of a road, we predict a steering angle, and we get an angle, and then we say the prediction should be approximately, of course, this is a floating point, so it cannot be exactly, but approximately this should be 0.5 radians or degrees, I don't know the unit. Great. So we have a single test case, a single input. We run it. How much do we cover of the code, of the Python code that creates the neural network? Well, 100%, trivially, because there's no conditional logic, there's no branching. So there's nothing that requires specific input. At the same time, have we tested the system enough? I don't think so. So knowing that this test passes on a single image doesn't tell us anything about the capability of the neural networks to really drive a self-driving car. So clearly coverage in the sense of statement or branch coverage or traditional coverage is not enough for neural networks, and researchers have proposed a number of alternative adequacy criteria like neuron coverage, surprise adequacy, and mutation killing. Just to give you a quick idea about them, neuron coverage looks at the activation of all the neurons in the neural network. So this phi here is the output, the activation of a neuron for a given input. If this is above a threshold, the authors of this technique, of this adequacy criterion, say the neuron was activated, and basically we measure the proportion of neurons that are activated. And this is neuron coverage. And then you can be more fine-grained and you can say, okay, instead of looking at the output and the single threshold, we can look at the output and divide it into k beans. And then now we want to cover all the k beans for every neuron. And that's another notion of neuron coverage. It's called k multi-section neuron coverage. It was proposed a little bit later. And these were the first attempts to go beyond traditional coverage. Then, as I mentioned, there have been a lot of other works that proposed other adequacy criteria, but you got the idea. Basically, we have a neural network and we check how much of it was covered. Great. So what do we do in traditional software when coverage is not enough? Well, we add more tests because we want to test also the executions that were not tested before. What can we do with neural networks? Well, let's assume we have an initial coverage of 80%. We say that in terms of neuron coverage or surprise adequacy or whatever it is, that's not enough. We want to cover more, so we add more tests that increase coverage. Great. What do we do with these additional tests? If we train the network again using these additional inputs, then what could happen is that accuracy goes down because now we are focusing on corner cases that we don't want to be overrepresented in the neural network. So the puzzling bit or the elephant when we get to coverage for neural network is what to do with the coverage metrics, because adding more inputs is not necessarily a good idea if we want to predict or if we want to achieve a high accuracy in the field. So in general, the problem of knowing if and when it is beneficial to add inputs to the training set to get a better network is still completely unsolved. And having a given level of adequacy is not necessarily telling us that we need more inputs. Maybe this accuracy level is already the limit, and we have to expect 5% errors that cannot be improved. So adequacy is not currently a completely actionable criteria in deep learning testing. Developers of deep neural networks don't know exactly to do with a given level of coverage, and actually people have started to question neuron coverage or other coverage metrics for neural networks as a meaningful measure of how they work. So the general idea of migrating coverage is nice, but we are not yet there. There's still an elephant in the room that we have to address, I think. Second software testing problem, test generation. So how do we generate test scenarios that are effective at exposing faults? In traditional software, there's a huge and incredibly vast literature on how to generate automatically or manually test scenarios, test cases. People did it randomly. People did it in a coverage-driven fashion. So coverage is driving what you generate in a diversity-driven way, in a mutation-driven. So we want to kill mutants with the generated tests, or in a black box way by covering the equivalence classes or the boundaries between classes. And now all the idea behind all these different approaches to do test generation is that we have a goal, which is maximizing coverage in the second case here, or maximizing diversity. If we achieve our goal, then we are more likely to expose faults. That's the assumption of these techniques. In the panel in the afternoon, we will be talking about some of these techniques in particular for traditional software. Great. So as you can imagine, people migrated many of these ideas to test of deep learning components and came out with novel techniques to generate test scenarios, test inputs for neural networks. And here you see a non-exhaustive list of the approaches. Here, really, we had a lot. Adversarial examples was historically one of the first to generate inputs that are challenging for a neural network, but then we had generative networks. Of course, we have neuron coverage, so we can use it to drive test generation. Uncertainty is something we can measure for neural networks, and we can use it to generate inputs. Surprise, mutation, and frontier. These are also concepts that can be used to support test generation for deep neural networks. Great, so let me quickly tell you something about a couple of these techniques, like the adversarial test generation. So in adversarial test generation, what people do is they take an input, then they find, like a traffic sign, they find the components, the elements in the input that are affecting the output to a major extent. And in this case, it's this pixel here and this pixel here. Then they manipulate these inputs to get a different outcome. So by changing these two pixels in this way, the traffic sign is no more recognized as a left turn, it's recognized as something else. Here, the green light, if you change this pixel, becomes a red light. So these are called adversarial examples, and they are minimal changes to the input that produce a misbehavior. In generative adversarial networks, instead, people use the neural networks to move an input from one domain to another. For instance, we can take an image to be processed by a self-driving car taken in sunny conditions, and we can use a generative adversarial network, again, to introduce snow artificially into the image in a very realistic way. So the ones that you see here, they are images that were originally taken in sunny conditions, and then snow was added by a gun. And then people compared the prediction in the original and in the new condition, and if the two deviate, then by differential testing, they find something that might point to misbehavior. Great, so I gave you some ideas only of the first two families of approaches. These are really families because there are many techniques inside these big families. There's also other families, at least 5 more, with a lot of techniques, but you got the idea. Here the idea is how do we generate inputs that challenge, that produce misbehavior on neural network. And that's definitely useful. It's potentially quite important, but again, there's an elephant in the room, which is the validity or the realism of what we get. For instance, if we change an image of a road to an extent that it would be impossible even for a human to drive that road because the road is unrecognizable, is it still a valid input? Does it still make sense that the neural network, saying that the neural network is producing a misbehavior or a prediction that deviates a lot from the prediction in nominal conditions? So the problem of narrowing down the generated inputs to the valid ones, that are the ones that really matter because they are the ones that can be found in the field, is still an open problem. So people find a lot of inputs that potentially generate misbehaviors, but we don't know if these are actually relevant or valid. And a related question is that of realism, of naturalness. So if by valid, I mean something where a human can handle the input. So for instance, we have a traffic sign, it's valid if a human can tell what traffic sign it is. Good, but the second aspect is that of realism, of natural or naturalness. So a traffic sign that has a couple of pixels properly chosen, manipulated, is definitely not realistic or not natural. It's not something that you can expect when driving in real conditions, in real roads, because of the way the pixels were chosen, because these are the ones that produce the maximum deviation in the output. So that can happen if we have an attacker attacking the deep neural network. Then, of course, the attacker can manipulate intentionally those pixels to get a misbehavior. But it's very, very, very unlikely that we see this in reality natural conditions. So again, that's an aspect that is not considered very much, and adversarial examples are very useful for definitely for security testing of a neural network. But if we want to know the dependability in the field, I don't think they are the best technique to use. Great. Mutation testing and mutation analysis is another technique that is widely used with traditional software, and one of the first works that proposed a mutation for deep learning component is Deep Mutation++. It was proposed in 2019 at ASE. And it is pretty simple. We have a neural network that is basically a collection of weights, represented here as the connections between neurons, and we change one or more to another value, and we get a mutant. And if the output of the original network differs from the output of the mutant by more than some threshold, then the mutant is killed by the input X. If no input X can do this, so no input can produce a different output, then the mutant is unkilled, and we need more inputs to be able to kill it. That's how the traditional mutation analysis idea has been migrated, I would say, to deep neural networks and deep learning testing. Great. So one of the issues behind this approach is that this test here is completely deterministic. So we have one output of the model, one output for the mutant, but in reality, if we train the model twice or the mutant twice, we get different outputs. So we cannot, we might, in this equation here, we might replace M prime, the mutant, with M. So we can have M trained the first time minus M trained the second time, and still the difference could be higher than some threshold, which means nothing. It just means that the training process is non-deterministic. So this non-determinism is quite important when we are making reasonings, when we are analyzing the output of a neural network, and we cannot just treat it as a traditional deterministic output. We have to take into account the non-deterministic behavior that is associated with training and multiple trainings. Second elephant is the coupling, the so-called coupling effect. So one of the reasons why mutation testing is so popular is because people believe that the coupling effect holds, which means that defects introduced artificially through mutations are representative of real faults. And if we have a test suite, a set of test cases that can expose the artificial faults injected through mutants, then that test suite is effective also at exposing the real faults that can affect the real system, not the mutant. So this is called the coupling effect. And when we are changing the individual weights in a neural network, so we are picking some of them and changing their value, here there's no insurance of the coupling effect. So how do we know that this change here is coupled with a fault, that a real fault that a deep neural network developer would or might introduce in neural network? And this is a big elephant. So it's great to have these mutation analysis and mutation testing tools, but we have to go beyond that. And I think questioning the coupling effect and investigating it is quite important for the future. Test oracle, that's another big issue, big problem in traditional software testing. If we have a program that computes the triangle type, we have the specs that define formally the different triangle types. Then when we have a test case, like the invocation of triangle type with 2 to 3, we know what to expect. Here we would expect isosceles. In that case, the execution is correct, otherwise it is not. Great. What's a test oracle for a deep neural network? Well, we can say that for a given input that represents a handwritten digit 0, the output expected is 0. For a given image of a road, the angle should be 0.5 with at most some error, but here again there's an elephant. If we just look at the output and the accuracy of the output for individual predictions, we know we don't know much, or we don't have, let's say, complete knowledge of what to expect at the system level. So we might have inaccurate predictions on individual inputs that are compensated by the overall system. So we can have individual errors that might violate this assertion and accumulate and are compensated at the system level, and there is no misbehavior of the system. Or the other way around, we might have little errors below the threshold that we check in these assertions, but they accumulate and they lead to a system level failure. So we cannot have oracles that talk only about individual predictions at the unit level, at the level of the individual neural network. We need some way to reason on the misbehaviors of the entire system. And there's an interesting paper presented at ICST 2020 that compared offline, which means single predictions like these ones, to online testing, which means testing when the neural network is operating in the field, like in a self-driving car. The other important area where there's a bit of research, especially in the AI field, in artificial intelligence and machine learning, more than in software engineering and software testing, is about understanding the conditions of misbehaviors. So here it would be quite important to report, when we do deep learning testing, to report to developers inputs that trigger misbehaviors, but also to point to the reasons why we have misbehaviors, so to the features of the inputs that produce a misbehavior. And there's an area of AI that is called explainable AI that goes in this direction, because they look at the inputs and they try to find the reasons why we have a given prediction, a given behavior of a neural network. And here you can see some examples of these explanations. So the reason why a given digit was predicted to be a 0 is because of these pixels. So these are the pixels that are, the light pixels are the ones that are most responsible for the prediction of a digit being a 0 or being a 1 and so on. So with these explainable AI maps or heat maps, we can understand what are the parts of the inputs where the attention of the neural network is mostly focused. But this does not necessarily point to features of the inputs. So here I think we are still far from an interpretability or an understandability of the misbehaving inputs that is really actionable for developers. Because from this low-level information about the pixels that are responsible for a prediction, we don't know in what ways we should improve the neural networks or the training set, or we should improve the test set for the neural network. So to summarize, in the talk I presented 6 elephants, 6 areas of future investigation where I think the existing literature made some progress, but now is sort of hitting a wall, and we need a way to jump over the wall, to go beyond the problems that we found. And one is test adequacy. So how do we know if improving adequacy is effective in the field? Test generation, how do we know about validity and realism? Mutation analysis, we have the non-determinism problem and the coupling effect problem. Test oracle, where we want to reason at the system level and understanding how do we know the input features that make a system misbehave. So these are big problems. They are non-trivial ones. I think they are the ones that typically in the initial phase of migrating from traditional to deep learning testing, people sort of ignored or didn't consider in depth, but that's to me where the future research should go. And in our pre-crime European project, we did something in that direction. So now in the final part of my talk, I would like to tell you about some recent results that we obtained that go in the direction of addressing partially, not all of them, but some of the elephants. Of course, these elephants are difficult to deal with. I think they will require more research than, I mean, the initial one that migrated the traditional software testing techniques to deep learning, but they are also very challenging, very interesting research directions. So about validity, what we did in pre-crime was to develop a technique for test input generation that is based on the notion of frontier. So we don't want to generate, here you can see the input is a digit for a classifier of handwritten digits. We don't want to generate a digit that is very far from the inputs that are classified correctly, something that is misclassified, but just because it doesn't look really like a 5 or any realistic digit. So to achieve this goal, we introduced the notion of frontier. A frontier is a pair of inputs that are very close to each other, like these two, but on one of them, the network behaves correctly, on the other one, it misbehaves. This is classified as a 5. So the hope is that if we are at the frontier, then we have more chances to produce valid, realistic natural inputs. And then, of course, to know how we performed, we did a human study. So we asked about the validity of the inputs to humans through questionnaires. And what we found is that first, our technique generates a lot of valid inputs, which is good. And second, we found that as expected, this depends on the quality of the neural network under test. If a neural network is low quality, the blue one, then it's easier to stay in the validity domain and generate frontier inputs. But if a neural network is high quality, like the orange one, that's more challenging, and of course that's expected. So if you really want to generate a misbehaving input, you have to go probably beyond the validity domain, which is something that we conjecture from the beginning. In the area of mutation analysis, we have introduced the notion of mutation killing that is non-deterministic, that is statistical, to take into account what I briefly described before. If we have an original program, an original neural network P, and we train it 100 times, each time we measure the accuracy on the test set, we will get a slightly different value. Here, the median accuracy is something like 75%, but there's some spread between 70 and 80% with some scattering of the distribution. If we do the same for the mutant, train it multiple times, measure accuracy, the accuracy is distributed like this. So how do we know if the test that we are using is enough to discriminate the mutant from the original program? We cannot just do a single run and compare accuracy, because we might get exactly the same accuracy. That does not mean that the test suite is not able to discriminate. It might just be due to chance. So to take into account the statistical distribution of accuracy, what we do is we propose to apply a statistical test like Wilcoxon to compute a p-value that tells us the probability of a type 1 error, basically the probability of an error when we reject the null hypothesis. Rejecting the null hypothesis for us means that the two distributions are different, which means the mutant is killed because the accuracy has dropped on the mutant. So in order to be able to reject the null hypothesis, what we require in our is killed mutation killing criterion is that the p-value is small, so we minimize the chances of a type 1 error, and that the effect size is non-negligible. If this happens, then we can reliably, from a statistical point of view, say that the mutant is killed, and this was presented at ICST in 2020. To go in the direction of ensuring that the coupling effect is valid, holds, we developed our own mutation analysis tool for deep neural networks, which is called DeepPrime. In turn, this tool is based on a previous work that we did, which was the construction of a taxonomy of real faults for deep learning components. And DeepPrime is not really mutating individual weights of a neural network. It's not picking a weight and changing it. What it is doing, it is simulating the process of introducing a real fault that we have observed in the field with real developers. So for instance, it takes the training set and it makes it unbalanced, because unbalancing of the training set is one of the real problems that developers encounter when training neural networks. Or looking at the architecture, DeepPrime can make the architecture suboptimal by dropping some layers, or looking at the hyperparameters, it can change the learning rate to make it inaccurate. And all these are based on real faults. So in this way, we get a mutant that has more chances, that is more likely to satisfy the coupling effect, to really be coupled with real faults. Of course, we have not shown yet with this work that the coupling effect holds. Actually, even for traditional software, there's no final answer to this big question. So I expect that even in deep learning testing, it will take quite some time to get even some attempts of answering the overall question, which is a big one in my opinion. But with DeepPrime, we are simulating real faults in a neural network, and this approach was presented last year at ISTA. About the test oracle, so we said that the oracle that we have are at the component level, at the deep neural network level, which do not necessarily correlate with system level failures. So in a work that we presented at ICST last year, we proposed a set of quality metrics and oracles, in particular for self-driving cars. So when you have a model like Dave2 or Chauffeur or Epoch, these are examples of neural networks that are widely used, architectures that are widely used for self-driving. You can observe different driving styles. Here in particular, the green and the red are under different conditions. But in general, even if you compare different models, you see different styles. So what is a good or a bad quality of driving? And in this work, we investigated a number of metrics that have been proposed to assess the quality of human driving under various conditions, especially when the quality of driving deteriorates, like under the effect of alcohol. And we have checked the validity of these metrics and proposed new ones for self-driving cars. And here you can see some. So standard deviation of the brake level is one metric that tells you a lot about the quality of driving for a self-driving car, the standard deviation of the lateral position. And we had a bunch that have been proposed going in the direction of having oracles that work at the system level. I talked about understanding and explainable AI, which potentially is very important, because when we get a misbehaving input, we also want to know why the neural network is misbehaving for a given input. But as we have seen, knowing at a low level that a particular pixel is responsible for a misbehavior is not particularly useful or informative for developers. Good. So In our ISTA 2021 work, Deep Hyperion, we propose to use human understandable, interpretable, high-level features. If we have a digit to be recognized, a handwritten digit, the orientation of the digit, where it is tilted on the right or on the left, it's a clearly understandable feature. The luminosity is another easily understandable feature. If we have a self-driving car, the minimum radius of the curve or the mean lateral position, these are pretty clear and pretty understandable features. So we have defined feature maps that take inputs and map them to an understandable and interpretable feature. We have produced a test generator called Deep Hyperion that can populate a feature map like this one or this one. And this tool is also trying to expose misbehaviors in each cell of the map. So the cells that have a bold contour are ones where we have misbehaviors. And sometimes having a particular region of the map with misbehaviors can be interpreted in a very discriminative way. So if you want a misbehavior, if you want to expose a misbehavior for the driving model that we are testing, the conditions that we have to achieve is a curve with a mean radius in this range, and we have to be able to generate a behavior of the car with a given mean lateral position. So these are definitely more interpretable. I'm not saying that we solve the problem. Of course, the problem of understandability of the inputs that are generated by automated test generators and automated and interpretability of the inputs that are generated automatically is still an open problem, but this goes in the direction of improving the interpretability and making automatically generated inputs more interpretable. So with this, I think I'm at the end of my talk. This slide is just showing you again the elephants, because now I want, of course, to hear your opinion about the elephants, your questions, your comments. I'm very curious about your reaction to my talk.
Well, congratulations, great
So,
keynote.
indeed. So I think while we are waiting for question on the chat, maybe I will try to open so that maybe people can jump on the conversation. During the keynote, Paolo, you mentioned a lot of problems. Actually, I think open problem about level of realism, of explainability of AI-based system, and you talked a lot, especially in the last part, on the certainty of an environment. But you also know that AI-based system have the problem on non-determinism. You give the same inputs and probably would be a non-deterministic behavior, even though you have an environment that has, for some reason, the same conditions. So here the question, do you consider we should be considered to address the problem of non-determinism in a specific sense? Do you think that humans should be considered in the loop in some way, just in a broader sense?
Yeah, thanks, Sebastian. It's a very interesting question, an important aspect that I didn't touch, because I talked about the non-determinism of the training process, which is one source of non-determinism, which is very often overlooked by researchers. But you're right, there's another source of non-determinism, which is the environment where these systems operate, because typically they are operating in very complex environments. If we have a self-driving car or a drone, I mean, any simulator, or I mean, if we are in the real world, that's even worse. You cannot have exactly the same conditions. All the simulators, to produce realistic effects like the wind or the light, they have some non-deterministic behavior, and if you run the same test twice, you get slightly different outcome, which means that we have at least two sources of main sources of non-determinism. One is the training process, but the other can be also the environment, especially if you have a complex environment. So what can we do about it? Well, we have to randomize, of course, across both sources of non-determinism, but this comes with a big problem because it takes a lot of time. So if we are talking about a simulator, it means that we have to run, just to get a single answer, like a single level of accuracy, we have to run the simulator a lot of times. So I think that's another important direction of future research, which is how can we optimize the executions of tests in environments that are non-deterministic to be able to still get valid results. Otherwise, really, we have to allocate clusters and days of computing time to be able to get any answer for the techniques that we want to develop. So yeah, you're right. That's another big problem that we have.
No, but I mean, you were very comprehensive. So I was just curious, to have your thought on that part, that I think you are for sure not overlooking, you're for sure focusing, but was curious to hear from you. I don't know if Giovanni, you had a question also from your side. I will have another, but probably, Giovanni, you have maybe come from your side, and there will have maybe other from the
sure.
audience.
Well, thanks for the great keynote, Paolo. Very insightful. And my question is more like a provocative one. What would you consider a bug in a deep learning system? Would you consider a misclassification as a bug, or how? I saw many discussions about it in other papers as well, and I want to know your opinion on that.
Yeah, that's a very good question. It's another elephant that I touched only marginally, but it's a very important one. So of course, for researchers, it's the simplest choice of definition is misclassification is a bug, because then you can count. It's easy. You can propose a new technique. You count the new misclassifications, and you are done. But that's not the end of the story, because to me, a bug is something that affects the development process. It's a mistake, in a way, done by developers in the process. And when we have built the taxonomy of real faults that was the basis for deep crime, we looked into the way developers of deep learning components can make mistakes. We looked at different sources. We mined GitHub and extracted the different comments on the issues that are traced there. We looked at Stack Overflow and the faults that people report there and ask questions about. We also interviewed a number of developers who are active in the construction of deep learning systems and components, and we collected a taxonomy of faults that affect deep learning developments. And these faults are, I mentioned some of them, and they are sort of implemented in deep crime. They affect typically either the training process, so they can affect the training data. So you have a bug if the training data is unbalanced, if a class is underrepresented, or if some conditions are underrepresented. They can affect the architecture of the neural network that you're using, because some layers that are quite important to extract some features are missing, or they are not sized properly. They might affect hyperparameters. The learning rate might not be properly set. So there's a number of bugs, and these are the faults. So if we're talking of what is a fault is something like this. The learning rate is set wrong, or the training data misses some particular kind of input. Then a symptom of this could be a misclassification, but when I talked about contracts, misclassifications are always there. If you have 95% accuracy or even 99% accuracy, 1% is still misclassified. So discovering one more or even 100 more misclassifications is not really telling you that you have a bug, unless you can, let's say, connect this misclassification to something that was done wrong in the training process. So some classes that are missing, that are important to be added, or some hyperparameter that was set wrong, some architectural choice that was wrong. And of course, making this connection is way more difficult than counting misclassifications. So everybody does the latter, but you're right, it's a big elephant. The other aspect is that we don't have a repository. So in traditional software, we also are missing repositories, but at least we have things like defects4j. So we have well-documented bugs that we know where they are, and when we create new tests, we know if these bugs are exposed or not. We would need something similar for deep learning components, because then we could say this input generation technique is able to expose a real bug, something that was done wrong for real in the development process of a neural network, not really something that is just misclassified.
I see.
So thanks. It's a
Thank
very
you.
good comment.
Thank you. Very clarifying, by
Got
the
a
way.
question on the chat, Paolo. I don't know if you noticed. How does the traditional mutation analysis compare to deep learning specific mutation analysis, the leading statement or an expression? I think it's quite it's an interesting question. It's in the chat, Paolo. You can also read it.
Yes. I've seen that. That's also interesting. I mentioned in my talk a work that we presented at ICST in which we investigated empirically existing tools for mutation analysis of deep learning components. We focused on, in my talk, I focused on the notion of mutation killing because it's quite important to make it statistical. But we also investigated this aspect, which is what if you apply traditional, let's say, mutation techniques and like deleting statements or expressions. And what you get is that the symptoms, the effects of these changes are typically much more visible. They either make the network no more compilable, or the training process fails with some exception, or you corrupt the shape of the input. So you can still do that. You can still inject traditional faults and find maybe something interesting, but it's a completely different category of faults. You cannot expect, so for instance, if your training data is unbalanced, it's definitely impossible to see this by changing randomly some statement in the program that creates the network and trains it. So the let's say traditional mutation analysis remains important, especially because these libraries like Keras or PyTorch are complex, so it's possible to misuse them. It's possible to introduce bugs in a way they are integrated in the system, but the two kinds of faults are quite disjoint from each other. So if you want to discover the faults that are specific to the training process of neural networks, then you need specific mutation operators.
I think I would add another question. I think there's still time. You mentioned, Paolo, during the talk about understandability or explainability of AI, and I usually associate it, maybe I'm wrong, on trustability of AI. So if you go, whether with researcher or practitioner, you want to make sure that this in AI system is trustable. It's a very difficult problem, but at least if you are able to make it explainable, we can find out what is wrong in it. So here, just to mention an example that you referred in the beginning of the talk, Copilot. Now you can create from text code, but there are also recent results that demonstrated that generating code from open source projects can generate unsecure code. So here, when using AI, it's very sensitive to the data. So what we should do or consider or should not do when using AI, or if you want, or what we should do for ensure reliability or testability of such system. It's a bit broad topic, but I wanted a bit.
No, I think that's very interesting. It's really looking deep ahead in the future because we are not yet there. Unfortunately, I mean, we are still the ones who program, and it's not an AI who programs instead of us. But looking at the example of Copilot, it's not a science fiction future. It's something that is increasingly, adopted. I know that developers, real developers, are trying to use Copilot sometimes they just to see what they get, and sometimes they get something useful and they use it. They change it a bit and they use it. So probably this has the potential to revolutionize the way we develop software. And as you said, being a software engineer maybe will mean testing the software that an AI produces, or testing the trustability or security testing, what it does. I don't know. I don't have an answer, but it's really fascinating to think of what could become software testing, software engineering in this future where AI create software or create code with us or instead of us.
Great. I think we are reaching sort of the end of this amazing keynote. I think the question and answer was very exhaustive. Thank you, Paolo, really. or Esau's talk and engage with all answer very assistively. I think we will have quite a few minutes of break after that, so will be a fresh energy for the next section. So let's thank everyone for what's joining here. Paolo again, and we see you in a few minutes after the break. Should be 15 minutes or so.
All right. Welcome back, everyone. After the break, now we are starting the second session of our workshop. Now, for the second session, we are going to start the tutorial by Rahul Gopinath. He's a lecturer at the University of Sydney, Australia, and a great researcher on mutation testing. I cite him a lot, by the way. And today he's going to give us a tutorial on learning and refining input grammars for effective fuzzing. I shared with you the link to the tutorial. It's on the chat. And well, welcome, Rahul. I hope you have a wonderful time at the workshop, and the floor is yours.
Give me a second.
Okay, no problem. And
I don't have access to sharing this window. Let me see again. Okay, I need to enable something before I can share. Sorry about that.
I think.
Yeah, I think so. I did not have this problem in Zoom, so I was not aware of.
Are you using Google Chrome?
I'm using Opera, which is I couldn't use Google Chrome because it was giving me a repeated looping for redirection. Okay, so
no problem.
This.
And everyone, if you have questions during the tutorial, you can type them on the chat. And during the question and answer, you can also ask them yourselves. So, yeah.
Okay. I need to quit and reopen before the permissions are.
Okay, let's just wait a little bit more. Everyone, stay tuned. And just after the tutorial, we are going to have a quick break. No quick break. After the tutorial, we're going to have a paper session. So stay tuned, everyone. Now we can see your screen, Rahul.
Okay,
thank you.
That is great news. Wonderful news. Okay, I hope you are able to see my window. Not yet. I can see. Not yet. Okay, so are you able to see the learning and refining input grammars for effective fuzzing? Hello, Giovanni. Are you able to? Okay. Okay. So again, thank you so much for introducing me. I am currently a lecturer at the University of Sydney, Australia. And my main research is on static and dynamic analysis of software, with a focus on fuzzing and specification mining. So before I start, please go to my SBST GitHub webpage, and you will need Python 3.10 to follow along in this project. Other versions of Python might work, but Python 3.10 is where I have tested this. And once you have Python 3.10, install the Jupyter notebook. Then clone the repository and finally start Jupyter within the repository directory. So I already assume that you have the Python and you have installed Jupyter. And here is how you would start the Jupyter notebook. Once you start the Jupyter notebook, you would be presented with a tree, a structure like this. This is the Jupyter notebook structure, and these contains our notebooks. So once we have that, the roadmap actually contains the organization of this tutorial. You can click on the roadmap. So here's the roadmap. When you click on the roadmap opens up, and here are the links to each of these GitHub Jupyter notebooks, and you can follow along on each of the notebooks. For example, you should go to the prerequisites, and you should actually run it all. Click on the kernel, and then restart and run it all, so as to make sure that all the prerequisites are completely executed. So this contains a few of the Python packages, a few of the Jupyter notebook packages that are important, especially the side index that you see. That is a Jupyter extension that you will want. So once you have that, so let us now start our tutorial. Now, search-based software testing is the application of optimizing search techniques to solve problems in software testing. One of the chief concerns in software testing and search-based engineering in general is defining the search space, because in most cases, the effectiveness of our technique depends on the search space that you have defined. Now, if the search space is too large, then it may be impossible to explore it effectively within the budget that you have. So for search-based software testing, the search space is defined by the input space. And especially for fuzzing, it is defined by the input space. So in this tutorial, I'll be focusing on effective techniques to reduce the input space of the programs. In particular, since the theme of this year's SBST is fuzzing, I'll be focusing on how to make fuzzing more effective by constraining your input space. And in this tutorial, we will examine a suite of techniques that you can use on real-world programs to focus your searching techniques search space. Now, the example that I use is fairly simple, but it can be applied to pretty much most of the parsers in the world. And I have worked out examples that you can actually look at for other examples. So let us consider fuzzing. So fuzzing is fairly simple. The idea is that no system should crash when you are given any input. So fuzzers try to generate random inputs that can induce crashes when the system is under test. So here is how we fuzz. We generate random input, which is then fed into the program. If the program crashes, then we have found a likely vulnerability because the input was unexpected by the program. That is, there's a logical flaw that could be subverted. Now, fuzzing is effective if the fuzzer can generate sufficient inputs that can exercise all parts of the program. And naive fuzzing is not very useful when the program under fuzzing expects even moderately complex inputs. For example, we use feedback-driven fuzzers such as AFL, and these are typically paired with search algorithms to ensure that the fuzzers can penetrate deeper into the program. And we will see one such generator next, and that is in our tutorial. Okay. And second. So this is in generating samples. You should be able to see the generating input samples. And if you click it, then the Jupyter notebook will load. And within the generating samples, you can start execution. And I will explain the rest of the details along the way. So here we can import our calculator, which is essentially our guinea pig for the day. And we need an error handler. And then we have a simple random fuzzer. And this naive fuzzer simply generates a number of random characters, which are then we can actually feed that into the calculator. And let us see whether calculator actually, it generates anything that the calculator finds to be useful. So unfortunately, this is rather unsatisfying because generating it this way, a calculator is not going to actually find anything that is useful. I mean, these are totally random inputs, none of which is likely to get past the parser. So let us actually try observing the error. So if you add something extra, then calculator tells us precisely where this parse error occurred. Okay, this error occurred at line character 5. So we can see that. And we can actually add this feedback to our fuzzer and make the fuzzer a little more intelligent. So you can say, okay, there is an unexpected character here. And if you add a non-terminated expression, then you can get a unterminated status. And you can also check whether a completed status is available, etc. Now, once we have this, then we can feed that to an evolutionary algorithm where we can simply say you have a fitness, a particular fitness if the input is complete. If you get an error that is unexpected, then the fitness is slightly different. And instead, if you have something unterminated, the fitness is again different. Now, in these places, you are actually the experts. This is a very naive evolutionary algorithm that I came up with just to show that this can be done. And we have an evolver, and we just verify that the evolver actually gets the fitnesses right. And once we have that, we create this initial population. Some error, but ignore that. And if you run all, you will actually find that it is able to generate fair inputs after a while. So these are generating inputs that can be that are actually accepted by the calculator sometimes. So here, this is accepted by the calculator. This is accepted by the calculator. So you can technically generate inputs that are accepted by the calculator. And we also have a similar example for JSON, where it tries to generate JSON inputs. Now, this is not all. Let's go back to the presentation. So for fuzzing parsers, we can make use of the search-based generation, as we said earlier. Now, another interesting technique that you can use is essentially to attach a feedback, attach instrumentation to it. And what we do is to adapt a hill climber. So we start with an empty string that is fed. So in the case of hill climber, our neighbors would essentially be anything that is one character extra to the program. So we start with an empty string and then try to generate its neighbors, which is one character extra long, and see whether the neighbors have a fitness that is beyond the previously existing string. So we start with an empty character, then attach a neighbor A, and then check whether it is actually accepted. But because we have instrumentation, we would know which characters this particular added character was compared with. Choose one of these characters, and then replace the neighbor with the next one. And then try again, attaching another character, and then choose again and again, until we reach a complete string. And we will see the implementation of this algorithm next. And this is in the track access notebook. Okay. So here again, for attaching the instrumentation, we use a proxy object. So the only instrumentation that we use here is essentially to proxy the input string. And we track the input characters, where exactly they are being accessed, in which location of the program these input characters are accessed in the past input string. Once the input string is transformed into any other data structure, we stop accessing. So this is the proxy object that we have. And then we can actually see that the proxy object is actually able to access, to tell us exactly where these character access occur. So here, because we looked for a space, we can see that. So here, the first proxy object is actually telling us about where the inputs came from. So if you actually split this my string into two, then the origins are actually mentioned specifically in the substrings that are produced. And again, if you create a range, then that particular range will also have a date. And then the xtxtr implements the comparison, the proxy object that captures the comparison. So here we do that. And then once we have that, then we look at our calculator, which is our example. So here's our calculator example. And then we'll see how we can actually modify the calculator example so that we can capture our input accesses. So we slightly rewrite the source code so that we can capture these input accesses. So we have a rewriter, and then that. And we can actually now capture all the character accesses in parse expression within the calculator. Now, once we have that, then we can simply run it through our fitness algorithm, a simple hill climber. And now you can see that the hill climber is actually able to generate values which are actually fairly reasonably calculatorish. So this is an example that will actually pass in to the calculator, and the calculator will accept it. And remember, we did this without the actual specification of the calculator. That is, we do not have the grammar of the calculator at this point. So if you can actually attach some amount of instrumentation, then you can manage to extract, to generate inputs for these input programs. So that is what we did. Now, this is actually very useful, but it's a little unsatisfying. The issue is this, that each time that you want to generate an input, we have to resolve our constraints again and again and again. And just for generating a single new input, you had to run through the entire solution, entire generation again. So this means that we are not actually making use of our testing budget that well. So this results in two major problems. The first is that it's very difficult to control the fuzzer without also impacting the non-deterministic behavior of the fuzzer. And this is important because we rely on the non-deterministic behavior of the fuzzer to be optimal in terms of search strategies. So we don't really want to impact on the non-deterministic behavior. And the second is that we spend our testing budget essentially essentially resolving the same constraints and again and again. So what is the solution here? One solution is to extract these constraints directly. That is, we want to constrain the search space. And how do we want to constrain the search space? We can actually extract the input grammar of the program that we are looking at. And once we have the input grammar, then we can use this input grammar to generate inputs that conform to this input grammar. And that will let us produce inputs that will get past the parser and into whatever is actually behind the parser. So this is what we will look at next. Now, what is a grammar? A grammar is a formal language description that specifies how an input is constructed. And there are different kinds of grammars based on the power of the grammar to construct increasingly complex inputs. And the simplest is the regular grammar, which can construct simple inputs that can be matched by state machines, that is, regular expressions. And the next is a context-free, next are context-free languages. And these require a stack attached to a state machine for recognition. And these are called push-down automata. And then we have things like recursively enumerable languages, which can be matched if you add one more stack to the push-down automata. And these are equivalent to Turing machines. Now, of these, context-free languages provide a good balance between the ease of parsing and generation and power. So most programs use context-free grammars as the base grammar. So we'll be focusing on context-free grammars in this tutorial. So here is an arithmetic expression grammar, which is a context-free grammar. And a context-free grammar is just like a procedure definition in programming languages. We have a number of keys that have associated definitions. And each definition contains multiple expansion rules. And each expansion rule defines one way to expand the non-terminal and contains terminal and non-terminal symbols. And each non-terminal symbol, in turn, has their own definitions. And terminal symbols are simply basic alphabets of the input. And the main grammars used in this tutorial are provided in this notebook. So if you go to the Jupyter notebook, you will see the grammar definitions here. And this contains our definition. And here is an example grammar. And that, as you can see, this is just a Python dictionary where the key represents the non-terminals and the definitions are simply a list of lists. And each internal list is the rule, which contains a list of tokens. And a token can be a terminal symbol like plus or a non-terminal symbol like term. So this is an expression grammar, and this is a binary Boolean expression grammar. So these grammars can be used for parsing. For example, given the arithmetic grammar, we can parse the input 8 by 3 into 49 into a parse string. Again, we have a parser in our tutorial. These are our library functions that we use within the tutorial, but they are these are well-known external algorithms. So I will not be actually discussing what these algorithms are. This represents an early parser, which is a complete parser for context-free grammars. It can actually parse things like ambiguous grammars, and it can produce reasonable output in linear time if the grammar that is provided is non-ambiguous. And these are really good in terms of using the grammars that are used by traditional programming languages. So this is a parser that you can actually look through. This is well documented. So let us go back to our tutorial again. Again, beyond the parsing, we can also use the grammars to generate nearly an infinite number of varied inputs, all conforming to the input specification. That is, given the input grammar, we can now go beyond the parser and reach deep code paths. And the grammars can also be very efficient in generating inputs. That is, we can now compile a grammar to produce a fast test input generator. And we have a test input generator, a grammar fuzzer, and that is the grammar fuzzer. And it produces fairly fast fuzzing. It produces fairly fast fuzzers, so we can use that in the tutorial. Now, grammar-based fuzzing is not a new idea, and there are a number of fuzzers that use grammars to generate inputs. The question is, where do we get these grammars from? And in many cases, the grammars may be available as a reference artifact. However, many programs do not come with a grammar. And even when they do, the provided input specification may not really be a whole story. So what do we do? The issue is that we cannot really trust the reference, the artifact, the grammar artifact that the developer may supply, if the developer actually decides to supply it. So what we can do is to mine the grammar from the program itself. And once we have this mined grammar, then we can use the mined grammar to generate inputs that get past the parser of the program. So going back, this is actually implemented in mining grammar. So that is 2.0 mining grammar. So it'll take a little bit of time to show up. Okay. So, yeah. So before I start, let us go back to the Keynote. And so the main idea here for mining the grammar is that the handwritten parsers that are actually used in these programs, they actually already encode the grammar in a recursive descent fashion. So if the program is written in recursive descent fashion, which is a traditional style, then that particular program already encodes the grammar in its control flow. So all that we have to do is to recover this grammar from the control flow. So what we do is to start by recovering the input string accesses. And we have already seen how to recover the string accesses from the control flow. So what we do here is to attach where in the program the input string characters were accessed. And once we have that, we attach the control flow information into that particular trace. And then we extract from that particular input comparison trace, we extract the dynamic control dependence trees that cover all features. And from the dynamic control dependence trees, we generate parse trees. So what is a control dependence graph? A control dependence graph is a graphical representation for the program where each statement gets a node. And there is a directed arrow between control dependent nodes. And statement B is control dependent on statement A if A determines if B executes. And each statement execution is represented as a separate node. And a dynamic control dependence tree is similar to a control dependence graph, except that we use statement executions. Essentially, each executed statement in a program is a node in the tree. And each statement execution is control dependent on the statement that caused it to execute. So in this tree, we attach the input indexes that we mined using the proxy string. And each input character is attached to a leaf node that accessed it last. And this makes the dynamic control dependence tree a parse tree. And here's an example parse tree for the arithmetic expression 9 plus 3 by 4. So let us see how that is done. So we come back here, and then we start. By importing all the inputs, and then we have a context-free context manager that keeps track of where exactly in the program the character accesses are made. So I'm simply stepping through, but all these things are well documented. So once we have the context managers, we rewrite our program so as to use these context managers that attach the information on the control flow that is traversed by the program when it executes. So here is the context manager that contains a method and a while loop. And here is the stack wrapper. That's again another context manager. And we add. So here is our full program after rewriting. So here is our full program that includes the context managers that I talked about. See, so these are the context managers. So we wrap all the conditionals and the loop conditions in context managers. And this attaches the information as to the character accesses. Once we have that, And once we have this, then we are ready to generate a trace. So we execute this. And here is our trace. So these are the character accesses that were made when we executed the program with the input 9 minus 16 plus 6, 72 into 3 divided by 458. So you can see that the first character was accessed. The first access was made at 9. The first index was 9, and then it was accessed step by step by the parser. Now, once we have this, then we want to attach the information. We want to extract the information from this and then reconstruct our tree that I talked about. So here is how we extract it. Sorry. Graph is not executable, so that needs to be handled. Sorry about that. Export the path to the graph wizard variable, that is opt homebrew. Restart the Jupyter notebook. And we start mining grammars again. So it takes a little bit of time. Okay, so now we simply start the kernel and execute it fully for now. Okay, so first clear our inputs, and then we start it. So we were at mining the generated traces, and here. So we have our generated tree that actually extracted the complete parse tree from the program while it was running. And this is what I was talking about earlier. So now let us get back to our Keynote. So now the next thing that we need to do, so we have the parse tree, but this parse tree is not fully abstract. These parse trees are actually specific to the particular execution that we just did. That is, we do not know which nodes are comparable, whether a particular digit node can be replaced with another digit node. And this is what we do in generalizing nodes. So we try to figure out which are the conditional nodes, which are the looping nodes, and whether the looping nodes actually require, which iterations of the loop are compatible with each other. Because sometimes one iteration may be compatible only with the odd numbered iterations, because there might be other things with Boolean variables that might be going on within the loop. So with one iteration of the loop may be looking for commas, and in another iteration it may be looking for digits. So we try to generalize the nodes. And how we do that? Essentially look at each of these nodes. So here, if you see, this is our parse expression, the derivation tree that we generated from 9 plus 3 by 4. If you look at the two while nodes, you see that in the first place, the first iteration of the while loop, the digit 9 was parsed, but in the next iteration of the while loop, an operator was parsed. So we cannot actually replace the first while node with the second while node. And this is why we need to actually generalize. And what we do is to compare each of the nodes that are named similarly. And then we try swapping them and check whether the resulting value is actually accepted by the program. If they are accepted, then they are compatible nodes. So we do the same thing with parse expressions. So we generate an expression by swapping one parse expression with the other, and then check whether it is compatible. And if it is, then we mark them as compatible nodes. And in here, we check whether the two while nodes are compatible. That is, we switch between the multiplication operator and the parenthesis. And that results in an input that is not compatible. So that means that these two while nodes are not compatible. So once we have that, we actually have a derivation tree where we actually can extract the grammar from. And this is what we will see in the next. So going back. So we now generalize the nodes. And then from there, we extract the grammar. And here is the grammar that we extracted. So this is not very nice to look at present. But what we do is that we can recursively improve, we can iteratively improve this grammar to generate more and more better grammars. And the nice thing is that once we have this grammar, then that grammar generates inputs that are completely acceptable by the program. Any number of inputs and it will generate. It can generate an infinite number of inputs. So we are here. And the way that we actually generate the grammar is to actually start with the root node and then extract all the first level children of it. And the names of the children becomes the tokens in the rules. And we extract each similar rule and then add the rules. And from there, we abstract the final grammar by looking at which nodes are repeating and others. And here is recovered arithmetic grammar. Actually, I have an example here. So let's see. Yeah, sure. Okay, so I just want to show an example grammar here. So here is the full example. Okay. So it will take a little bit of time. So let me go further into the Keynote. And once we have this grammar, we can generate any number of inputs. And another entire set of extracted grammars are available in my GitHub page. And this contains grammars extracted from JavaScript, from JSON, from C, and any number of programming languages, and CJD code and others. Now, what happens if you find a crash? So before that, let me actually go back here. Somehow my Jupyter notebook is fairly slow today. So I'm going to close off these things. Okay. Since I don't have a lot of time, so let's see what happens if you find a crash. So why did the program crash? And we can use the delta debugging to minimize the failure-inducing input. Okay, but however, this new input is really tiny, but it doesn't actually tell you why the crash happened. For example, would any of these things crash? That is it 5 characters that caused it a crash? Or is it the double parenthesis or the presence of 5? So what exactly is the cause of the crash? So can we do better? And this is what I tackle in abstracting inputs. And in abstracting inputs, so again, so these are a few bugs from real world projects. And each of these are minimized test cases. While they look simple, they aren't actually telling us anything more about what caused the crash. So for example, are the repeating variables important? Are empty objects important? What if you have other declarations? So the question is how exactly we can do that? And the solution that we found is to parse the failure-inducing input and then try to generalize it by repeatedly replacing each node with a set of nodes that are automatically generated. And if all the nodes that are generated that way is accepted by the program and reproduces the hash, then we know that we can actually abstract that input. And that produces an abstract failure-inducing input. And this gives us a specialized grammar. Actually, this is provided. Okay, so before we go there, so that is provided in the abstracting inputs page. And you can see that I actually tried to abstract a failure-inducing input. And I am actually able to produce input. So what I'm trying to abstract is a simple value. If the input contains double parentheses, then fail. And you can see that I am able to. So this is a failure-inducing input. 1 plus double parentheses 2 into 3 by 4. And we can abstract that and finally obtain a grammar that only generates inputs that contain double parentheses. Now, this is interesting, but can we do better? And this is what we do in the final notebook, that is input algebras. So in input algebras, what we do, so in input algebras, what we actually do is to try and combine different failure-causing inputs. So with abstract inputs, we have a grammar that specifically focuses on a particular pattern. It generalizes a particular pattern, and it will only produce inputs that matches a particular pattern. It may be like double parenthesis, or it may be division by 0, or any number of such patterns. And what input algebras does is to actually combine them together. You can say that a particular input contains both division by 0 as well as double parentheses. Or you could also say that this particular input contains double parentheses but does not contain numbers 5 to 9, or any number of such features. So what we have, so here is an example with JSON. So the first one is where we say that our program fails if the key value is null. And then we also want to negate that. And then we add one more condition. One key must be empty. And then we capture these both behaviors, and then we generate a grammar. And these are done automatically. Once we have that, we can generate a grammar that exactly produces whatever we actually wanted. So here I am simply saying that it should contain at least one item where there is an empty key, and it should not contain any null key values. And we can actually pass it to the tools that I produce and generate a grammar which would always generate inputs, and all inputs that actually allow this particular constraint. Okay. This is the final input algebras slide. And run that and see the results. Now, this is the grammar that actually that gets produced, and this is a constrained grammar that produces only inputs that correspond to the particular expression that you started with. So here the expression was it should contain both these D1 and Z1. It should not contain either D1 or Z1. So at the end of this particular talk, I have talked about how we can generate valid inputs for programs without specification, and I have talked about how we can mine input grammars, and I have also shown abstracting the inputs so that you can generate any number of such inputs, and I have also shown how to combine such inputs using an algebra. So that ends my talk, and I am available for any questions.
Thank you very much, Rahul. Great tutorial. Very thorough explanation of how to implement everything, since even the evolutionary algorithm at the beginning. Very interesting. Thank you very much. And we still have a few minutes for questions, so if you all have questions, please put them in the chat or join in and ask them directly. I have a question meanwhile. When I was working with fuzzy in the past, one of the few things that I read about on the literature review is the difficulty in getting past the parser, right? Getting valid inputs. I see that your solution of getting the grammars and then generating those valid inputs make you go past that parsing part. Is that that's obviously an advantage, but is that the only advantage of your solution, or what can you say about these difficulties in fuzzy and how grammars can solve them?
So thank you for the great question. So as you said, getting past the parser is the first step. Once you get past the parser, then you reach the system behavior. Okay. Until you reach the parser, you do not actually reach the system behavior. But once you have gotten past the parser, then you have interesting behaviors that you can actually examine. So for example, for understanding when a division by zero occurs in a calculator expression, you need to actually produce expressions that contain that division by zero. And that requires the extraction of the grammar. But once we have that, then we have the grammar, so we can minimize the input and precisely understand what caused this behavior. So it may be that there is a division by zero, or it may be that there is a floating point exception, or it may be that you have a null value somewhere. And in the third part of my tutorial, in the abstracting inputs, this is what I tackle. So this is what goes beyond just the parser. And once you have, essentially gotten this together, so if you have something that contains multiple faults, how you can actually decompose that and then combine them back together. You can say that you want to produce an input that does not contain a division by zero or does not contain nested parameters, but contains other bugs that you are interested in. So these are the things that I talked about in the last part. Unfortunately, it was a little more rushed, so it is not as detailed as I wanted it to be.
Yeah, no worries. It was a great tutorial, by the way. Thank you for answering the question. I believe you have a question, Sebastiano?
Yeah. I mean, I'm very big fan of, fuzzy, because it can be applied in large scale. If you're going to talk to Google and then you mention about fuzzy, that's probably what they're applying. And I was talking with an engineering about that. I was more on a technical side. So what is the challenges or apply fuzzy in different languages? Did you see, moving from object-oriented to, Python, like it's more sort of scripting language, if you want, difficult, different? What would be the challenge? What are the available solution, or how transferable is your solution? What is your general thought about that when moving from programming languages?
So there is one clarification that I should make here. The techniques that I presented here, and these are all in Python notebooks, and even though I was not able to present it fully, you can still go through them. They are all language agnostic. They can be applied on pretty much any programming language that follows at least structural programming techniques. If the program does not follow structural programming techniques, what you will get is a more degraded version of the grammar, or at whichever portion of the program structural programming techniques like while loops, conditionals, etc. are in there, you might get a little more degraded grammar. But otherwise, what I have found is that we looked at Java, we looked at Python, we looked at C. And in all of these languages, we can apply these techniques. And there is, it is actually language agnostic. Super. And I have also mentioned that in my GitHub repository. This can be applied so long as you are able to actually, at least wrap the input string in a proxy so that you can find where in the program these input accesses occur. And this can be done in pretty much any programming language that is currently out there.
Yeah, I did ask intentionally because I think that's value of what you are proposing. And when I also, there would be some discussion about, and you have seen previously in Paolo Keynote, how to use systematic testing for AI and stability system. So if you move from actually programming languages, and you try to move forward to AI, and astrophysicist, what do you think would be challenging to move there, or there would be any? As I know that is a bit teasing, but I like to link talks to previous people.
Yes, that's a really great question. How would any of these techniques have an application in AI or testing AI? One thing that it might have is at least in generating inputs. For generating inputs, we can actually generate inputs by considering the system as a black box, so long as the system obeys a very minimal, interface. That is, it should tell us when the input is incomplete, or it should tell us when the input. So if you provide a string to the system, it should either tell us that the input was valid, that is, the system can accept the input, or it should tell us it is a valid prefix, that if you attach something more, then it would become a complete string. Or it should say there is no way that the string is a valid prefix. If a system obeys these three constraints, then you can actually use the hill climber to generate inputs. And it doesn't really matter whether it is an AI sitting in the black box. Now, mining grammar is harder. Until now, I haven't seen a good way to mine grammar. However, there are efforts from Caroline Lemieux and others for mining grammars from black box systems. However, I'm not very sure how scalable these are. For once you have source code, of course, things completely change. But black box mining is still an ongoing research. But abstraction of inputs, certainly you can do that.
Would be one way to go.
Yeah, and combining these inputs, these can also be done. Thank you for
the question. Thanks, Rahul.
Thank you, Rahul. Thank you for your wonderful tutorial. Everyone, please congratulate on this amazing tutorial. And I guess now, if you have questions, please put them in the chat. And I think we can go to the paper session, the first paper session. Thank you, everyone. Vincenzo, you're on.
Let's start with the paper session, of course. Of course, I have the issues of sharing the screen. Let's try to fix them. Okay.
For the session starting, you, Vincenzo, leading the first paper session in a moment.
Back.
Yeah.
And I can share my screen here. Can you see it?
Yes.
Okay. Okay, sorry for the inconvenience. It's Vincenzo here, and it's time to leave some space to the authors that submitted the research papers to our competitions. We will have 2 sessions. Each one will host 2 presentations of 2 papers. Paper session 1 starts now until 12, and then we will have a lunch break, and followed by the second session chaired by Gunel Jangirova. We will have 2 formats of paper, long papers that are 50 minutes long. We will have 10 minutes for the talk and 5 minutes for the questions, and short papers for which there are only 5 minutes for the talk. Of course, I encourage you to interact with the authors, and for doing so, you can either write us on the chat asking a question, or you can share your cam and ask directly to the presenter, or you can ask via Twitch, and Giovanni will report us the questions from Twitch. Let's start with the first session. We have two papers. Both of them are applying machine learning for software testing related tasks. One is for test case prioritization, while the other one is for test input generation. The first authors are Safa Omri and Karsten Sins for the Karlsruhe Institute for Technology. I met them 2 years ago at the Deep Test workshop, in which they presented a paper on software defect prediction. It was my first virtual event. Many things have changed, but we are still virtual, not for our choice. And I will play their video, and then you can ask them question by sending a mail to Safa. I will leave the email address of Safa in the chat box.
I also think that Safa is online here, so she can join us for the question and answer after this.
Hello everyone, I am glad today to be part of the SBST workshop. So I am Safa Omri, and thanks a lot for giving me this opportunity today to present our research paper, Learning to Rank for Test Case Prioritization. Software applications evolve rapidly because of continuous functionality extensions, changes in requirements, code optimization, and fixes of faults. Moreover, modern software is often composed of components engineered with different programming languages by different internal or external teams. And during this evolution, while continuously releasing new features. Therefore, many industries use a continuous integration strategy, a common agile technique in which engineers frequently commit their latest code changes to the mainline code base, and developers commonly need to know that unmodified code has not been affected after such code changes, and regression testing is a crucial technique to ensure that these changes do not introduce new bugs at each CI cycle. However, regression testing could consume around 80% of the overall testing budget and require weeks to run all test suites. For example, Amazon is conducting 136,000 builds per day. Google engineers might wait around 45 minutes to 9 hours to receive testing results. In order to reduce the cost of testing, several techniques have been developed, such as test case minimization, selection, and prioritization techniques. The test case minimization aims to eliminate the redundancy in the test suites or remove obsolete test cases to reduce the size and thus the cost. The test case selection aims at identifying the test cases that execute the changed area of the source code, and the test case prioritization is probably used as an optimization mechanism for ranking tests by their likelihood of revealing failures without eliminating any test case from the test suites. However, existing prioritization techniques require gathering code coverage data or performing static analysis, making such techniques time-intensive and cannot be executed within CI cycles, and limited from a practicality point of view as modern software is often written in different programming languages. Moreover, recent test case prioritization approaches shifted to using historical data about failures and successes of test cases based on the hypothesis that test cases having failed in the past are more likely to fail in the future. Unfortunately, such techniques are based on machine learning techniques which do not allow incremental learning but regularly construct new models from scratch, making them time-consuming, leading to potentially outdated models and not well adapted to changes in the execution environment. In order to address these challenges, we propose a new test case prioritization approach in CI. We formulate the test case prioritization problem as an online learn-to-rank model using reinforcement learning techniques, and the following problem formulation for test case prioritization is based on basic learning to rank results from the field of information retrieval and applies reinforcement learning to make the ranking approach adaptive and suitable for our CI context. The figure shows the CI cycle. A developer commits code changes that trigger a CI cycle. The test case planning system generates a prioritized test suite, and a subset of the test cases is executed in the specified order until a timeout is reached. It is usually not possible to execute all available test cases within a CI cycle. And when executing the test cases, some will fail and some will not. We investigated two research questions. How efficiently can our approach perform priority-based test selection? And second, how effectively can our approach perform test prioritization? The experiment was conducted on 11 projects. The first 10 projects are open source and all data are publicly available, and the last project is an industrial project. For the first research question, how efficiently can our approach perform priority-based test selection? Our approach learns priority ranks for all test cases, and when applied in the CI context, it might terminate before all test cases are executed. So this behavior is similar to the behavior of test selection techniques, and we use the following standard commonly used metrics in software test selection to assess the effectiveness of our approach when not all test cases are executed. We use the metric test recall. It's intuitively, the test recall approximates the empirical probability of a particular test selection strategy catching an individual failure. We compare our approach against three test case prioritization methods. The L-bounds approach, we were able to re-implement the approach since a detailed algorithm is available. With RETEX, the first online learning approach to the best of our knowledge using reinforcement learning in the context of test prioritization and selection in continuous integration. And we use random test case prioritization as a baseline method. It shows that 95% of the test failures are still reported back to the software engineers, while only 40% of the total available test cases being executed, compared to at least 67% of the total available test cases using RETEX. To answer the second research question, how effectively can our approach perform test prioritization, we use the commonly used indicators to measure the effectiveness of test case prioritization techniques. The average percentage of faults detected, the APFD, and the normalized average percentage of faults detected, the NAPFD. The APFD measures the quality by ranking the fault detecting test cases in the order of test execution, and the NAPFD is an extension of APFD to include the ratio of detected to detectable faults within the test suite and is therefore suitable for test case selection where not all test cases are executed and faults may remain undetected. Our approach outperforms almost all studied approaches. We highlighted the best values in bold. Among all the studied projects, the random method has the worst performance. The IOF, Rahul, Druid, and SetSync approaches had the worst performance. To understand this behavior, we analyze the failure detected over the cycles. In those systems, we verify peaks in the failure detection in a few comments and long periods without failures. Moreover, Jude projects had the lowest number of TI cycles among the systems evaluated, and the SetSync had the lowest number of failure reported. In conclusion, we developed a novel lightweight method for test case prioritization in CI based on foundational results of learning to rank from the field of information retrieval using reinforcement learning techniques. Our approach is adaptive and learns ranks from the available test cases during its runtime by observing test results and its own actions and their effects. Our experimental evaluation results show fast learning and adaptation of our approach on 4 industrial case studies. Our method is language agnostic and does not require access to source code, and hence can be integrated as an extension or plug-in for existing CI environments like Circle CI/CD, GitHub CI/CD, GitHub Actions, etc. As future work, we plan to add additional metadata to our approach with the hope to enhance its overall performance. Further work should also consider coverage metrics of test cases during the early stage of development when little failure historical data is available. This could allow improving the effectiveness of our approach. In a CI environment, the actual tasks still be solved in each cycle are often similar to previous cycles. Thus, future work on reusing the previous CI cycle results should allow for potential speed ups in future cycles, and furthermore, adding information from the execution environments to the reinforcement learning environment can enhance the quality of the test ranks. This brings me to the end of my presentation. Thanks a lot for your attention.
Congratulations to Safa. We just knew that she's having technical issues to activate microphone and camera. If she can write on chat and answer questions. Safa, are you there? Okay, I guess I can safely go on with the next presentation. It's next presentation is from Jaakko Peltomäki, Frankie Spencer, and Ivan Porres from Obo Academy in Finland. And this time they're applying machine learning and specifically generative adversarial networks for a test input generation and to test the cyber physical systems. So this time the presentation will be live. And I asked them to open their mic and their camera, and let's enjoy their presentation.
Be recorded.
Okay, do you want me to play the recorded version?
Well, please, if you can do it quickly, it would be more convenient because I wasn't really prepared to do it on the
Perfect,
spot.
I'm on it.
Okay,
we're waiting for
thanks.
you for the questions.
Yeah, sure.
Okay, let's start with the presentation then.
Hello, everyone. I'm Jaakko Peltomäki. I'm from Åbo Academy University. And what I'd like to tell you is about how to use generative adversarial networks for test generation. This is a joint work with Frankie Spencer and Ivan Porres, also from Åbo Academy University. So the aim of this talk is to tell you how to generate test suites with generative adversarial networks, that is GANs, in an online fashion. And just a few words about the assumptions. So we assume that the system under test, it's some sort of a deterministic black box mapping from an input space to an output space. So we output vectors. And as is common, especially with cyber-physical systems, we have some requirements for our SUT. And here we assume that they are given as a fitness function f, taking values between 0 and 1, with the property that the test from the input space I is falsified if and only if its fitness equals 1. So high fitness tests are the same as challenging tests here. Moreover, we assume that evaluating these SUTs is expensive. So then a few words about GANs. So I don't really have the time to explain them in detail, but here are some broad ideas. So consider the input space and some probability distribution P on it. And a generator, say G, it's a mapping from an auxiliary space I prime to this input space with the property that it transforms some distribution on I prime, say the uniform distribution, to this target distribution P on the input space, which we would like to sample from. And said in other words, if we want to sample according to this distribution P, we would do the following. So instead we sample uniformly on this auxiliary space I prime, and then we map those samples via this map G, and then we get samples on I that are actually distributed according to this P. That's the purpose of a generator. And here we are all the time talking about Wasserstein generative adversarial networks, but it's just a way to train this G based on a large data sample from P. There are other ways, but in this paper, we focus on these ones. And how to then use this for testing? Well, consider this set. This is the set of challenging tests for our SUT. So what we would like to have is a generator for this set. So like if we had such a thing, we could sample uniformly on this one, then we are basically done. We can find the test suite simply by using this generator. So we would like to have something like this. The problem here is that, okay, how do we train the generator? Cannot really do it in a traditional way because it needs a large data sample from the input space according to this target distribution, and we don't have it. So what instead we need to do is train this Wasserstein GAN in some online fashion. And this paper is basically our proposal, how would you could do it. And let me first explain some broad ideas how this is done. So first we obtain some random sample of tests. Then we train a Wasserstein GAN with these tests. We can do it now that we have data. We don't use all of the data necessarily. We just use high fitness tests from the random sample, whatever high fitness means. And then our aim is really to make this test suite larger. So we would like to add test suite. So how do we find new tests? Well, we have a generator now that we trained it, so we can use it. So we sample the generator and select the good test, whatever that means. And then we just add this to our test suite and proceed as long as we're not satisfied, or as long as we have budget. So this is the big idea. Use the generator to propose new tests. Of course, this what I just described is vague. Like what does it mean that we include high fitness tests? And about that, I don't have the time to talk really. So you have to look at the paper. But another issue is that what does the good mean here on this line? And I'm going to tell you something about that, just to give you some ideas. So like, what does it mean that a candidate test generated by this generator is good? We just don't want to select arbitrary stuff. It could just, I mean, we somehow need to drive this G into learning this set of, or the distribution on high fitness tests. So not everything is good here. And how we do it, what do we mean by best or a good test, is the following. So we train an analyzer. So it's an auxiliary machine learning model, could be a neural network. That's what we use. And what we really just do is that we algorithm again with some additional details. So first we sample some random test suite of n samples. And while we still have budget left, we do the following. So we first train this generator on high fitness tests from this test suite, whatever this high fitness means. Then we train the analyzer on this data we have so far. And then we start to sample this generator for tests. And we basically sample a batch of tests, and then we can estimate how good they are using this A. And now this step, we get some information how good the tests are, but we don't have to do any executions on the SUT. So this is a crucial point. Then, okay, we selected the test with the best estimated fitness, obviously. And then we execute this selected test on the SUT to learn its actual fitness. And then we add this best test to our test suite, and we keep going until we're satisfied. And an important point here is that is this line, So we really need to execute this test we selected on the SUT to learn its true fitness, because otherwise this training data we use for this analyzer could be garbage and it might be unreliable. So that's also very important. Well, we don't get stuff for free. That's the point. And yeah, the other issue is that what high level, or not high level, but what does a high fitness test mean, and how do we train the generator using it? And I don't really have a time to tell you how this is done. It's briefly that we make a training batch and we sample tests from the test suite to it randomly, but not uniformly. It's just in a way that high fitness tests have higher chance of being included. But yeah, you need to look at the paper for that, or ask me some questions later. And the intuition here is that over time, this analyzer should get more accurate in predicting the fitness. And this should mean that more high fitness tests get included in this training batch. And hence, as G is trained on high fitness tests, it should be able to produce samples from this set of challenging tests. I guess that's fairly obvious what we're after here. And I'll skip that. And yeah, of course, that's just an idea, and we cannot really prove things. But for this, we we devised some experiments. I don't have the time to explain them here, so you need to look at the paper again for this. But well, let's just say that we have one experiment which indicates that we can achieve state-of-the-art performance with our ideas, meaning that in a way these ideas what we have are workable ones. So that's briefly it. So thank you for listening. I'm out.
Congratulations, Jaco, for your presentation. We will hear about their tool also later during the tool competition session, because they also participated to the tool competition. They were quite active. We enjoyed their participation because they gave us a lot of feedback, and it's very constructive. And I cannot see questions right now in the chat. I invite you to do so, but I have many questions on my own. And the first one is about the generative adversarial networks. They are very popular right now for test input generation and to test deep learning systems. One thing that you showed is how to train it, but suppose that you have the same domain like we had in the two competition with two different agents. Should you train your generator 2 times or multiple times for different agents to test?
Yeah, that's a very good question, and actually something we are looking into. So I don't know, like so far we've done it, separately for if there is a need. But I guess that it's like very reasonable to do some sort of transfer learning, that you're in the same domain, you already have one model, you somehow want to transfer it to the other one. I don't know, like for starters, you could use the same weights when you have a neural network for your next one. Maybe it's a good starting point, or maybe you could do something smarter. But really, this is in the open, so I don't know.
I think it's a smart solution yours to use the initial weights of a similar agent and then fine tune it on another. Let's see if it works. I'm interested in that. So
yeah.
Good luck for that. I have also one question from Alessio. You can see it in the chat. I can read it for everyone. He's asking that if, in your experience, how long did it take to train for the GAN to produce noticeable improvement?
Yeah, so we really did this on only this SBST tool competition, and for that one, the most of the time is taken by this simulator. So it really is a short time which is used for the training of these machine learning models. But let's say that we have some budget. So I think what we saw is like maybe after 2/3 of the budget's been exhausted, the generator starts to, maybe we use like 1/3 for random search. Then there is 1/3 where nothing really happens. It's trying to figure out what it's seen, and then we are seeing something. But really, we just did this in this one domain, and so something like that. So I cannot really comment what happens generally. Yeah.
That's great. I have one last question out of many. Is your approach applicable to other domains other than cyber-physical systems, like image classification or text recognition or speech recognition?
So if we think about testing, so whenever we have I mean really, when you want to test any black box function which is deterministic, you always get the same outputs for the same inputs, then you can use our system. So it doesn't have to be cyber physical system. We're just trying to sell it as a cyber physical system thing. But I mean, even if you had some math function, whatever you want to optimize or find inputs for it, this this is usable as a optimization method. Yes.
Okay, it seems that there are a lot of future works ahead. Good luck with that.
Yeah, sure.
And congratulations for your presentation and your paper. See you later for the two competitions, of course. And
thank you, and see you later.
Thank you. Okay, right now we can end the first session. We have a lunch break until 1:30. I can leave the I can leave to Giovanni the closing words. Sebastiano.
Okay, I think they will.
Thank you everyone for taking part in this first part of our workshop. Thanks for the presenters, Safa and Jarko. Great work. We're going to come back at, let me see, 1:30.
1.
Yeah. And so you can have your lunch break, or if you're in the US, a nap. And yeah, see you later. And for the next presenters, for the next paper session, you can use this time to test your video and audio. And yeah, that's it. Thank you, everyone.
Okay, I think we can start. It's time. So, hello everyone, it's Tonela. So the lunch break is over. I hope you had a good time during the lunch break and came back recharged. So we're going to have our second paper session where we'll have 2 more papers presented. And the first one will be presented by Sebastian, where he will be talking about the studies they have done where they've compared the quality of manual and automatic tests. So the stage is yours, Sebastian. And as per usual, if anyone has questions, please put them in the chat during the talk.
Yes, thank you very much. And welcome, everybody. I hope you had a nice lunch break. I am very much honored to be able to present to you today our case study in the Python project for material science workflows entitled A Comparative Evaluation on the Quality of Manual and Automatic Test Case Generation Techniques for Scientific Software. Now, I assume that most of us here today are software engineers, so let me start with a very, very brief introduction into computational material science. Now, assume for 1 second that you are a computational material scientist and you have a brilliant idea on a new and very exciting new material. So how would you go about analyzing that material? Now, you could obviously go to the wet lab and synthesize the material and then prod it and poke it and measure all of the material all of the material's properties. Now, this takes a lot of time and a lot of money. So this is where computational comes in. You still have the same idea, but instead of actually synthesizing, what you do is you go to a computer of some kind and input your geometry and the material makeup into that machine. You then go to a HPC cluster where you then simulate in different depths these properties of the materials. After some time, this may be some days or even weeks, the simulation called the density functional theory simulation will have outputted a result that you then analyze and check if everything worked. Maybe you find that the geometry didn't work. Maybe you find that the material in it of itself didn't work. And after a couple of these loops, you might have found an actually exciting new material. So how do these simulations look? How do they work? In a nutshell, basically you have a human in the loop workflow that is highly resource intensive. And since it's basically written by mostly physicists, you will have to deal with a monolithic archetype. it is monolithic because most of the people that are developing these DFT codes are actually physicists. They are not software engineers by training. And you will have to deal with a lot of numerical approximations. Now, when we are dealing with numerical approximations, only this one workflow is just half the story. Not even half. There is maybe like 45 different of these DFT codes in existence right now, all simulating slightly different things. Maybe one of them simulates the full electrons of an atom, or maybe another just looks at the outside electrons. So all of these different codes that we see in the middle, so every single one of these looks like this. All of these codes here in the middle, they have a proprietary input and output format. So as a computer scientist, we obviously want to work with all the data that is available to us, and we have to unify all of these input and output formats. So this is where we come to our software under test, which is called Atomic Simulation Environment, or ASE. The ASE, and a big acknowledgement to Daniel Speckhardt from the Fritz Haber Institute, without whom this work would not have been possible. He's a dev on this particular computational material science workflow. Without this, we couldn't actually analyze much of the data because of this proprietariness of the in and output files. What can we do with the atomic simulation environment? Well, we can do basically every single thing that I talked about in the very beginning. We can build and manipulate these atomic systems, i.e. the geometry, the structure, the compound. We can generate the input files for these different DFT codes. We can then call the executables, and we can collect the results from those output files. So what did we actually look at? We looked at the following question: how do the automatically generated test suites of the test case generation algorithms compare against each other, as well as against a manually created test suite? So we've done a couple of experiments, the results of which I will introduce to you now. Don't be alarmed. On the next slide, there is going to be a kind of big table. We will go through it slowly and step by step. Let us start at the very left. What did we actually look at? We looked at the branch coverage of the initial program, the baseline program, and the test suite that came with it. As we can see, we reached with the baseline program only a branch coverage of 25%, which is really quite low. If we then look at the mutation coverage to understand how sensitive is this original baseline test suite, we see a picture that is even more dire. It's only 3%. So only 3% of all mutants were managed to be killed through this baseline test suite. We generated a session of 8 hours with the through our first author, Daniel Trübenbach, a manual test suite. That manual test suite managed within 31 test cases to actually cover the entirety of the program, 100%. And if we look at the mutation coverage, we also see a rather high value here of 90.5%. For the 4 remaining approaches, we will look at the data in a more visual way. Let me just quickly say that we used the Penguin tool for test case generation in Python. I see that the developer of which, Stefan, is also in the audience today. We ran all of these approaches for 600 seconds and 30 different times. to account for randomness. So let us look at the actual data in a more visual way. Let's first look at branch coverage. So we see the behavior that we would expect, the more modern and more state-of-the-art approaches such as Dynamosa at the very top of our results list here, and the FD random, which is kind of similar to the Java rendupe approach, only for Python programs, reaches a lot lower than the state-of-the-art approaches. But let's take a look here where the axis actually ends at somewhere just over 60% for the absolute maximum. This is, while an improvement on the original test data, this is not really all that great. And if we look at the mutation coverage, the picture again becomes more dire. And there is one outlier that we ourselves are not really able to explain. We see that the whole suite approach really only gets a rather unsensitive test suite. We have talked to Stefan before, and we are still in the process of understanding what happened here exactly. Since my time is almost over, let me quickly come to the conclusions and observations. The workshop that we are all part of here, we are looking at how to improve things so that they might be actually used in the real world by real developers. And in our case, this would be the computational material scientists. So what did we find? Well, first of all, and this is the positive note, we did actually see an improvement over all of the baseline test cases, but we were unfortunately significantly worse than manual test suite. We encountered 3 different pitfalls, 2 of which are actual pitfalls. The other one is a general problem. Firstly, as soon as we have complex and structured input data, our current automated test case algorithms, they really struggle. Pitfall number 2, the dynamic typing in Python can potentially interfere with our generation power. Now, if we have something like Java where we are statically typed, we can infer from the types something for our test cases, for test case generation, namely which type should we actually use here. And lastly, we had a problem explaining the generated test cases to our domain scientists. This was due to the fact that methods and variables were just numbered all the way through. I know that Stefan has been working on this already, and we are looking forward to seeing the results of the improvements that Stefan did in this regard. I hope that this talk might have provided a bit of an input into the 3 main areas where we see problems. And with that, I hope I can spark a discussion either here or in the actual conference in Pittsburgh. And I am happy to take any questions that you might have. Thank you very much. Okay, I see that Stefan has a question.
So
unless you have.
No, go ahead.
Okay, the Python code, it has some type hints. The physicists are quite good in demarking what types they actually want to use. However, this is only true for this particular use case. So we did see some improvement in some methods that were actually marked with, okay, you should expect a bool or something. We did actually see an improvement. Where we did not see much happening was in a second study that we did after this. So we experimented also with a second material science program called Elastic 2.0, where the devs actually did not do that. This is preliminary data, so it's not fully evaluated yet, but it did seem like the actual test case generation algorithms did struggle somewhat. Of course, Stefan, if you want to, we can talk about this in the future in a more personal session. I'm looking very much forward to do that. Any other questions?
I do have a question. So as we're comparing manual testing to the automated one, I would like to ask, like, what is the effort that was required to do the manual testing? What is the level of knowledge you should have about the system under test? And if you sort of normalize by that effort, do you think that the automated test generation approaches are still useful?
Okay, so our first author, Daniel Trübenbach, he spent almost exactly 8 hours to generate that test suite that covered all of the branches. He did not have any prior knowledge in these particular kinds of workflows. He was literally thrown into this topic by me and by Daniel Speckhardt, the dev of ASE. We were just trying to see how fast could he do this or create this test suite, and it was basically 8 hours for the full coverage. I think this answered the first half. There was a second half of your question. Can you repeat it again?
Of course. So I was asking whether if you think we normalized by this effort, like 8 hours versus 600 seconds, do you think that the automatically generated ones are still useful?
Yeah, that's also a very good question. Now, I personally see automated test case generation. We can basically throw as much time at it as we want. It's literally only us torturing electrons at this point. So we're totally fine in scaling this up. Why did we stop after 600 seconds? Because we didn't see much improvement at all.
Okay.
Yes, of course, we could scale this up, but as always in search-based software engineering, we could just be reaching a local optimum or a plateau of some kind. And who says that if we let it run even a second longer, that we wouldn't find the next jump? So this is obviously a trade-off.
Okay, so our time is over, so I think we should stop here. Thanks again, Sebastian.
Thank you.
So our next paper is by, okay, it's Towards Runtime Search for Real-World Multi-Agent Systems by Abigail Diller and Eric Fredericks. So I think I saw the authors in the chat, so if they could share the screen and start, that would be great.
Hello, can everybody hear me okay? Okay. All right.
Yeah, I'm not seeing the presentation. I don't hear the speaker.
Yeah, let me share my screen. Okay. So can everybody hear me and see my slides?
Yes.
Okay. Hello, everybody. It's a pleasure to be here today. My name is Abigail, and together with my co-author, Dr. Fredericks, we are here to present our early stage research on runtime search for real-world multi-agent systems. Let's get that out of the way. So a multi-agent system is comprised of multiple interacting intelligent agents. An intelligent agent operates autonomously to achieve an independent goal. A multi-agent system can face uncertainty at runtime, for example, in the form of unexpected environmental conditions or unplanned agent interactions. The number of combinations of such uncertainties may be difficult to enumerate, and as such, runtime testing may provide assurance that the system continues to exhibit expected behaviors even when faced with uncertainty. However, testing a multi-agent system can be a challenge as different agents may require different testing approaches. For that reason, we are investigating the use of search heuristics to augment the runtime testing process. We chose to investigate search-based software testing strategies as an adaptable testing strategy may help to mitigate the high level of uncertainty that the system may face. And search-based testing may account for the unique characteristics of individual agents. We were particularly interested in testing in situ in order to acquire real-world data and to identify potential challenges with our approach. To accomplish this, we constructed this experimental test bed, which we have modeled as a multi-agent system. We have one agent, an Arduino, acting as tasked with monitoring ambient environmental conditions to ensure that they're in a comfortable range. We have another agent, a Raspberry Pi, which continuously generates test data and monitors the power consumption of the system as a whole. So for our procedure, the Raspberry Pi acts as the testing agent and the Arduino serves as the agent under test. And I will now outline our procedure for performing search-based testing at runtime. So to begin, the testing agent configures the search. We are currently targeting a genetic algorithm for our search heuristic. So the testing agent will generate sets of test data. Then the testing agent will transmit the test data to the agents under test. After parsing the test data, each agent under test will execute a series of test cases and transmit the results back to the testing agent. And then finally, the testing agent will process the test results, incorporate them into the fitness function, and execute the subsequent generation of the search. So down on the left, we have the fitness function, which aims to maximize test case failures and maximize the novelty of disparate test cases. And then we have a sample test case, which checks to see if a recorded temperature value is within the operational parameters of the temperature sensor. So here, an example of a test case failure would be a recorded temperature value of negative 350 degrees Celsius, as this is far outside the operational parameters of the sensor and outside of the conditions that the system is expected to encounter. To better explore our procedure, we have several testbed extensions in progress. Here we have a Raspberry Pi Zero, which will serve as the testing agent for future experiments. And then to enable deeper study, To enable deeper studies into power monitoring, we are incorporating a solar panel, which will be piloted by several servo motors, and we are adding an additional current sensor to monitor the solar panel output. Using the testbed extensions, we plan to significantly extend our body of test cases. We currently have 20 test cases implemented, leading to a very small search space. So we are hoping with a larger search space, we can yield more meaningful results from the search. We also plan to incorporate power monitoring metrics and timing constraints into the search to better emulate a production-ready system. And finally, we plan to conduct a full empirical evaluation in order to analyze our results. I would like to thank Grand Valley State University and the Michigan Space Grant Consortium for supporting our work. And thank you for your time today. I would like to open it up for discussion and answer any questions that you may have. Yeah. hmm So far, we haven't encountered any major challenges. Figuring out how the agents are going to communicate going forward, I think, will be a little bit of a challenge, as right now the two communicate via serial, like a USB cable, and introducing additional agents. There's a limited amount of ports on the Raspberry Pi, so developing that communication could be difficult, or trying to establish wireless communication may present a challenge.
Okay, thank you very much.
Yeah, thank you.
I will have maybe another question if there is no one else at the moment. Take advantage of that. I really like your talk and a lot intersection between testing and actually usage of physical hardware, as Giovanni said. There's a common problem that I think I have seen when talking with industry, having a similar setting that you had, not the same, of course. You had sensor data coming from outside the world, temperature, can be weather condition in a general sense. The problem that I have is that when you have multiple sensors, how do you find noisy sensors or defective sensors among a general load of information? Do you think it's something that you could look for in the future, like multiple testing on multiple system or deviation from the actual information I get from the environment?
I'm sorry, could you rephrase the question, please?
No, let's say you sort of analyze information coming from one sensor. Imagine you have multiple sensors. That's a scenario you have. Yeah, one sensor is selling something different to the others. So that could be one sensor not behaving as expected. They could be just noisy, or others could be noisy. So how you will, in this context, you will change or move forward on the research you have done?
I'm sorry, asking how we'll incorporate multiple sensors?
Testing of test generation with multiple sensors. I don't know if this something you're moving forward. Anyway.
Sorry.
I don't know how to simplify it.
We have one more question in the chat. Maybe we can go on with that. So Alessio is asking whether the test cases are repeatable, or did you observe any flakiness in the generated tests?
Sorry, one more time. I think I'm having a few audio problems.
Okay, so the question is also in the chat. I will read it again, of course. So Alessio is asking whether the test cases are repeatable, or did you observe any flakiness in the generated test cases, so that if you rerun them, you get a different outcome?
Sorry, I'm trying to see the chat. Sorry, I'm having a hard time hearing, and I'm sorry, for some reason I can't see the question in the chat. So far. So we have the same set of test cases that we're using, and running different evolutions of the search. We were getting it's generating different test values. So for example, the test cases that are checking the temperature value, we would be getting different values that are being fed into it each time, but the search would converge very quickly, usually at the same generation each time, usually within, I want to say maybe like 8 or 9 generations. So realized very quickly that the generated values that were just sort of coming to a point where it might be different values, but the search was converging around the same point every time. Does that answer your question?
I guess so. Thank you very much.
Thank you.
So I think can move on to the next question now. Thanks a lot, Abigail.
Thanks a lot.
Yeah, thank you very much.
Thanks a lot.
Okay, thank you. All right. Oh, Eric just said multiple sensors are on our horizon for future work. There you go. Sounds good.
Okay. Yeah, no, but it was both related to the question from Alessio and this one. But I guess that would be the future. Yeah, at least I believe that.
Mm-hmm. Okay, so let's give it 2 minutes before we start the discussion panel. In the meantime, if you're a panelist, could you please test your video and audio? Hello, anybody? Hello, Mara. Hello, Andres. Hello, Paolo.
Hi, good afternoon, everyone.
Hello, everyone.
Hello, Mark. Hello, Marcel. Hello, Lionel.
Hi.
Am I audible?
Yes,
Yeah.
you are.
Hello.
Hello. I think everyone is here. Great. Perfect. Okay, so let me share my screen for now. Just 1 second. Share. There we go. Welcome everyone to our discussion panel at SBST 2022. This discussion panel is called SBST versus fuzzing, intersections and differences. As the name says, we are here to discuss the main differences between testing using evolutionary algorithms and testing using fuzzing. There are many differences, many intersections, and we're all here to unveil those. Thanks all the panelists for being here. I know that for some people the timing is not really ideal. It's morning, very early in the morning, and well, thank you for your effort being here. I'm sure this is going to be a great discussion panel. We don't have exactly like a strict panel topics that we're going to talk about. We have some topics where we're going to talk about, but the idea is that this is a discussion panel. You as panelists, you are going to drive it towards the discussions you want to have. First of all, Sebastiano, do you have something to say?
No. I will just invite each panelist to present themselves in the context of fuzzing or search base or both, what they have contributed, and then we go ahead with the conversation. That would be probably the best way to warm up the air.
Perfect.
In here.
Yeah. So, shall we start in alphabetical order? And could you please present yourself and your work on SBST and or fuzzing, please?
Alphabetical according to first name or last name?
I guess maybe we'll go in the same order as in the slides. So Andrea, Nibal, and then the rest. Whoever is the best. Maybe.
Sorry, I didn't get you. Do you want me to start? Okay, yeah. Okay, I'm getting some echo here. I hope that works. Okay, so I'm Andreas Zeller. I'm a software engineering / security researcher at the CISPA Helmholtz Institute of Information Security. We are hiring at all levels. If you're interested in having positions for PhDs, postdocs, faculty, especially at this intersection at software testing and security, please let me know. I have written a mostly coordinated and written a text, the fuzzing book, in which I put together all techniques of fuzzing. And this also includes search-based software testing, which already gives you an idea of how I position the two. It's thinking of fuzzing as a rather vague term that encompasses everything that is related to test generation. And search-based software testing is a very successful, yet slightly narrow technique under this big umbrella of what we consider fuzzing and test generation.
Hello, everyone. Oh, there's a bit of echo as well. Okay. Annibale Panichella, assistant professor at Delft University of Technology. I do believe I'm probably the only one here that needs to introduce myself, as everyone is way more famous as a researcher worldwide. So I'm the mouse among the giants, but I'm very humbly happy to join the panel. I'm actually mostly working on search-based software testing, but I had some work that combined search-based part with grammar-based fuzzing. And well, compared to what Andreas Zeller, I have a slightly different view of what is what. I think I actually have the opposite view, where search-based is broader, and depending if you not we go for random search, then it's more toward fuzzings. But we can discuss a little bit later on this aspect. And that's it from my side, and I'll give the floor for the next panelist.
Oh, thank you very much.
I believe
this
is me. I'm not sure, but well, I've been working in many and varied different areas of testing. I'm not going to recap that. Various aspects of test automation and empirical studies. And I didn't know it at the time, but I've been doing, first testing for a long time. But I rarely used the term. And I should start using it. Actually, it was a bit silly on my part. I believe I agree with Andreas, his definition of fuzz testing. However, in practice, I'm not sure that's how it is being used by first testing papers, though I agree with what he says. I think that creates issues and divisions among research activities and research communities that are not really justified. Thank you.
Right, thank you very much. Next one is Marcel, please.
Yes, hello, my name is Marcel Böhmer. I'm a faculty member at the Max Planck Institute for Security and Privacy in Bochum in Germany. And I work in fuzzing. So I work, my group develops techniques. We develop techniques that try to find a lot of bugs and try to find these bugs faster. And try to find these bugs on a lot of machines. So this was effectiveness, efficiency, and scalability. But I'm also looking into some kind of theory that may be explaining phenomena we see in fuzzing. For instance, I'm interested in fundamental limitations. A recent paper that I published was establishing that the cost of vulnerability discovery using fuzzing is exponential. I've also looked at efficiency, like when you have a white box fuzzer and a gray box fuzzer or black box fuzzer. And when you have a white box fuzzer that is really effective and can in principle prove the absence of errors, versus a technique that simply randomly generates inputs, how do they perform against each other, and therefore explain why we see a lot of black box fuzzers and gray box fuzzers these days in industry rather than white box fuzzers. So my position on SBST versus fuzzing is that both solve the same problem. They're only different communities. I've been fortunate enough to organize a meeting at Shonan where we invited a lot of people from both communities, SBST and fuzzing, and also the symbolic execution community. and found that there is a lot of different vocabulary. I think that will be Lionel's position as well. We are investigating similar topics, but in different communities. So SBST is a lot about search and a lot about exploring different optimization techniques and applying them to the testing problem. But the fuzzing community is trying to look at performance and particularly for different program language. The SBST is often Java, we often C. And so I think we are solving the same problem, but we are different communities and we have to go together.
Next one is Mark, please.
Hello, everyone. I'm Mark Harmon, and I worked on search-based software testing initially, and then formed a startup called Magica to try and commercialize it. And we were acquired by Facebook and set about deploying the Sapiens technology there. And the thing that struck me was that almost everybody in industry, both within the company and in other companies with which we worked, all referred to Sapiens as a fuzzer. And it intrigued me and got me interested in learning about fuzzing. And so I think if I summarize correctly my position, it would be as follows. So I think Andrea Sella says SBST is a subset of fuzzing, and Annie Belay says fuzzing is a subset of SBST. And Lionel says, you know, we spend a lot of time discussing all this nomenclature. I think he said this on this rather excellent platform for social media interaction that you may have read yesterday. So I actually agree with all three of them. And so any student of set theory will understand my position.
All right, thank you. Next one is Myra, please.
So I'm Myra Cohn, and Mark's put me in a very difficult position now. But I've been working primarily in the search-based software testing community for years, and I've worked with not just unit testing, but more at the system level, configurability, GUI testing. And I'm actually more on the opposite of Andreas, and I actually think that fuzzing is probably more of a subset of SBST. I think SBST in some ways is more general, expansive, and I think fuzzing has a more specific use case. But I do also think that there's a lot of overlap, so I'm really looking forward to today.
Brilliant, thank you. Next one is Paolo, please.
Yeah, so my name is Paolo Tonela. I'm at University of Svizzera Italiana in Lugano. And actually, I think there's a big overlap. I have been working on search-based software testing for a long time. And if I compare to fuzzing, it's a little bit difficult to find the differences, what's in the complement, in the difference between the two techniques, because one could say maybe search-based is often biological inspired, which I mean is not necessarily false of fuzzing. Search-based is optimization, but that's also something that fuzzing does. It's optimizing some reward, some feedback. One might say fuzzing is more random, but then they introduced guidance which makes it no more random. So I guess the overlap is probably more than the complement, the two complements. Still, it's true, communities are different. You read a fuzzing paper and you don't see any citation to search-based techniques and vice versa, which is sort of a pity.
All right, thank you very much, everyone, for the introduction. I already see lots of topics of discussion here, just from the introductions. And do you have anything to add, any one of you, so far? Okay. All right, so I guess we can start by maybe discussing the main differences, as Paolo already mentioned one. It's mainly biological inspired for SBST, and fuzzing, although started a little bit differently and randomly, still being guided now by evolutionary algorithms. So what do you personally think are the main differences that differentiate those two techniques?
So maybe to make it easier, when you use one or the other, maybe they will make easy to position. That will be simplified, probably, yes. The answer.
Yeah, but it's difficult to answer that question because many fuzzing questions at different steps in the fuzzing process actually use meta-heuristic search. I mean, for example, genetic algorithms are used to for the process of seed retention, seeds being individuals or chromosomes in GA. And you even have technique like particle swarm optimization that is used for mutation selection. So it's very difficult to compare those two things as if they were disjoint, because a lot of fuzzing techniques make use of meta-heuristic search at some step or another. I mean, this is a problem. In fact, the problem is in the question of the panel. Since fuzzing is so general, it's basically any randomized technique for test case generation, including SBST techniques. Then how do we compare? I mean, how can the comparison make any sense? It's very difficult. I don't think the question is even makes sense. I think there is just a huge confusion coming from the fact that the two stem from two different communities, use different vocabulary, while at the same time trying to achieve the same objectives. So that's complicated.
Yeah, indeed, this question was made intentional because the next was how to standardize what would be the right way to name fuzzy and search-based and according to what you have said. So actually it was intentional.
I think Andreas has something to add.
Yes. First of all, I'd like to. I'm getting some echo here. Myra, could you turn off your microphone? Great. Thank you. Thank you very much. No, I'm still getting an echo. Okay, good. Okay. First, I'd like to say that the term fuzzing that was coined by Bart Miller late tonight. Bart Miller is a compiler person or a programming person, and therefore I would say the term fuzzing was coined by our community in the large. So it wasn't the security community that invented it. It's just the security community in the last 10 years happily adopted it because it's so effective in finding bugs. Yet there is a difference in communities of software engineering and security. You see, in security, you find bugs, and the way you find them people don't care about how they find bugs, as long as they find bugs. Well, as long as they find vulnerabilities, not any bugs. Crashes, hangs, vulnerability. And this spirit of anything goes, as long as I find bugs, okay? If I can do anything as dirty or as unsystematic as can be, as long as I find bugs in the very end, it's. And this has led to a huge explosion in creativity, which is fun. And people do anything to find bugs. That's the currency by which they are valued in the community. And if we think about search-based software testing as a technique that is based on evolution and guidance, we have, say, for instance, grammar-based fuzzing. You have a model, you have a language, you create inputs. Very effective, but you can do so without any guidance from the program. You can do so in a black box setting. Finds vulnerabilities, great. It's closer to model-based testing than to definitely. And well, we can also discuss about the relationship between model-based testing and search-based software testing, but you see that anything goes in there. Think about symbolic testing, path constraints. Back from the program, which constraints to solve. This can be a search process. This can be randomized, but it doesn't have to. You can also just throw your path conditions into a constraint solver, find a solution, and be done with it. Well, very simplified approach here. But people who do, but if all you want is to find as many bugs as possible, you don't care about such methodological decisions. Just do whatever works for you. And if things work, you get a paper out. And if they don't, if they are just nice and elegant and systematic whatsoever, you do not get a paper out of it, at least not in the security community, maybe in the software engineering community. But for me, the difference between fuzzing on one side and test generation on the other side is merely a naming of different communities, and maybe even more important, whether you test your own program, which you have knowledge and you can exercise some amount of control, which is a software engineering setting, and then typically people call it test generation, or whether you test someone else's program. That's actually the thing that's secure, that is the security we need to introduce. Testing third-party programs in a setting where things are as difficult as can be. You only have the binary, you not even have the binary, you have no knowledge, you have no access to developers, no source code whatsoever. That's what was new with fuzzing when Bart Miller introduced this in the 1989.
All right, thank you. It's a very comprehensive description. And I think, as you mentioned, there is the security keyword that I heard a lot here. SBST usually is on the finding functional bugs, and also I've seen many papers on fuzzing testing security issues. Is that a real difference? Do we as SBST researchers test for security? And I mean, yeah. Go on.
Me? Okay. So when I did my PhD, in symbolic execution. The first paper that I published was 2014 ICSI partition-based regression verification. So symbolic execution, and so what do I do when somebody asked, "What do you do?" My friends asked me. I told them, "Well, I find bugs." So blue screens didn't really sound interesting. But now I tell my friends that I find security flaws in the supply chain, and security flaws that you are definitely going to be impacted by. Right. So my tools run at OSS Fuzz, which is fuzzing 500 open source projects, 24 hours, 7 days a week, on 25,000 machines. So I find security flaws. Sounds much more interesting. There's money in security flaws. But the problem is the same, right? Conceptually, intellectually, we are still finding bugs. So I think it's just a matter of selling that research. And but maybe I can also add to Andreas' quote unquote rant. Fuzzing, I think, is a lot more structured than it might appear to be. I think what we do though is, instead of exploring different ways of searching for an objective, right? We want to satisfy an objective in search. We are interested in performance. So how cost intensive the fitness function is, how much time you spend in computing the fitness of a certain test is something which we really care about in fuzzing, and which we have optimized. And that's why security vulnerabilities, that's why I think the drive to kind of make this applicable in industry is also something which has driven the fuzzing community.
All right, thank you.
So maybe there is anyone else wanted to join?
Yeah. I think anybody, Paolo.
Okay, can I take the lead? Sorry, Paolo. I'll take over a little bit. No, so I definitely agree with what much has been said. I think the one big difference is that obviously in fuzzing we look at the bugs. If you find the bugs, we're happy. In search-based, sometimes we also look at, for us also, the test cases. They don't find bugs can be useful. It depends if you want to give some confidence level that, for example, the system is reliable to certain type. I'm thinking about machine learning, right? If I create tests for machine learning for different counterexample, I know that the model works well with certain counterexample. This also is an important result to show that the system is robust. So the bugs matters. There's plenty of search-based technique also applied to find bugs. But then let's say the test case, they do not find bugs actually also useful in many contexts. We can give level of not guarantees, but confidence that the system is robust enough. Although to be honest, I have slightly different. I think I introduced in the introduction, and I think probably Myra agrees with me. I see actually the setting is in a different way, right? So in search-based, in theory, we don't need to have a fitness function. We don't need to use evolutionary algorithm. So, well, Mark, you define it, but search means we use optimization, whatever that means. And that can be random search, that can be evolutionary algorithm. And the fitness function can be extremely expensive, very well suited to the code, or could be a bit more grained level. It doesn't matter. But to me, at least, it's still search-based. And then depends on how much, let's say, guidance we want to introduce. We go toward what we call now the search-based, but then obviously as an overhead for that. And then if you want to go like less heavy computation, then we go for fuzzing. But I can tell, at least looking at the paper lately, also in the top venues, really it's a really confusing understanding when the draw lines is. I'm not making any name, but just to make an example, there is a paper I've read in XC 2020 where they call this is fuzzing. But at the end, they were using many objective genetic algorithms. They were used approach level and branch distances, which is the same thing we use for search-based. And it was rebranded with the entire paragraph. This is not search-based. This is fuzzing. And honestly, I found really, really confusing to understand where the line is. So it's just a matter of names. Anyhow, so for this, I wanted just to say, I agree. There's a lot of join. Maybe none is above the other, just the same thing, and we decided how we wanted to interpret. So the fact that maybe I see search-based as broader things, and other people here see like fuzzy is a broader things, maybe it's just a way to say they're probably just the same thing, and we should just use a proper, common naming and common guidelines. I think the about what you're looking for has a huge impact on how we evaluate the tool. So if, for example, if I want to submit a paper on test case generation, then maybe I need to go for a smaller benchmark, but many repetitions to do a statistical test. If I have to target for fuzzing, then I don't care about statistical test. I go for much larger benchmark, one repetition, I found some bugs. I've seen paper, for example, in the top XC this year, which is exactly what I see. Well, I open a search-based paper, smaller benchmark, statistical repetitions. I open a fuzzing paper, we find bugs, that's important, but on the statistical side, it's a bit different, right? Because if the benchmark is too large, we cannot do the repetition. And at least I can tell, when I try to submit to the two things, really depends on who is going to be the reviewer. So if I know his reviewer is a fuzzer person, I know what I have to target for. It's a search-based person, I have to know what I target for. It's both, then the paper is really on the luck, basically. I don't know who is going to take the strongest in the review process. But that's my personal experience, at least.
By the way, everyone, feel free to unmute yourself and talk right after the others. Okay?
I think Mark wanted to raise the hand, or Lionel, or both.
Go, Mark. Go ahead.
Oh, thank you very much, Lionel. Yeah, I tried the raise your hand option on the mid space, but it doesn't seem to do any electronic hand raising. So, yeah, jazz hands. I think there's a consensus here that these are really the same thing, and we could spend the next hour and a half discussing how minor differences. But actually, so if they are the same, then when you ask what is the difference, I think there is a difference in priority and the order in which things were considered, and that has led to more impact for techniques known as fuzzing than techniques known as SBST. And I think if you look at the origins of the two fields, then fuzzing started off by saying, let's just use random search and see what we can shake out. And SBST started off by saying, hey, we've got these clever algorithms. What's our fitness function going to be? What have we got? Coverage. Okay, let's measure that and try and optimize for it. And it turns out that if you just say, let's find bugs, as Andreas was saying earlier on, just anything to find bugs and start off with just random. The thing that got people excited about those first fuzzing papers in the early 90s was, hey, here's a bunch of really well-tested C utility functions that everyone's using every day, and yet we find bugs in them. Bugs that you didn't even know were there, bugs that you never even experienced yourself. Now, most people in industry at that point would say, okay, everybody's using these tools, they all work, nobody's experiencing these bugs, so you're just finding a load of bugs that don't matter. But the fuzzing people were smart. They thought, what kind of bugs can you have in systems that lie undiscovered for ages, that aren't really affecting any real users, that don't seem to be causing any real problem, but people should care about? Let's go after security. And that, in my humble opinion, is why all of this fuzzing work latched on to security as the killer app, the vertical that they go after, and they mined it to death. And they went fantastically well, because they just said, we want to find as many bugs as we can, as fast as we can, and it's got to be practical. So we've got to deploy it in industry on big systems, but we're only going to use random search. We're going to make it fast as hell, and we're going to find as many bugs as we can. And that meant that they, if you look at AFL's list of bugs found, it's bug kind of, like trophy store. It's phenomenal, right? So I think that that's something the SBST community, the communities are different, but the technologically, there's no real difference, right? So the SBST community can learn a lot from that, the power of random search and finding a good vertical. But interestingly, what's happened is the fuzzing community has come around and said, no, we've been doing this random search for about 10 or 15 years, and we found all the bugs we can. What could we do to make our search smarter? Maybe. And then as Leona was saying, I think it was Leona, I can't remember, so it's saying like, oh, well, maybe we should put these other things around it and have, for smart seed searching, and, let's use evolutionary algorithms. So really now we're in a technical position where the only difference is that in SBST, random is somewhere buried in the heart of it when you get stuck. And the smarter optimization algorithms are right in the core granularity. Whereas with fuzzing, just because that historical happenstance, random is right at the heart, and the smarter stuff is in the outer loop, but really that's the only technical difference I can see, and it's not one we should, I think, spend too long on. That's what I think.
Well, can I follow up? I actually think that maybe it's more philosophical, and when I think about SBST, I think about a problem, and I think about modeling it as some sort of search problem, and I think about, what are my objectives? And I have lots of different objectives I may use, and they're going to change. And with fuzzing, I think about it being as more of a technique that fits a particular topic, in this case, trying to find security bugs. And so every time I approach an SBST problem, I think about, okay, how am I going to model this? How am I going to represent it? What are going to be my objectives? Are I going to balance my objectives? Am I going to have some sort of Pareto front I'm interested in? And so I think about more of it as a modeling problem and approaching it that way. So maybe under the covers, the techniques are exactly the same, but to me, what differentiates them is sort of the use case and how they're being viewed. And so I'll let others respond to
that. I think we all agree that there are many similarities, and that the differences in vocabulary and emphasis comes from the fact that it originated from different communities. I agree with what everybody said, also Annibale. But as a result, it's not just a difference in vocabulary. It has other consequences. The most serious consequence is that the different research communities largely ignore each other. If you look at fuzzing papers, they talk about future work. In their future work descriptions, for example, they talk about things that have already been done, but using a different vocabulary. They do not reference related work. Why? Because that work doesn't use the word fuzz, but rather security or vulnerability testing or search-based testing. And this is, from a scientific standpoint, it's a problem. And but of course, it's a problem which has a solution, which is for the communities to work together and to organize common events. I don't know exactly how to do that, but and beyond vocabulary, there is also, and Annibale said that, and also Mark, there is a difference in emphasis. But sometimes, again, this leads to ignoring existing solutions. For example, you have a lot of recent surveys on fuzzing who are asking questions along the lines, oh, maybe we should use the statistical testing in analyzing results. Questions like that, And, in other types of questions whose answer is pretty obvious and has already been worked out, So it's not just a matter of using a different vocabulary and putting a different emphasis on things. It has actually consequences on scientific progress and integrity, unfortunately.
With Lionel here. I was working on a paper with a PhD student of ours at UCL on fuzzing, and they looked into the main shortcomings of fuzzing papers in the past few years, and one of them was lack of statistical tests, for instance, or lack of multiple repetitions, which is something that SBST no SBST reviewer would let it pass, in a paper, that because of all the established ideal in the community. So doing the rebranding, if we looked at each other's literature, we would pick those problems and maybe solve those scientific problems.
Some anecdotes here. In my last reviewing for CCS, which is computer communication security, I always get the fuzzing papers, and I'm happy to review them. So in my last gig of that, I had folks who invented configuration testing. IMARA. So they invented the idea that a program could actually come in various configurations, and one could test these systematically. They even went as far as reinventing pair coverage. Another author invented the idea of rather than calling the program with random input and random system input, how about we call individual functions directly? So they would synthesize sequences of function calls, which they would invoke with random arguments. This was all new. Nobody ever in the community had thought about that. The third paper I had was people reinventing model-based testing. They came up with the idea, if only we had a model of a state machine of things in order to test things, we could actually use the state machine to derive test cases. This is incredible. This is not just rebranding. This is cultural appropriation, what we're seeing here. So I'm having fun in these. I'm having fun as a reviewer because I can kill these papers with 2-3 strokes, and I feel like a karate fighter or something. You're dead. That's fun. But what's even more striking is that typically none of my co-reviewers noticed that. So which is what I'm now more or less routinely serving on. I never decline an invitation from the security community, because I think that we should serve more on different communities. Maybe, and that's a call for us, for SBST/test generation/engineering community, we should also have more security researchers in our field, such that they get an idea of what's going on over here.
Very good. Yeah, Marcel.
Yeah, so I entirely agree also with Andreas, and Mark raised his concern in chat earlier, or his suggested this in chat earlier. We should all come together as a community. And I wouldn't blame the authors for not knowing work that we did in SBST. I think that's something which is emerging from engagement from in between both communities. And without this engagement, we'll just work in silos. We can make a similar point from that Andreas made about fuzzing, not doing statistical tests, and reinventing problems and solutions. For instance, one thing in SBST that always struck me was that we compared. So our fitness function, a typical fitness function in SBST is coverage. You want to maximize coverage, and coverage being a proxy for bug finding. And so SBST work is then published with, we have a fuzzer whose objective function is to increase coverage. Sorry, we don't have a fuzzer, we have a test generation technique whose objective is to increase coverage. And then we measure the coverage of that test suite that is generated. And then claim that our method that now increases, that has more coverage, is better in terms of bug finding than the other technique, the other SBST technique that we had before. And this might not obviously be true. And because of this focus of the security community on bugs, people have actually investigated this. Of course, in software testing, this test suite effectiveness question has been studied a lot too. But recent evidence, particularly for test generation and particularly for fuzzing, shows that the agreement between an evaluation based on coverage and an evaluation based on bugs might be moderate, might not be strong. So that's interesting because the different perspectives of the communities where bug finding is just not that important. Maximizing fitness function is more important in the SBST community, which is fine too.
So I think we can summarize this initial maybe part of the discussion that these two community, at least for next year SBST, should try to go together. They're related in the problem they want to solve. And of course, would be important also to include the security dimension. So to move a bit from this topic, general topic, with fuzzing, what is SBST, we had another probably wanted to talk, which is more difficult probably even. What is the impact of SBST and fuzzing in the last year? So the most complex part is what is impact first, and what you think was the impact that was expected to be achieved and has been achieved actually. So hopefully that's opened another door for the conversation. So who wants to start? Maybe you, Lionel, you have an opinion about what is impact or what could be the impact that has been achieved by...
Yes, I'm not 100% sure about the question, but I would say that on the SBST side, the main contribution has been the very deep exploration and evaluation of sophisticated search algorithms for a variety of testing problems. I'm focusing on testing here, it's SBST. And on the fuzzing side, I think the main contribution has been the combination of a variety of techniques ranging from static analysis, symbolic execution, and others, together with some form of search to solve problems related to either white box, gray box, or white box generation. So I think those are the main contribution. And for the latter, for fuzzing, I find that there is a lot of interesting work that somehow smartly combines those different techniques. And I find that interesting as well. Even though in SBST too, we have been trying to combine techniques. I mean, for example, I've been working recently on generating test data based on very complex constraints at the system level, combining exactly this, combining solvers and search. So we also do that on the SBST side, but it has probably been more of an emphasis on the fuzzing side.
Great, thank you. As Mark said, there's a simple impact metric of breadth times width. Is there a way of measuring this maybe on using the impact of those tools in the industry, perhaps? If you fuzz or if you create automatically generated tests for industrial software, perhaps you're going to affect more people. Is there any relation in this sense? Is fuzzing being used more often in the industry? Is SBST is being used as often? How they impact in this case?
I think anybody wanted to join.
Yeah, so I would say definitely here I'm the least experienced with industrial partner compared all the all the panelists. But at least in my experience, industry, it doesn't really matter if you call this fuzzing or search-based. Probably they know more as fuzzing, and then I'll still do genetic algorithm and test case generation. I would say that definitely fuzzing is a keyword/brand is more known for the security aspect. I think in terms of impact, it's mostly what type of bugs are found. So we use search-based to find normal bugs, null pointer exception, right? But let's say there are important bugs, but not critical. And at the moment we look at I think Marcel said before, at the security vulnerability, of course, that's way more dangerous for the company. If you think about a bank and there's a vulnerability that people can steal money, this is a bug, but it's definitely more severe than a random null pointer exception in subpart, hidden part of the code that probably is very hard to get from the internet. So in terms of bug, I don't think there's more impact. I think they all find bugs, but definitely on what it matters for the business value. I think if you go to security, there's way more business value because it's more critical. Depends on the type of organization, but then normal bugs. That's at least what I can see. But when I talk to company, because you're definitely using some search-based testing with a partner, business or it's a large financial organization, really doesn't matter to them. I can call it sometimes fuzzer to let everyone understand exactly what we do. But for them, I don't think they really like, I want to use search-based, I want to use fuzzing. What they want is some automated tool that tell developer there is a bug here and there, and then it just run on the machine over the weekend, and maybe on Monday, there's plenty of bugs that can be double-checked by developers.
I mean, to me, I have always, as I just commented, I have always difficulties to talk about the industry or the impact in industry because I see such a variety of situations across domains. I see many companies, and yeah, I'm not talking about, the like of Facebook and Google's. I'm talking about, the more common companies that you see everywhere, relying on software in one way or another. The level of maturity of test automation is still largely very low. So a lot of the testing is still very much manual, except for the execution part. So I have all these difficulties to answer that. And on the other hand, you read and you hear about very large companies such as Apple, Facebook, Google, who have usually their own software engineering research departments, of course, applying much more sophisticated approaches to testing. So I don't know how to answer the question. Progress and impact is not the same across the board, far from that. It also depends on application domains as well. For example, the automotive industry obviously depends a great deal on software, and increasingly so, but their level of maturity, well, is not comparable to Apple, Facebook, or Google, in terms of software development. And there are many reasons for that. Their needs are also different. Their constraints are also different. But still, that's not the only explanation. So, yes, I'm sure fuzzing is used. It has had an impact in a variety of environments. But there are many environments where people don't use any form of smart test automation whatsoever. Why? That's another discussion. But I'll let the others answer the question.
Right, thank you.
Yeah, I like Mark's answer before the question was actually asked. When he went into Facebook or Meta, which is how is it called now? He explained Sapiens to them, and they asked, what is this? I mean, is this a fuzzing technique? And so this might be the answer: fuzzing, SBST, impact.
So,
where's Andreas? Okay, cool. Yeah. I think, Mark, you said you're going to have to leave a little bit later, right? A little bit early. Not yet.
Yes, that's right. Yeah. We finish at. Are we finishing in 13 minutes or an hour and 13 minutes?
We're finishing 1 hour and 15 minutes. Yeah.
Yeah.
You still have time. Okay. Great.
Not a plan. There's still time to talk about.
Okay, good.
I suddenly thought I'd done my calculation of time differences wrong, and I was supposed to be somewhere else.
I mean, this whole time zone thing is a little bit confusing. Anyway, yeah, I think what Lionel said before as well, like the domain in which the testing software is applied makes a lot of difference. As Mark typed in the chat as well, for instance, healthcare applications of computer vision for detecting specific kinds of tumor. Testing these, whether you test it with SBST or fuzzing, it's going to cause a large impact. Very good point. Yep.
May I? Go on, Lionel. Sorry.
No, go ahead.
Well, I was going to try and introduce a new question for the panel, so you may want to go first.
Yes. I think, anyway, one thing that both communities have in common and that are related to impact is the very difficult question of scalability. When you work with industry and you try to apply any techniques, whether it's fuzzing or SBST, you quickly are confronted to that problem. That most of what is published, most of what is written doesn't scale. And actually that was originally one of the big motivation of using search in software testing and other areas of software engineering. It was to address that issue of scalability. And to some extent it has helped, to a significant extent it has helped. But we always seem to be losing that race. As we make progress, things get larger, faster. So we are running after the problem, without ever solving it. But that's, to me, probably one of the most important obstacles to impact, along with practicality, because there are techniques that are just not practical. If you have to use symbolic execution, but you cannot handle floating points, numbers, like it is the case with symbolic execution, then you forget about cyber physical systems. You can just forget. I mean, don't even bother. And then forget about white box fuzzing. So so there are a lot of practical issues as well, due in part to limitations.
To Paolo, I think.
So related to this, I think an important aspect is the cost of an individual execution, because in search-based, but also in fuzzing, you have to execute a lot in order to learn, to follow the guidance and get the result that you need. What I really like in search-based techniques, which I'm not sure is available in fuzzing, if you want to make a distinction, is that we have a lot of different meta-heuristic algorithms that we can choose from. And some are more heavyweight, some are lightweight in terms of cost of execution, of computational demands. So if you start with a population-based algorithm, then you know that you have to execute the entire population of individuals before you can assess the fitness and get the best individuals, and you can evolve them. But at the other extreme, you can go greedy. You can use hill climbing, you evolve a single individual, and then you get to something maybe locally optimal, but still useful in a much more fast way. So that's an interesting aspect that I see in search-based techniques. I'm not sure if in fuzzing they invented something similar, or if they have this kind of configurability of the cost of the execution, because that's a big obstacle to the applicability of these techniques.
So there's been a lot of research in speeding up fitness functions, speeding up the coverage feedback essentially, and using machines like CPU features for this, hardware features for this. So there's some research in reducing the cost as much as possible.
Okay, maybe I can add something. So what, Paolo, what you mentioned, right? They have different search algorithm. So I've read, obviously, not as many papers Marcel had done on fuzzing. So correct me if I'm wrong, but from my understanding, many papers on fuzzing, they do use evolutionary algorithm, but often they don't call it like that. So for example, there is the initial seed, which is what we call the initial sample, initial population, and then they don't do crossover, they just mutate, for example, some seed, or they randomly sample new seeds. But this is in evolutionary computation, it's like a mu lambda evolutionary algorithm without crossover. At least when I read some of these papers, it's exactly the same thing. So you have some sampling and you mutate the sampling to search around in the region, but just not called evolutionary algorithm. It's called mutation-based, whatever, or seed-based, etc. But of course, Marcel, you are the expert here, so if I'm saying something wrong, feel free to stop me. I know some people do cross the line between fuzzing a search base where the crossover is there or not. So I've seen some people like, we don't use crossover, so there's not a search algorithm, we just use mutation. This is fuzzing, but there's a category evolution algorithm also without crossover, and hill climbing is an example. So I said this is also one thing I found a little bit fuzzing on how we define when an algorithm is evolutionary algorithm, when an algorithm is actually a fuzzing algorithm. So it's fuzzing in the fuzzing, yes.
Would you say it's a fuzz, kind of like a fuzz topic? Fuzzy topic? Right.
Should I respond to that?
Yeah.
Okay, so people in fuzzing don't think of the typical gray box fuzzing algorithm as an evolutionary algorithm. They think of it as more like a novelty search. You simply, the algorithm is very simple. You keep on generating inputs. You start with an initial corpus. You modify the seeds in that initial corpus that you call initial population. And anything that improves the fitness, any input that increases coverage will be added to the corpus. Every other inputs will be thrown away. So there's no population that is being evolved like in evolutionary algorithms. It's just adding new inputs that increase coverage to the seed corpus with the intention of fuzzing that input and increasing coverage further.
If I may say, then in that case, I would call this an archive-based evolutionary algorithm. There is no population, it's the simple hill climber with an archive. So you run new, and when it's new, you add it to the final archive. There's even actually a later version called double archive. Yeah, but there are variants of, so the thing is, at least I'm not an expert in evolutionary computation, but in the optimization based on evolution, there's many sub-variants of evolutionary algorithm. It's true that in SBST, maybe we stick too much to classical genetic algorithm. There are so many variants with population, with multiple population, with archive, with multiple archive, etc. So in that case, for what I understand from your explanation, I would call it that an archive-based hill climber.
All right. I think Mark wanted to introduce a question before, Mark.
Hi, yeah, I did. Can I introduce you to my friend I brought along here, who's been in the room? We've been in the room. This is my friend, the elephant, who's called Oracle. And she's been in the room for an hour now, and we haven't mentioned her once. So we did agree that these two technologies are largely the same. So it would be good, therefore, particularly if we think about how can we build a community shared, get them together and so on. It would be really great if we could actually work out what is a shared problem for both communities, because then we could have workshops on how we can tackle that, and then all the differences would fall away. And it seems to me that both these technologies, the ways they've developed, have got this real problem with the Oracle problem, because we essentially, what fuzzing did, sorry, Andreas, I'll yield to you in a second. I can see you're very keen to, I want to finish my framing of the question. So you know, the reason fuzzing was so successful is because it went after the implicit oracle really early on. You know, we went after, in SBST community, we went after things like coverage, and we had this a huge panoply, as Paolo was saying, of possible things we could go after because we got fitness, whereas they just had this simple hammer, right? Just go after random search. So whenever I've seen any testing technology be successful in industry, it's almost always been because you just go after the implicit oracle. Things shouldn't crash, things shouldn't go out of memory, you know, these kind of things. When it always gets harder is when we try to imbue the technique with some kind of oracle intelligence. And I feel like the reason I'd like to spend some time on this is, firstly, I'd love to ask the audience, you know, like on Who Wants to Be a Millionaire? I tried phoning a friend. If I was a fuzzer, I'm sure I'd do 50-50, you know, but, you know, ask the audience, you know, like what ideas could we have on how to solve or tackle the oracle problem? Because this would be interesting to fuzzers and SBST, I think. Anyway, sorry, Andreas, I think you're keen to talk, sorry.
Yeah, I also saw the elephant in the room, so the oracle problem, of course. And I'm happy to report that in the fuzzing community, there is no oracle problem. It simply doesn't exist. If the oracle problem, these very words exist in the security community, and this is about the oracle problem in Ethereum contracts. By the way, today, if I Google the oracle problem, I end up with Ethereum contracts, certainly not with anything related to test generation. Maybe it is related to test generation, but the oracle problem is also a word that now has been culturally appropriated, has been taken over by some other community apparently. Now, why is there no oracle problem in the fuzzing community? Because it's all about exploitable bugs and a crash. Some undefined behavior is something that can actually be turned into an exploit. That's the first. That's what you start with. A hang. If the program hangs, this can be turned into a denial of service attack. We have crashes. We have hangs. We have depletion of resources. Depletion of resources also is an attack. There you go. This is it. All these are generic, implicit, and there's no need to specify anything. Having said that, the really, really big security issues that have made it into the front page of our newspapers are not related to crashes at all. Think about Heartbleed, for instance, when a TLS server happily sends out all sorts of memory contents, including passwords and whatnot. Think about recently, what was that? A Log4Shell, for instance, where anyone using some dollar colleague brace, whatever, JNDI thingy, can execute a shell on a foreign server just because we can. Boom. These are all things that in principle could be found by fuzzing / test generation / test automation whatsoever, but they're not. And they're not because they go under the radar and because we don't have oracles to check for these. And the fuzzing community doesn't see this because for them, these are things that are, well, would require some kind of specification, and the word specification is actually hated over there because you have to understand you're talking about other people's programs. The last thing you want to do is to write a specification for someone else's program, so they're not really willing to do that. But if we can come up with better notions for oracles, possibly generic oracles for security issues, thou shalt not leak this data, thou shalt not gain control over that, and if we had means to also validate these during testing and actually guide our approaches towards the ability to control things, towards the risk of leaking things, yeah, then we could make quite a splash.
Paolo.
So I agree that if we go for some more subtle properties, the oracle becomes more difficult. So if in security, if you want to prevent SQL injection, common injection, or escalation of privileges, these kind of things, then the Oracle is not definitely, the application should not crash or something like that. It's you have to encode it, but I see a difference with respect to functional testing, because in functional testing somehow the Oracle is very application domain specific or very application specific. In security, you are a little bit luckier because all the ones that I mentioned are security properties that should hold across applications. So of course, instantiating them for a specific application is not trivial, but at least you have like a high level description of what is a security property that should hold, and the problem becomes more a translation problem, which is not trivial, of course, but that's the kind of problem you have to face. In functional testing, even expressing the specs, what is a desirable property is difficult and probably is not reusable across applications. So in this respect, doing functional testing seems harder to me.
All right. Well, I think I have echo on my side. I'll try to. Do you hear any echo? No, okay, then it's my side. Okay, that's easy. No, I wanted to add, this is in theory, right? So fuzzing is about security, and search-based is about other type of testing. But I have to be honest, lately I'm getting very confused on what I see, because now we have also paper that, for example, do adversarial example for machine learning. It's called fuzzing. But we also have like the same thing, search-based technique applied into security. And then we can call it search-based, just ignore completely what the fuzzing community has done so far. So I think it's good that we are discussing this, and we should definitely probably open up in between the sub-community. We are at the moment, right, that actually we start crossing the line with just different terms that we don't really know. I'm talking for myself, for example, what is done on the other subfield. There was, for example, lately, as an example, in cyber physical system, testing for self-driving cars, and we have like half of the paper called as search-based testing and half of the paper called as fuzzing testing for finding not vulnerability but exactly the same type of things. So car crashing, accident, etc. And obviously, at least my anecdotal evidence now, if I put fuzzer in the title, I have to go for certain standards in the evaluation. So many ones, bugs, we don't care about coverage, etc. If I go for search-based, maybe I'm not super sure about how many crashes I have, but I have to provide statistical analysis, lower random things, etc. So I think the problem, at least I'm facing as orders at the moment, it really depends which keyword I put in the title, what type of, okay, obviously we do research for research, not for getting accepted or for making the reviewer happy, but it's some kind of relations in there. And I think we are definitely the problem where if we target the same problem, we don't know exactly at this point which of the two stands. We have to my view, two different standards for evaluating things. And since now we apply the same technique, not only in our confined sub-area of security and non-security, I think I've seen at least a bit of a problem. I have a problem in classifying papers when it's not about security or functional testing, for example. And also how do we do the evaluation? So that's probably something we should work together to establish common guidelines, empirical guidelines or something on those lines. I don't know what is the thought of the other panelists about that. If you also face the similar issues as well, both as authors, also as reviewer.
So one of the panelists here, Lionel, is one of the authors of one of the most influential benchmarking papers for randomized algorithms. So I think it already sets the scene for what we at least expect in the minimal sense.
Yes. The Oracle issue, as I wrote in the chat, to me is orthogonal, but of course highly important. Any test automation technique needs a way to obviously detect failures automatically. Of course, if you only rely on crashes and such runtime problems, you limit yourself in terms of your capability to detect problems. And in my experience, there are a lot of critical problems in practice that do not lead to crashes, even in security, where the system doesn't crash but leaks data, for example. So then you can just ignore that. But I guess anybody interested in test automation has to be interested in the automation of test oracles. I mean, it's an unavoidable problem. Hence, for example, the rapid development of the area of research referred to as metamorphic testing, whose objective is to help minimize the effort associated with automated oracles, because that effort should not be proportional to the number of test cases you execute. Well, yeah, I agree. But I think it's a little bit different than the main focus of this panel, though.
So I think you wanna.
Yeah, so I think one of the most exciting recent developments in the Oracle problem, I don't know whether it belongs to the fuzzing community or the SBST community or the general automated testing community, is equivalence modulo inputs, EMI testing, where you have, and they find a lot of bugs recently, and particularly under Chen Dong's group. When the key idea is essentially you take something and you have an expectation, then you make a change to that something, and then you expect a certain change at the output. Okay, let me be more concrete. You're testing a compiler. A compiler takes as inputs a source code, right? A source code that is being compiled. What you do is you don't need to know anything about that compiler, but you know how you can change that source code in a way that it doesn't change the meaning of that source code. Maybe you inject some unreachable statements. So you change that source code and see what the compiler does for this. And then you compare these two executions, the original execution and the expectation for that execution that you have. And if there's any difference, then you report that as a bug. And this is a semantic oracle because even though you don't need to know what the compiler does and how it compiles anything, it shouldn't change. You can do the same for databases. You can do the same for SAT solvers. And I think there's a lot more to explore in this direction.
I also think there was a keyword used by Lionel before, test cases. Perhaps in SBST the oracle is more visible in a test case with all the assertions, whereas in fuzzing your oracle is the crashing, right? And this leads to a small difference that I observed, which is, at least that's my observation, which is in SBST we are concerned in generating good test cases, and in fuzzing it's more like system testing, isn't it?
So can I follow up on that? I agree with this. I think in SBST the focus has really been on generating the tests and making them more human readable and making them and tying them more to the problem. Whereas fuzzing, I think the tests that are generated, it's less relevant if they're something that I can comprehend. And so I think that people have also focused on really minimizing the tests and getting good coverage in the SBST community, which helps you at least have a potential for manual oracle development. So I think that there's been probably more focus on the functional oracle rather than just crashing in the SBST community. But and I agree with the metamorphic part. I think we should be thinking about how we could do metamorphic testing both in fuzzing and SBST, because it's a really interesting question, and I think that's the future of a lot of oracles that we don't have, because we're not going to have functional outputs as we move more into ML and other environments.
Great, thank you. Mark, is your question about Oracle answered? Do you have something else to add?
But I don't propose you need to necessarily spend more time on it if there are other things we should be talking about. Oracle's happy you talked about her anyway. Let's see, she's smiling in it.
Okay, cool. I think there's another point that I think we could talk about, and which is the domain in which those two techniques are usually applied. For instance, is there any difference between applying SBST or fuzzing and the popularity between those two techniques in, let's say, mobile applications? What is used currently for testing mobile applications, or, you know, testing ML, as someone mentioned, right?
I will also add, as Eric mentioned in the chat, superficial system and maybe enabled systems, make it broad and connect to the keynote today. And I think Paolo already exhaustively answered, but I think many other people want to join on this, since we are talking about fuzzing SBST in a general sense.
Okay, no comments on this? Guess it's not interesting. Okay. All right, so I guess we can perhaps talk a little bit about some shortcomings of the techniques. As someone mentioned, there is the scalability problem, which everyone is concerned, and there is research currently being done on reducing the cost and making it more scalable. But do you have any insights on the current limitations of the techniques, and where should we focus or test automation research? Let's not say fuzzing SBST anymore. What are the main limitations for those techniques? What we should be focusing right now?
I mean, to me, my experience when working on real problems in real context is that using one type of technique, meta-heuristic search of some kind, any kind of problem analysis, usually doesn't cut it. Usually, the solution requires a smart combination of techniques. And actually, that's what fuzzing is doing to some extent already. But I was never able to solve a real problem in a real context by using only search or by using only a given technique, whatever it is. I always had to somehow think very carefully about how to smartly combine them. So search-based SBST should not restrict itself to search techniques and should interface with other communities if we, actually the fuzzing community has been successfully doing so. If we want to solve real problems in a practical and scalable way. And it's not easy, of course, but I think it's indispensable.
So Paolo, I think you were raising your hand.
So a follow-up to what Lionel just said is my experience, the importance of surrogate models. So that's something that is not so much used and explored in the research, but whenever I face a complex problem, currently I'm working a lot on deep learning systems like self-driving cars or drones, and cost of execution is a big issue, and if you can replace some of these executions with a surrogate model that can anticipate, that can predict what's going to be returned by the fitness, then that's going to help a lot. And I mean, Lionel is one who investigated these. There's great papers by Lionel on these. We are also doing it, and that's probably something useful across both communities.
I have 3 problems that come to my mind immediately, where things that we should work on. One problem that is, and I think I resonate with Lionel and Paolo here, one thing that is commonly under-researched or underestimated is the effort for setting up test automation. Also, if you think about, I am just going to use a fuzzer and I'm going to throw this fuzzer to the input of the system, where is that input? How can I actually start the execution of the system? How can I feed this input into the right place? This is in practical systems, which are not just whatever some Unix utilities with standard in and standard out, where you can make this whole thing a part of a pipeline. This is a big, big problem. Suppose I have something simple, an Android app, and this Android app communicates with the server, and I want to fuzz this server interaction. How on earth do I do this? Well, I can have a PhD work on that, maybe for a month or maybe for 2. Then he or she may come up with a solution. But this is difficult. This is hard. Simply figuring out all the many, many ways a system can interact with its environment beyond just standard input. The second thing, is performance. I mean, we are routinely talking about settings in which we graciously assume that we can execute a program 100,000 or 1 million times. Why not? I mean, I recently had this discussion with a PL person, and we said, oh, I want to use a grammar for producing valid inputs. And he said, why do you do that? Why don't you just generate random inputs and call the compiler every time until you finally get something that is actually syntactically valid? Interestingly, that works. If you send a single semicolon to the GNU-C compiler, that's actually a valid C program, so you're done. But the thing is, you cannot simply assume that this is actually feasible. If you're talking about testing cyber-physical systems, you may end up with settings in which 1 run per minute may be the right thing to think about. Okay, so this is so this means that we actually need means to extract models from these systems and test the models rather than the actual real thing. Lionel has had an ERC proposal on these very topics. But these are things that any kind of test generation would greatly profit from. And while we're talking about extracting models and testing these models, one thing that is true for all sorts of test generation, academic test generation research, as I've seen it, is in practice, people have a good idea on where the bugs are. And they have a good idea on what should be tested. And they have a good idea on where, on the properties of an input that actually might help in finding bugs. Yet all of our settings assume there's no human in the loop, which is fine for automatic evaluation because, yeah, let's just send this off and let's hope that it's going to find some bugs. But in practice, you always have developers who have an idea of what should be tested and what should be tested most, or where the past bugs have been. And this is not just data that one can go and extract automatically from some bug repository. Yes, you can do that too. But we seriously should think more about finding ways to integrate humans and to give humans control over what is being tested and how it is being tested. And these 3 things, increasing performance, not requiring millions of test executions, easing setting up things, and giving users control over what is to be tested. These are things which may be less attractive from a research point of view. It's like, say, build systems, something that, or build systems or configuration systems, packaging on Linux, whatsoever. These are things that do not necessarily attract much attention from the academic side. Yet there's so many people suffering from them. And putting humans in the loop, yes, this is far more effort than doing things automatically. But these are things that can make our tools far more powerful and make them far more integrated into the daily routine of our testers.
I guess this is an interesting topic, humans in the loop testing. So maybe other people wanna elaborate a bit on their point of view on that topic, on this topic.
I'd like to just bring up one other issue that I think is that we haven't talked about that's really important with both of these topics is this idea of flakiness, because we're using these automated techniques, and I've experienced this both in the SBST community, but also when using fuzzers. And we're executing things a single time, we're trying to cover something. And so I know that a lot of the SBST techniques at the end, once we've generated the tests, we can now go back and confirm that they really do pass or fail. And so maybe there's a little more built-in ability to detect flakiness, whereas fuzzing, my impression is that we get what we get. So I'll leave that open and see if people want to answer that.
Well, flakiness is related to the oracle problem we talked about before. I mean, partly. Obviously, whether your tests are flaky also depends on how, how, I don't know how to say that, how accurate, I'm not sure that's the right word, your oracles are. So the two are related, but of course that's not the only factor of flakiness.
I'm pretty sure if you ask anybody in any practical testing scenario, what's your biggest problem, bugbear, they'll say test flakiness. So I think Myra's raised an important point there.
Yeah, I think one aspect of flakiness is related to the guidance that you want to give to the search process, because sometimes to get guidance, you have to somehow mitigate flakiness. If you have like a complex environment where different executions are always slightly different, because I mean, the environment itself is non-deterministic. Then if you want to get usable feedback for the process, for the generation process, then you have to do a single run multiple times, and then you have to average, or you have to compute the worst case scenario in multiple executions, which adds to the cost of execution problem. So really it makes it explode.
Regarding the human in the loop, I find that this is a very large source of uncertainty and complexity in what we do. And the reason is that we cannot make any assumptions about the human in the loop in our profession. You know, I don't know, in other professions, if you are civil engineers, where you can make some assumptions about how a civil engineer works and what he knows, you know. But a software developer, I mean, you know, given the variety of software developers I've seen in various domains, you cannot make any assumption. So then if you cannot make any assumption about what they know, what they can do, what they cannot do, it's very hard to devise a solution that you can claim is generally applicable. I mean, usually that doesn't exist.
Marcel?
Yeah, so I have two aspects on human in the loop. The first is when you talk to people in the industry about fuzzing versus static analysis tools, the first problem they point out is exactly which Andreas said earlier. You have to set up the fuzzer. You have to somehow glue the fuzzer to your target. And so this process of gluing your fuzzer to the target is very elaborate, and people that don't know fuzzing require some guidance. So there's some research in fuzzing about generating this glue between the fuzzer and the target. But still, I mean, if we could help with these manual processes. So static analysis tool, just for comparison, you just point the static analysis tool to your program. It doesn't even need to compile, and it tells you which bugs there are. So how can we help the human in kind of setting up, making it easier, onboarding your project in a very simple term way? So for instance, VS Code, which is an IDE now, also integrates some initial fuzzing kind of annotations you can do. And the second aspect that I would like to talk about is when you look at Google Zero. So at Google, what they have, they scale a team of 5 people to 25,000 machines using fuzzing. They can fuzz 500 open source projects, and there'll be more on these many machines. So fuzzing allows you to scale a small set of people to a large number of machines, and it finds bugs, and it continues to find bugs forever, right? But Google also has another team, which is called Google Zero, where they actually employ the elite hackers to find bugs in your programs. So they also use fuzzing, but in not as a process that starts from setting up and then continue let it run forever, but that uses fuzzing more like an integration into their search for these bugs. So they look for, as Andrea said, they have an intuition. This is where maybe we can find a bug. So then the objective is to generate inputs that would then expose this bug. And so they do this in a very iterative way and followed by intuition. So maybe another way of looking at fuzzing and human-in-the-loop fuzzing is how can we integrate, how can we kind of scale that elite hacker team better by just providing them better tools, bug finding tools. And fuzzing could be one component in this.
Anybody? On the spot.
I think Annibale just left. Oh no, he's back again. Okay, I'm going to start anyway. Okay, there is research that is simple, and there is research that is hard. Research with humans is far more complex and far harder than anything I can just kick off automatically, maybe on 500 machines at a time. If I come back with bugs, that's all fine too. Having said that, though, the amount of automation we're having right now also encourages benchmark-driven research. So as long as our efforts are being evaluated, not even by proxy measures such as coverage, but actually by statistically very shaky measures such as the number of bugs found. What does it mean? One technique found one bug, the other one technique found 0 bugs. What is the statistical meaning of this, if at all? Okay. Yet I see this plenty of times in security papers. Our technique found 3 bugs, the other one found 2 bugs. Therefore, our technique is better. Having said that, the 2 bugs that were found by the old technique actually were found ages ago and have long been fixed. That this is not a good measure. If there was one thing I would wish for, and which can also be subject of research, is actually far more independent evaluation of tools. It's far too easy when you are doing things automatically, in particular, to twist your research such that it fits a given target. You have you want to find a particular bug. You already know that this bug exists and you want to find it. Yeah, sure, I can turn a couple of screws in my hyperparameters. I can adapt my algorithm such that it searches in the right places and for the right amount of time. I've even had stories of groups employing hackers to find bugs first, and then later the tool was tuned to rediscover these very bugs that were already known. And that's something I find, and combine that with the fact that, in particular in the security community, sharing of tools and data is largely not done. So you cannot simply download the whatever fuzzer from this and that paper and try it out on your own benchmarks. No, that's not possible in most cases. Not even as a reviewer you can. So typically papers contain this wonderful series. We will release the tool sometime after it has been accepted. Where sometime obviously is like in temporal logic, always eventually release or something, but no idea of any time frame. And if there's some kind of research that I would see, it's not so much about, oh, we came up with this novel we came up with this novel tuning of using whatever neural nets to tune the AFL choice of such and such in order to in order to be even better than before, because none of this is actually motivated by any observation or so, just comes out of the blue. What I would like to see is much more independent evaluation of tools, and also research standards that allow us to do that. Because if I can tune my approach arbitrarily towards a particular benchmark, well, what does it mean if I then produce a tool that fits that benchmark? Actually, these papers are not even harmless; they're actually harmful, because others will be asked to compare against this tool, which is going to be very difficult if neither the tool nor the benchmark nor anything else is actually available. And that's something where I see, and we see plenty of papers like this, hundreds of papers where people do some arbitrary twist, and yet they are better than whatever was before. Oh yeah, how cool is that? And the tool's not available and the data is not there. This is not really helpful for research and test generation in the wider sense, whether you call it fuzzing or search-based test generation. I see this more on the fuzzing side of things. So, so you can all feel safe and non-threatened. But that if there was one wish where I would like to see more research, then it would be in actually trying out things and comparing things and finding out where the strengths of individual tools are and where the weaknesses are, and not as told by their creators, but as told by impartial evaluators.
Well,
actually, I had something to say first, but given the hint of what Andreas said, actually, I would like to continue on that a little bit. I think, Marcel, you published a paper recently, right? It's 10 out of 42 FADs that were actually available publicly, which is actually in the line of what Andreas said. I think about the benchmarking, but there is a common problem I see actually between FADing and test case generation, the benchmarking, that we use a benchmark of known bugs, because that makes the evaluation of the paper easier. Like we have 10 bugs, we know them, how many of those we find. But rarely I've seen actually paper that try to see, do we find new bugs as well, other than the one that actually are already part of the benchmarking. But that's obviously takes much more time to analyze each individual test, each individual crash, which make much easier not to run a CI/CD pipeline, run any tool, and if you find one extra bugs in the set of known bugs, that makes the publication much easier. But I would say this is an anti-pattern I've seen in both communities, not only fuzzing and not only test case generation. So actually, I wanted to say something on the previous part about putting developers into the loop. I think that it's important to add the sets in the beginning of the process, right? Because developers knowledge about exactly maybe where is the bug, what is the most difficult part of the code, the most complex part of the code. But I think we also need it afterwards, right? So we use fuzzing or test case generation, we find an exceptions, that's a bug, but obviously the bug needs to be fixed. So even how we provide the data and how we can explain why the crash happened, so the root cause analysis, is something that also I haven't seen that much as well. Right, I found the bug, we are happy, but is the input that triggers the bug that easy to understand for developer? At the end, it's something I would say widely unexplored as well. I think remember a few papers 10 years ago, I think from not less 5-6 years ago from Phil McMean about, for example, English-like readable inputs for string related programs. But that one is well, right, because that makes it more difficult as well. So we find crashes, we are happy, paper published. But are those crashes easy to understand? Are the test cases easy to understand with the test input? If you look at the fuzzing part, that one I think we should also work a little bit more.
Should we rebrand the research terms?
Yes, I think someone in the chat mentioned test automation. But as a devil advocate, I think in industry, testing automation is called for test execution. There's an entire developer-oriented is about how to run the test in automated fashion, multi-parallel fancy machines. So I'm not even sure that test automation is the right keyword here, if you don't want to confuse the practitioners.
Yeah, but there is no term that will not confuse some constituency of some kind. So, at least you can logically justify that phrase and explain that automation covers not only execution, but also generation, oracles, and so on.
Shall we call it automation 2.0 or deep automation?
You are good at new keywords. Yeah.
All right, great. Well, those are certainly many problems that we can advance on. I think we mentioned scalability, human in the loop, flakiness, and many others. And I just want to point out something very interesting. When Myra said flakiness, everybody nodded, said, yeah, that's a good point. Mark also went far and said this is one of the most troublesome problems in testing, but I don't think we mentioned any fuzzing or SBST paper that tries to acknowledge this problem and tries to solve this problem. What do you think is being done right now in search, in automation 2.0 to solve this problem? How should we solve this problem? Because this is clearly a hard one and a very impactful one, right? Do you have any insights on what to do forward?
At least in the search, at least in the SBST community, I mean, I think this is similar in some ways to, you think about like overfitting, or you have tests that maybe are too weak, and so a lot of times after we've searched, we rerun our test cases to see if we get similar results. I think that's the way the SBST community has tried to at perhaps crashes are less flaky, and I don't know, maybe that's why fuzzing hasn't addressed it as much, but I've seen some fuzzing tests recently that I was surprised were flaky. So I think it's out there, and I don't have perfect solutions, but I would be curious to hear if other people have them. So. Yeah.
I don't know if this is helpful, but one thing that I found in our company, and I think it's true in others as well, is there's an extra step when you deploy these tools that we don't tend to look at in the research community. And I think it's a step where you run all your test automation and you get some results from it. But then in between that and the developer, there's a separate piece of logic that decides what signal from all of this. Think of it as science. We do all this scientific experiments, automated or with human in the loop or whatever, we get some results. We don't just dump all that on the developer. There's a separate piece that says, let's decide what of this signal we're going to pass on to the developer. It might decide, for example, yes, this test failed, but it's flaky. It failed, but it's not an important bug. So all this stuff, this piece, in many of the companies I've seen, that there's a lot of effort goes into working out what to put in that piece, and yet it's not really something we research about. And I think if we could think, perhaps tackle that through the lens of at least asking, well, what would you do if you had all these results, but then you just have to decide what signal to pass on in terms of at least not bugging people about flakiness, then that would actually mean that a lot of the technologies that are developed in the academic community would instantly move a step closer to being immediately deployable.
I think this is a good point, Mark. Those signals, and it's totally doable, right? Because we have many executions of fuzzing for hours, and you have many executions of SBST. You have a lot of information to pass on. You just have to find those signals in there, right?
I mean, people have said that the research community tends to overfit on things like benchmarks and so on, and that's true. But maybe that's just a behaviour that is natural given all the kind of wider pressures to publish and so on. So maybe there's a way to turn that to an advantage by formulating some of these. I suppose that's down on us in industry to do this, but anyway, formulating some of this middle piece that seems to be missing in a lot of most research papers. Just say we find this many bugs and that's good, we're done. We find more bugs than them, so we're better, you know. But actually, this whole thing about deciding what signal you would pass on to developers to make it most actionable and so on is a kind of missing piece in the research picture. I guess to make it less missing, we'd have to actually try and turn it into a more crisp research question. So I'll shut up at this point and let others talk.
Thank you for your answer. I guess we have still 20 minutes, and I would like to use those 20 minutes maybe to talk about the path forward now. I think we have established that SBST and fuzzing are two communities with very similar problems, very similar research questions, many small differences. But what do you think would be the path forward to, bring the communities together, make one more aware of the other, perhaps stop rebranding things and citing papers from the other community? Is there anything we can do to solve this issue, this gap between the communities?
Yeah, one thing that we wanted to touch in this part is, for example, education could be one thing that could help moving forward from new, PhD student, new master courses that go on the long line. We'll have search-based fuzzing and showing, for example, the relation to them.
Well, I think Marcel already wrote something that I definitely agree with. Joint workshop and touch to seminars, etc. The other thing is maybe having hybrid program committee, right? Because we already have some dedicated workshop. SBST is an instance, but it's also the fuzzing workshop, I think last week or 2 weeks ago, I don't remember. Probably we built the subcommittee, right? Invited the same people and the same speakers, the same talk. This is the other things. Maybe the other thing we can look at also is to writing common shared guidelines for evaluation. There is something done lately on empirical evaluation. I think MC also was leading in that to build guidelines on how to evaluate also empirical study. Maybe there's also something we can do, knowing that we have different ways to look at evaluation and find common truths between the two sub-community. There might be a way to do that. Yeah, and probably using a common naming or keywords or whatever to be sure that we don't target sub-community as well. These are possibly, at least my view on this. But I would definitely rather go on the common shared guidelines on how to evaluate randomized algorithm, whatever that is, fuzzing or test case generation. Of course, Lionel, your paper on statistical analysis will be the top of the item list to look at, but that would be something to look at.
So should SBST next year be a combined SBST fuzzing? I was calling it SBuzz. I don't know if that works, SBuzz, but I feel like, should we make an explicit effort to try to put the communities together? And would that work? Would people, or are people just going to stay in their own silos? I'm not sure. And we have different approaches. And so I'm worried that bringing people together is not going to be as easy as possible.
Well, I think that could work. This year, for instance. Oh, sorry. Go ahead, Andreas. Daniel?
No, Andreas has a very good suggestion to even add to the current confusion.
I'm sorry here, but I agree with Marcel and what has been said before. I mean, there's some commonalities here. We're all interested in generating tests. We're all interested in finding bugs. This is true for all. This is what unites us, whether we consider ourselves security researchers or software engineering researchers or practitioners. We want to create good, reliable, bug-free software here. And actually crossing boundaries here, getting inspiration from various communities in various domains, finding out where the pitfalls are and where the successes are. This is great for us. This is exactly what we as researchers should be doing. And if the word software testing, maybe even search-based, if this keeps particular members of our research community out, maybe we should try to be as inclusive as possible.
Yeah, our joint goal is to find bugs, and we can develop and explore these techniques. And I think what we can raise the bar of is to make our science more reproducible, publish our tools, increase the soundness of our evaluation, and then be inclusive, as Andreas mentioned, and then actually facilitate, instead of arguing that the other community is stealing from the first community, and essentially facilitate the integration of both communities by organizing meetings, organizing joint workshops, organizing Dutch tours. I think all of us have the same goal, and so I think we should just continue this conversation, essentially.
I agree. We should join forces. By the way, Mark has to leave now. Mark, thanks for joining us. He's gonna leave a little bit earlier. Thanks for all the comments, and yeah, thank you. And I think, as Marcel said, joining forces, and also Myra mentioned about like maybe including fuzzing in the SBST next year. Actually, this year we explicitly added search-based fuzzing in the call for papers. Although we didn't receive any fuzzing paper, let it be known that SBST also accepts fuzzing papers with search. Yeah, right. And I guess maybe next year we can think about probably including fuzzing in the TOE competition as well, attracting more submissions that could, join both.
What about in the SBST tool competition, if we advertise it more we can have fuzzing versus SBST, and that would start a interesting competition.
Yeah, definitely. Imagine putting both in a boxing ring and see who wins. That could work. So I guess we can use. Okay, anybody?
Okay, maybe it's the very end. I'm sorry if I'm breaking this very conclusion discussion, the path forward. I posted something in the chat. I really want to know what's the panelist view of it. So we all agree, right? Fuzzing, search-based. We have a program. We want to find an input that reveals some counter or misbehavior or crashes, bugs, whatever. Now, if my input is an image and my test, the program under test is a machine learning, how should we call that? Search-based testing, fuzzing, or example generation?
Well, I think in deep learning testing, you see all of these, all the combinations you see. Well, if you look at the names of tools, there's DL fuzz that is very popular. It's a fuzzer, right? But it's not very different from other tools that generate using different search-based techniques, inputs images for GAN-based image generators or search-based generators. So I think you find the same problems and the same overlaps as we have discussed today.
Thank you. Well, let me share with you then I think Sebastiano was doing a great job during the entire discussion here, taking notes of the main discussion points and summarizing what basically.
So we need inputs from you if you are in the right direction, what to take for next year, what input, output will be of this meeting.
Exactly.
Maybe you go over a bit.
Would you like to?
Well, not that easy. There were different. No, it's okay. You can go, Giovanni. It's not a problem.
Yeah. Well, would you like to share the
Yes,
slide?
Yeah.
Yes, please.
I think there is a tension between two aspects. One is that it's natural for researchers to somehow regroup according to the type of technology they're interested in, whether it's meta-heuristic search or whatever else. And you find that in many areas of software engineering. So some people are interested in symbolic execution and so on. The problem is that this is not fully, this is not very effective in terms of problem solving. And in the end, we want to solve problems because it's an engineering discipline, and the goal is to solve problems. And more, and even furthermore, we need to solve problems in a large variety of contexts that require different solutions. Context being defined by the domain, the type of system being developed, the technology underlying the system, and so on. So we have that contradiction. As researchers, we focus on technologies we're interested in. We regroup according to that, and because we like to discuss with our peers on, whatever aspect of search, meta-heuristic search, or symbolic execution, or whatever else. And on the other hand, we need to solve problems that require multidisciplinary solutions. And somehow we have to resolve that. I'm not too sure how, but we have to resolve that if we want to have more impact. And both are justified. I mean, of course, it's justified to discuss with your peers about particular types of techniques you are commonly interested in. There's not, there's nothing wrong with that. But we have that tension between those two objectives that we need to resolve. How is not easy, and I don't. It could be a very long discussion, but I don't want to continue on this. I'll let other people speak.
Okay, I will try to share the screen. I think I am in problem with the access. Let me see now. So probably, John, you have to go because I think I want to use efficiently this time left, and we want to go over the few points. I try to summarize, but maybe. Yeah. So it seems to be that at least from the beginning of the conversation, it was very difficult to all of us to position in what was fuzzing, what was SBST, because they target very similar problems and they have very similar techniques. So one thing we could already do moving forward is SBST to be more inclusive, starting with dynamic. Maybe a provocative one would be search-based fuzzing, but maybe could be something a bit better, more tuning. But this is not really come so easy. We have to agree on the reviewing criteria because they have been evaluated in different ways, and Anibale mentioned a few times, but not all him. And of course, means also change the way the tour competition is made so far. We try to have a competition very inclusive. There is no differentiation really between fuzzing and SBST, but they are targeting the same problem. We try to think about what are the actual criteria. So I actually use the terms from Lionel. So we probably SBST and fuzzing community should work together. And what means that? It means to organizing common events, seminars, hybrid PC members. It could be one way to make it happen, making people applying to our calls. For sure, this means also to have criteria that are related maybe also to fuzzing. For example, the focus is security, has been talked a few times. Scalability is one important aspect to consider. When we go for complex system, surrogate models is something that maybe can achieve the goal of addressing the assessing the reliability of those systems. But even more challenging probably is very not yet clear how to do it is humans in the loop. That was been mentioned a few times by Andreas. And of course, scaling execution cost is really something that need to be addressed in a different way, in different forms. Yeah, fuzzy, sorry. And last but not least, probably even the Oracle probably could benefit to combining and putting together fuzzy fuzzing and SBST technique together, where one complementary problem that has been mentioned by also Myra and Lionel is flakiness, which is a complementary problem. There were probably the three main dimensions that we have identified. I don't know if we have missed anything on the way, but if there is any topic that you think should be included for moving forward the community, we are here. No.
Thank you very much for capturing all those notes, Sebastiano. And I think we have like 3 minutes left. I would like to thank all the panelists for this amazing discussion. We certainly killed some misconceptions about fuzzing, about SBST. We talked about problems and it was very insightful. I'm sure the audience really enjoyed it. And to be a little bit precise, we had 110 watchers at some point watching your discussion panel. So a really good turnout. Thank you very much. And would you like to add something else before we leave for a quick break?
This has been really exciting, and thanks for the invitation.
Yes, thank you for organizing a very interesting panel.
Yes, thank you for setting this up, and I'm leaving less sure about the difference. So I have a lot to think about after the panel.
There's a very fuzzy line between both topics.
Yeah. Actually, me and Giovanni were a bit afraid to have this conversation that we ended up in a fight, or actually was very constructive, very well. But we're joking about it actually. So I think we ended up all agreeing on the same point and same direction of the community. So it's quite interesting and fun. So thank you very much for it.
Exactly. Thank you. I hope you had as much fun participating in this discussion panel as we had watching it. So thank you once again for being here. And everyone, please congratulate our panelists.
Thanks
and
a lot.
see you soon.
Thanks a lot to everyone.
Yeah.
Cheers.
Cheers. We are going for a quick 15 minutes break now, and after we're back, we're going to have the tool competition. So stay tuned, everyone. Have a nice break, and see you soon.
Hi, Vincenzo.
I guess it's time.
Yeah, I don't know. Shall we wait for Sebastiano, Giovanni to join, or shall we go on our own?
We can start from the organizer slides.
Yeah. We're here. You can go on yourselves. I'm gonna watch this. This is interesting.
Great. I'll try. Can you see my screen? Right. You don't see my notes. Okay, because I don't know what I'm showing otherwise. So welcome everybody. This is the session where we are discuss the tool competition. So this is a joint work between myself, Alessio Gambi, Gunel, Vincenzo, and Fiorella that took care of organizing the competition this year. Some of us were there last year and some will remain. Let's see a bit of history of the competition. So till last year, we had a variable number of test subjects and projects, and it was mostly focused on test benchmarking tools that generate tests in Java. Then last year, we had a big change, and we included a second type of competition besides Java about cyber physical systems. So specifically, we target self-driving cars. So the last line is our most recent result last year, where we had a very nice number of remarkable number of submissions. So we got 5 tools for CPS and 5 tools for +1 baseline for Java. So the good thing of this year is that we kept this positive trend, and we managed to have 6 tools for each competition that scored the highest number so far. So we got 6 tools from 4 groups for the Java competition, and then Gunel and Fiorella will tell us more later, and 6 tools from 6 academic partners for CPS. So our task and our organization is as follows. Gunel and Fiorella took care of the Java competition, and I will give them word in a minute, and myself and Vincenzo took care of the cyber physical testing competition. So now, without other further ado, I will ask Fiorella to take the lead and tell us about the tool, the Java tool competition.
Okay. Can you see the screen, right?
Yep.
Okay. So for what concerns the Java tool competition, we relied on the previous infrastructure, the one used in the past edition. So we have a fully Dockerized infrastructure that is aimed at running in an automatic way all the generators, and at the same time is able to easy the comparison between the several generators that are submitted to the competition. In particular, our infrastructure takes as input a set of classes for which the tools have to generate their test cases based on a specific time budget. Once those tests have been generated, we are able to filter out all the uncompilable classes together with the flaky ones, and relying on PyTest and Jacoco, we are able to compute metrics used to rank the competitors, and in particular we relied on structural coverage such as line coverage and branch coverage together with mutation scores. The difference with respect to the past edition is that in this year we relied on Google Cloud in order to scale the generation process. All the tools are evaluated based on a specific scoring formula that weights different kind of metrics being computed, and also use some penalties, one related to the time used by the tool to generate actually the test cases given the time budget, and the other one is related to the percentage of flaky test and non-compiling test. Similar to previous edition, also this year the infrastructure is available on GitHub, and going a little bit deeper on the benchmark we used, similar to previous edition, we selected Java projects hosted on GitHub, which rely mainly on Maven or Gradle as a build framework and contains JUnit for test suite. We come up with 4 different projects from which we selected all the Java classes and filtered out all the classes for which the economatic complexity of the methods were less than 5. After that, we ran rundup in order to see on which classes rundup is able to generate at least one test case given a time budget of 10 seconds. And from the resulting set, we randomly selected 65 classes to use as benchmark. Those classes have been used considering two different time budgets, namely 30 seconds and 2 minutes, and the generation process has been repeated 10 times. In order to have a ranking between the different competitors, we used a statistical procedure. Mainly, we relied on the Friedman test and on a post-hoc Conover test. Going on the tools, we used similarly to previous edition Randu as baseline, and this year we have 6 competitors, 2 coming from academia, namely EvoSuite and BBC, and the other 4 tools actually came from industry. In particular, we have two different versions of UTibot coming from Huawei, and 2 different versions of KEX coming from JetBrains research. Going on the results, what we found is that actually in terms of both line and branch coverage, it seems that the tools coming from academia are slightly better than the ones coming from industry, and the same trend can also be seen if we look at the mutant score. Based on the ranking, so we can conclude that EvoSuite is the winner for this competition, followed by BBC. What we have learned actually is that based on the competition, we have identified some aspects that must be improved in terms of the used infrastructures, and also we have pointed out that Docker simplify actually the overall evaluation procedure, meaning that more participants are competing in the competition, and also we are trying to fill the gap between academia and industry. And the other part is related to the fact that Google Cloud leads to higher scalability for the competition. What are possible next steps? First of all, we want to modify a bit the infrastructure, and the most important thing is try to reach as many tools as possible, try to have a benchmark made up of a huge number of classes under test, and probably see whether it is possible to use also Python as a new language to experiment with. And with this, I think that I will give again the share to Alessio. And
thank you. Okay, let's resume. I guess you can see, right? So for the cyber-physical competition, we, as I said, we target self-driving cars or advanced driving systems. Unfortunately, we didn't add a real car to test, so we had to resort to simulation-based testing. So for simulation-based testing, we use BeamNG.Tech, which is a state-of-the-art simulator, and this is the simulator that we also use in the previous edition of the competition to have some continuity between the 2 editions. So the idea of our simulation-based testing is that the algorithms will create roads of increasing difficulty for the test subject until something bad happened. So in our setup, the test subjects are lane keeping assistance systems. So are those software components that monitor whether the car is on the road in the correct lane and try to keep it that way, that no matter the shape of the road. And this is exactly our setup. This year, differently from the last year, we have 2 test subjects. One is called BeamNG AI, which is a so-called omniscient trajectory planner that mimic basically a racing driver. The new entry is a Dev2 implementation from NVIDIA, which is a deep learning system that uses images to predict steering angle. So it's an end-to-end imitation learning approach that tries to stay on the road. So we want to test lane keeping systems, so how the test cases look like. I repeat this for who was not here last year. So the idea is that a test case is a sequence of points into a dimension and 2-dimensional space that gets interpolated into a road. Then this road is used to generate the simulation. And here you have a screenshot of the actual simulator that eventually is used to test our test subjects. This is a test case. What's a failure? So we primarily are focusing on the so-called out-of-bound episodes, when the car goes basically either out of the road or invades the opposite traffic lane. And when this happens, we identify this, our setup identify the situation and computes how much of this car is outside the current road. And if this value, so the red area, is above a configurable value of a tolerance, then we flag this execution as faulty. So the test subject was not able to keep the car entirely inside the road. To run our experiments, we have developed and evolved since last year an infrastructure that you will find on GitHub that is extensible in the sense that tool generators implements an interface to generate test cases. Then they pass it to our pipeline that validates the scenarios, run them into the simulator, and return to the test generators the simulation data. And everything is done as automatically as possible. The infrastructure can be configured by specifying generation and execution budget, max speed, size of the map, and the OBE tolerance. And what comes out of this execution is a report that summarizes how good was the test subject. For the contest, for the competition, we adopted two setup. One, which is called BeamNG AI, which is exactly a replica of last year's setup. We have this BeamNG AI tested on a very tolerant oracle and driving at high speed. And the second the second setup of our experiments instead involved DAVE2. And because DAVE2 was trained for driving a lower speed, we limit the speed of the car, so the speed limit on the road, to 35 kilometers per hour. But to compensate that this is a very that is easier to drive at lower speed, we also reduce the tolerance of our oracles, meaning that our oracles will trigger they are more sensitive towards out-of-bound episodes. So before moving on and giving the word to my colleague Vincenzo, a brief summary on how we ranked the test generator. We decided to adopt a formula which is new compared to the last year, that basically tries to evaluate two pieces of our equation. On one side, we want to evaluate the quality of the generated tests. For doing so, we compute a feature map from all the execution of all the tools, actually all the faulty execution of the tool, to create a map where similar faults end up in the same cell of the map. Once we had built this map, which is inspired by the work of Zodi Nasa at ISTA, we could compute the coverage achieved by each tool over this map. The idea is that the more tools cover find bugs in all these cells, the better they are. That's described the generated test, but not the test generation approach. Therefore, we also included a few metrics describing the effectiveness and the efficiency of the test generator. The effectiveness was defined as the number of valid tests over the number of all generated tests, meaning that we kind of penalize generators that generate a lot of invalid tests. And efficiency was instead computed by as a ratio between the generated test and the used budget by each tool. And we normalize this across all the runs of all the tools. Now, to conclude my part here, we had a remarkable number of participants, 6, and those are ADA Frenetic, Ambient Gen, Frenetic V, Gen RL, Evo MVT, and Vogan. And the nice observation here is that they cover a wide spectrum of test generation techniques, ranging for, let's say, traditional randomized and search algorithm to the use of reinforcement learning model-based test generation and GAN networks. with this, I would ask Vincenzo to take over and present the result of the competition.
Hello, everyone. Let's see how these tools performed. We will start from the first aspect we evaluated, and this is the out-of-band diversity. And I'm going to show you the number of failures that have been triggered on top, and for each of the two agents that we have bottom, the out-of-bound diversity measured as the coverage of the feature maps that we have already seen at the beginning of this of the SBST workshop presented by Paolo Tonela. And I'm showing both of them to demonstrate that the best tool is not always the one that finds as many more failures, as happened to Ambiagen. That was for BeamNGI the second best in finding failures, but then, as we can see at the bottom, it found a much more diverse failures covering the feature map. The second aspect that we evaluated is effectiveness, and we evaluated how many of the tests were valid. And we can see that 4 out of the 6 tools, namely Ambiagen, FreneticV, GenRL, and Evo MBT, generated almost all valid inputs, and that was impressive. Wogan generated a lot of tests. For BeamNGI, it generated more than 2,000 tests, but most of them were invalid. Then we evaluated efficiency. Efficiency, as Alessio said, is depends on the number of tests, but also on the amount of budget that has been used. Each pie chart shows the remaining budget left to the tools, and we can see not only generated more than 2,000 tests, but also used less than the 3% of the budget, while tools like Adafrenetic used the whole budget to generate their tests. And now let's discover who won this year based on these results by applying our magic formula on for each of the tested agents. We have that we can declare Ambiagen the winner for the second edition of the SBST CPS challenge. Ambiagen left FreneticV and Wogan fighting for the second and third place. But of course, we want to congratulate all the participants because they showed us a wide range of solutions to the same problem. So the competition is this year's competition is not even ended because we still have the participants' presentations, but we are already looking at the road we have ahead and what we want to do next. Next year, since this year we have seen that by adding different agents, we have slightly different results. We are going to add more agents, and especially agents based on machine learning, like reinforcement learning based driving agents. And also, we want to make the problem more challenging by making the test space more complex. As an example, weather conditions or obstacles to the road. And next year, we will have a little bit of healthy turnover because Alessio will leave the organization to competition, and especially of the cyber physical system part. And this means that you, if you want, can organize with me next year's CPS 2 competition. This is all from us, the organizers. Let's start with the presentation of the tools.
So actually, we will start with the Java competition. So I will ask Gordon if he can start sharing his screen and turn on his camera. Hi, Gordon.
Can you hear me?
Yes.
Okay. I've got 7 minutes or something, right?
Yeah.
Okay. So I've shown this video many times, so most of you probably have seen it at some point. If you haven't, this is what EvoSuite does. You select a class you want to generate tests for. EvoSuite will do some static analysis where it investigates what dependencies are available, what we're testing, what are the coverage goals. Then it applies some different search algorithms, produces some unit tests, applies some post-processing, and in the end we get some unit tests which are then analyzed by you in the competition. A little bit of context to justify the specifics of the competition setup. So in addition, actual genetic algorithm, which is only a very small share of EvoSuite's code base, really. There's lots of code around this doing some static analysis where explore the entire, try and find all the dependencies and what EvoSuite can construct. The output of the search is actually an archive of solutions mapped to the individual coverage objectives. And then there's a range of different post-processing steps applied to what is in the archive. We apply minimization to produce tests that are shorter and more readable. In the initial representation, every literal value, every number is a separate variable. There's some inlining to shorten the tests some more. Then we generate assertions using either mutation analysis to produce a minimized set of assertions. Then we've got some finished tests minimized and with assertions, but they may not compile because it's actually more difficult than you'd expect to produce code that always compiles. So what we do is we separately try and compile each of the tests generated, and if there's a compile error, we remove that test. We remain compilable tests multiple times in random orders in order to get rid of flaky tests. And then there's various phases of writing tests to disk, writing statistics to disk, and so on. And not all of these aspects are actually relevant for the competition. So we have a highly optimized configuration that takes into account what you're actually measuring during the competition. So here's a snippet of code from the competition framework where you provide the tools and run, which are then run on your infrastructure. And so the algorithm now used by default is Dynamo. And we do things like we wouldn't use in a default configuration such as testing deprecated methods because that increases test coverage. We do not apply minimization to the assertions we generate in order to maximize mutants, but more importantly, because it just takes a lot of time. And since the competition provides very small time slots in which this has to fit, we determined it's not actually worth the effort. We just generate all possible assertions. We do minimize tests, however, even though time reduces the chances of producing flaky or non-compilable tests. And then there's some other options which are completely irrelevant for the competition, such as whether or not tests are inlined.
how pretty or long the test is not part of the metrics. We're not including this. We don't need statistics and so. And everything else you see here in the configuration is tuning the amount of time EvaSuite gets to spend on each of the phases of the whole chart. And so in most of the empirical studies we're doing in EvaSuite or have done on EvaSuite, we report the time spent by the search, but the competition gives an overall all the phases of the search. So this is the actual tool competition where we've split the available time into somewhat intuitively and heuristically derived values, where the most time is obviously spent on the actual search, but we also try to give ample time on things like minimization. Okay, so here's the actual results from this year. Nothing super surprising. Line coverage and branch coverage goes up if you increase the time. No surprise there. Maybe I should say the actual configuration as last year. We didn't change anything. The interesting is the rightmost plot with the mutants killed, which actually goes down with more search budget. And it's not entirely clear to us what exactly happened there. But one thing we did observe in the logs that there's loads of class not found for projects. A very large number of runs made the PIT mutation tool fail with the class not found exception, which means that the tool completed and you can measure coverage, but once you run the mutation analysis tool, you don't get any results. It's either a problem with PIT, but more likely what's happening is that EvaSuite heavily instruments the tests, and somehow that instrumentation probably messed up with PIT's own bytecode instrumentation. And so there's two different ways you can do this. Either use a custom class loader, which typically is but it's not compatible with PIT. So use the alternative approach in the competition, which is to re-instrument classes at runtime, and that is what caused the mutation problems. Side point, this doesn't work with Java Greater 8, so if it moves to a new Java version, we've got a problem there. With respect to the individual projects, the surprising bit to me was that I was always scared of Guava, because Guava used to be the example of, but actually there's other projects in the competition classes where EvaSuite performed worse than on Guava. So maybe either the problem of Guava isn't as bad as I thought, or the other projects are even worse than I thought. What EvaSuite struggles with Guava is dynamic EvaSuite source code, and a huge chunk of it, of complex code, is dealing with generics. So if you give EvaSuite something like this, it'll try to reasonably instantiate the type parameters, but it's not very good at it. And really that part of EvaSuite should at some point be written. That is essentially all I have to say about this. I'm glad to see that we had no crashes of EvaSuite this time. So none of the classes of the competition, EvaSuite itself crashed. There were a couple of cases where EvaSuite timed out and then the process out, but EvaSuite itself did not crash. So I guess that's a good point. And that's essentially all I can really report. Thank you very much.
Okay, thank you, Gordon, for your presentation. I don't know whether, Gordon, can you hear us? Okay, probably Alessio want to jump in and ask a question.
Yes, unless someone else from the audience wants to ask any other question, I will just go ahead.
Only see a question by Giovanni.
Okay, so Giovanni, forgive me, I'll go first. So I don't know why, Gordon, I cannot see you. Your camera or connection is not good. But thanks for the talk, as nice as always. I have a question about one comment that you made about your test, that EvaSuite relies heavily on instrumentation, and also tests that are generated rely on instrumentation. And I was wondering if there is a line where too much instrumentation should be considered as a factor that invest, because the argument would be that if you do something under the hood that the developer may not seeing it, so you look at the test and the test may do something different because of the instrumentation. What do you think? Is this why EvoSuite instruments so easily the test may be also another interesting question for whoever does not.
Got it. I'm sorry you can't see me. I can see my video, but maybe my connection is actually bad. I don't know. So there's two sides to EvoSuite's instrumentation. There's what EvoSuite uses during test generation, and that's irrelevant for the it does use to run tests, but the instrumentation is entirely to ensure that tests are non-flaky. So we could, and there is an option in EvoSuite to deactivate that runtime instrumentation, but the effect this will have is that you will have things. So what the instrumentation does is it allows EvoSuite to, I don't know, set the date time, what the random number generator produces, the virtual file system, and so on. These are, I think they're all things that you would otherwise do using other mocking frameworks. I mean, the main issue is simply that PIT assumes it provides the class and instruments, and EvoSuite assumes it provides the class load and instruments, and in the end you get either PIT instrumentation or EvoSuite instrumentation. So the tricky bit is combining. I think per se the instrumentation invalidates anything about the tests being useful to developers or so.
Okay, so we should not consider that as a cheating. I'm joking.
I wouldn't say so, no.
Thank you.
Okay, we have few minutes also for a question by Giovanni. What does it happen when you let EvoSuite create, say, a map without generics when the collection requires generics?
Yeah, thanks. That's an interesting question. I can this because as a developer, I would want to see a test that instantiates my generics. So I have to confess, I've never tried what would happen. I suppose it would create difficulties because if you instantiate, say, a map, and then you need to provide parameters of the type you've instantiated. I don't know what would happen if you would just use raw types rather than generics. So this I would consider cheating. Is developers would want to have, right? I don't think they would want to have tests that use raw types and not generics. But I'm afraid I can't answer your question. I don't know what would happen. Well,
Okay, so thank you, Gordon, for your presentation. And I think that we can move on the second presentation for the Java competition. Actually, I have to play a pre-recorded video now because we are gonna present a tool from JetBrains, and unfortunately, they were not able to properly participate in the conference due to the situation, the worst situation here. So I will play the.
Hello, my name is Azat, and today I'll be talking about the participation of my tool called KEX at the SBST 2022 tool competition. So KEX is a platform for analysis of JVM programs, which is mainly focused on the automatic test generation for Java programs. It is based on the symbolic execution method and uses an original approach called Reanimator to generate test cases from the symbolic inputs produced by symbolic execution. And it is currently a research prototype which is developed in our program analysis and verification lab. And this year we submitted our tool to the SBST competition, but also we submitted other version of our tool called Kex Reflection, which is basically similar to Kex, and only difference is that it uses Java Reflection API to generate test cases from symbolic inputs. If we look at the higher level overview of Kex, it consists of three main modules. First, it takes a set of compiled classes as a jar files as an input. Then it transforms each method of the input into internal representation called KFG, which is basically a control flow graph for the Java bytecode. Performs some transformations over that representation. Then a KFG is transformed into another internal representation called predicate state, which is closer to symbolic representation, and we performed several symbolic transformations over that representation. And then predicate state is converted into SMT formula for constraint solving, and Kex can be used to generate test cases or detect errors from depending on how we formulate our constraints. And SMT solver produces an SMT model which Kex can later use to generate an error report or to produce a test suite, and etc. As an SMT solver in this competition we used Z3. So let's look closer at some main modules of Kex. The first of them is KFG. As I said, it's a control flow graph for JVM bytecode, which also represents program in a static single assignment form. And we use this representation to perform code instrumentation, to perform various optimizations over loops, and etc. And on this slide you can see an example of control flow graph for a simple Java program. Then KFG is transformed into predicate state. Predicate state is basically just a list of predicates, and each predicate in most cases corresponds to some instruction from JVM bytecode. But it's not always the case. In some cases, like on this slide, you can see that some predicates are marked with the symbol P, which stands for path condition, and we encode the path condition directly in the predicate state in form of predicates. And we use this representation to perform some symbolic transformations, to perform alias analysis, slicing, memory spacing, and etc. So the next step after predicate state, we send this predicate state into SMT formula and receive an SMT model. We convert this SMT model into a set of symbolic test inputs, an example which you can see on this slide. So basically our test inputs is just a description of Java objects. And to actually produce test case, we need to generate code that creates these Java objects. On this slide you can see the example how it's performed using Java Reflection API, and it's working, but you can see that it's not very maintainable, understandable, and etc. And remember, this is just a simple case where we create two objects of class point. For that reason, we created our approach called Reanimator, which aims to generate test cases from those symbolic inputs using only public APIs of objects. And you can see on this slide an example of generated test case. It's much more simpler and easy to understand compared with reflection. So if we talk about the weaknesses of our tool, there are two main ones. First is the symbolic execution method, and I think I don't need to explain that it's very resource-intensive method. It requires a lot of computation. And the other part is actual test generation process. If we talk about Reanimator, we can say that it's not always able to actually generate test case that uses only public APIs, and there are a lot of cases where symbolic execution was able to produce valid symbolic inputs, but Reanimator failed to compile them into actual Java code. And another part is that Reanimator also resource intensive because it's also based on symbolic execution. If we talk about reflection, well, it's easy, simple, fast, and it works, but the downside that it's very hard to maintain the tests produced by this method. So if we talk about the results of KEX on the previous year, they were not very good. We received a score of 44.21 and took 5th place. And the main failure that we were not able to produce test cases for 5 out of 6 projects last year. And the main reason was that our tool had a lot of technical issues. So if we look at the results of the current year competition, KEX scored 80.94 and ranked 7th. KEX Reflection scored 133 and ranked 5th. And on this table you can see the average line coverage by project. And we can say that KEX received, well, first of all, we were able to generate test cases for all of the projects, and we received an average score of 30% line coverage for basic KEX version and 26.2% for KEX Reflection. And this result is very interesting because our intuition was that KEX Reflection will be much more efficient than KEX because of the previously mentioned Reanimator issues. But it turns out that we were not able to fix all the issues with the test generation, and for that reason KEX Reflection was performed worse on some projects than KEX, and on average it received lower line coverage. But if we talk about our main conclusion from this year competition, we can say that our success was that we were able to fix all the major technical issues, and we were also able to improve our results compared to previous year. But we can say that our tool is still need to be improved to become more competitive with the other participants, and we plan to work on it further and submit a better version for the next year competition if we're lucky. That's all. Thank you. You can see the contact information on slide, and if you have any questions, feel free to contact me via email. Thank you.
Okay, so if someone of you has to ask some question about this tool, please do not hesitate to directly contact via mail the authors. They are happy to answer your question. And we can move on with our third competitors coming from academia. It is BBC. For this, we have a pre-recorded video, but authors will jump in to answer your question. So let me start playing the video.
Hello, my name is Xavier Deroy. I'm an assistant professor at the University of Namur in Belgium, and in the next few minutes I will present the result of using basic block coverage as a secondary objective for unit test generation at the SBST 2022 tool competition. Basic block coverage is a secondary objective that addresses the problem of implicit branches, like runtime exception, when trying to generate a test. Let's take an example. Here is a method under test coming from the XWiki project, an open source enterprise wiki system. When using a white box search-based unit test generator, the method under test and the related dependencies are provided as input to a generator that will usually apply a genetic algorithm to produce a set of tests covering each line of code. To evaluate how close a given test is to covering a target line of code, the algorithm will use two metrics. The approach level measures the distance between the execution path of the generated test and the block of code containing the line. And the branch distance measures the distance between a test's execution and the coverage of a true or false branch of a particular predicate in a branching statement. For instance, assuming that we try to cover line 409, the generator will create an initial population of test cases. When executing the different tests, they will cover the different statements of the method. If the current tests do not enter the for loop, we have test cases with an approach level of 2 and a branch distance between 0 and 1. However, the approach level and the branch distance only check control-dependent nodes. This means that if we have implicit branches, like for instance null pointer exception thrown at line 404 or 405, the fitness value of the corresponding tests will be the same. So what can we do to address this issue? In their work, Fraser and Arcuri propose to use testability transformation to make implicit branches explicit. The general idea is to pre-analyze the code and instrument it to add additional instruction to guide the search to cover implicit exceptions. The main limitation of this approach are the extra cost of the pre-analysis and the difficulty of detecting implicit branches in classes used directly or indirectly by the class under test. Instead of using pre-analysis and testability transformation for unit test generation, we defined a new secondary objective called basic block coverage, which was presented and evaluated in our paper recently accepted for publication in the Empirical Software Engineering Journal. The intuitive idea is that basic block coverage can be applied when two test cases cover the same blocks but trigger implicit branches along the path to the target line. In such a case, the two tests will have the same approach level and branch distance. To decide which test to select, basic block coverage zooms in on the partially covered basic block and looks at the line coverage of the two tests. If one test covers more line than the other, this test will be selected. For the unit testing tool competition, we used our implementation of basic block coverage for Java programs. This implementation has been done on top of EvoSuite. We configured EvoSuite to use Dynamosa with two secondary objectives to maximize the basic block coverage and minimize the test length. We set the usage rate to 0.5, meaning that whenever two tests have the same fitness value, there is a 0.5 probability of comparing the basic block coverage of the test. We also set the sleep time to 10 seconds, meaning that there is a delay of 10 seconds before using basic block coverage for each new target added to the active list of targets during the search. Our implementation of basic block coverage is openly available on GitHub. From the result of the competition, we see that in general, the lines and conditions coverage increase for basic block coverage when the time budget increases. However, we see a decrease in the mutation score. We will further manually investigate this decrease by looking at the generated test. One possible explanation could be the difference in the number of generated tests, more than 18,000 tests in total across the different runs for 30 seconds time budget, against only a bit more than 15,000 tests in total across the different runs for a 120 seconds time budget. As expected, the results of basic block coverage are close to the one of EvoSuite, which is also in line with our previous evaluation of basic block coverage for unit test generation. There is, however, a difference in the coverage and mutation score of the different benchmarks between EvoSuite and basic block coverage. The tool seems to cover the benchmarks differently, and this difference seems to evolve over time. Further investigation is needed to identify the factor influencing the effectiveness of basic block coverage for specific benchmark, like for instance the presence of different kinds of implicit branches and the sleep time for small search budget. More information about basic block coverage for search-based crash reproduction and search-based unit test generation are also available in our preprint. If you are interested in our work, do not hesitate to look at the other topics we're working on and reach us by email or via social media. This work has been partially funded by the European Cosmos Project and the Cyber Excellence Project funded by the Walloon region.
Xavier, can you hear me? Okay. Let me remember the audience that if they want, they can post their question and or they can directly ask question to you. Actually, I have one curiosity about your tool. All these slides are related to structural information in terms of type of test being generated. Have you, can you give us some more information about what is the, for instance, readability of the test cases being generated, actually?
No, for one simple reason, we didn't look at it. So the readability will be the same as well what you would find for EvoSuite generated test, I guess. Yeah, let me just add something here since Gordon is in the room. Thank you again for the great platform that EvoSuite is, because we can try all our crazy idea on it.
No, actually, because we are also thinking about improving the competition and try to add new metrics for evaluating the competitor. One possibility could be to actually look at how readable are for a tester perspective the test being generated.
Yes, but then you need some metrics to define what you mean by readability, right? So yeah, I have no idea how you do that in the first place. I mean, it depends a lot of well, the developer, the organization they work for. I mean,
one possibility could be to rely on some existing tools, such as Busenheimer readability tool. Actually, this could be one first possibility in this direction.
Yeah, sure. I don't know the tool, but yes. Well, one danger here maybe is that, well, competitors will probably just add some more objective just to maximize those kind of things, right?
I know.
Yes, unless you're saying machine learning. Sure. Always machine learning, right?
I have a question. So you probably mentioned it in the presentation, but what is the primary objective of this test case generation? The secondary one is
Yes. So the idea of basic block coverage is that you only want to activate that for tricky cases. So that's why we have delay. And what we meant by adding a primary objective is well, when you want to reach a line. So everything is defined as reaching a line in when you use Dynamosa. So whenever Dynamosa adds a target, well, target means reaching a new place in the code usually, then we have a delay before activating BBC. But those are the primary objectives. So in this case, no, we use the default one from
the combination of
yes. So line coverage, brand coverage, weak mutation, and I don't remember the others. But
yeah,
yes.
okay. I see. Thank you.
Okay, so if there are no more questions from the audience, I think that we can thank Xavier and Furia actually for having submitted their tool. And we can move with the last presentation for the Java competition. And I will ask Giovanni actually to play the tools, the pre-recorded video for UTBot. That is a tool being provided by Huawei, and actually also they cannot join the conference actually today.
Hello, I'm Alexey Mishushin, one of the developers of UTBot, and I'm presenting its result at the SBST 2022 tool competition. Since we participated for the second time, just a brief description of UTBot. It's a white box automatic test generator that tries to cover as much code as possible with unit tests and to find any possible hidden bugs in it. To do so, it uses symbolic execution for path exploration and generates human-readable code in Java or Kotlin. Let's take a look at the example. We have a simple function from Go that sums two integer numbers and throws an exception. Hello, I'm Alexey Mishushin, one of the developers of UTBot, and I'm presenting its result at the SBST 2022 tool competition. Since we participated for the second time, just a brief description of UTBot. It's a one-box automatic test generator that tries to cover as much code as possible with unit tests and to find any possible hidden bugs in it. To do so, it uses symbolic execution for path exploration and generates human-readable code in Java. Hello, I'm Alexey Mishushin, one of the developers of UTBot, and I'm presenting its result at the SBST 2022 tool competition. Since we participated for the second time, just a brief description of UTBot. It's a white box automatic test generator that tries to cover as much code as possible with unit tests and to find any possible hidden bugs in it. To do so, it uses symbolic execution for path exploration and generates human-readable code in Java or Kotlin. Let's take a look at the example. We have a simple function from Go that sums two integer numbers and throws an exception if there will be an overflow. And we have two generated regions for it, one for successful executions and one for explicitly thrown runtime exception, because we found a branch that will lead us to unchecked exception. Also, we can track system changes. For example, we have methods that change the state. It modifies these instance parameters and statics. And we have methods where we can find those changes. We have assertions for modification on these parameters and statics. And we can see models before the execution and models after the execution and the difference between them. Now, let's move to the improvements comparing to the last year version. The first one, called Concrete Executor, it's a tool that runs method under test concretely in a child process. It's a highly important feature for us because we used to have symbolic models before, symbolic models after, and result value. We might miss JVM crash or hanging tests, or there might be past diversions or something like that. And now we, using Complete Executor, can avoid all of this. We'll have models before, symbolic models before, and concrete models after, and result value. And we can pass those values to code generation and be sure that we will have all correct tests. So we use Concrete Executor whenever our engine is stuck. We can eliminate past diversions or find hanging tests or JVM crashes and add them to error suite. We use it in instrumentation code coverage calculation, and it gives us guarantee that we will have at least one generated test for each method. The second improvement is about code penalize. We have struggled with lists, maps, and other collections in the last year. So we decided to write our own equivalent in behavior implementation that are much easier to analyze. For example, we can see add all methods without any cycle. That is much easier for symbolic execution to explore. Then we have introduced mocks, and now we can write unit tests for methods with non-deterministic behavior, or for methods that work with network or file system, or with some libraries. We have two strategies. Either user can define a set of classes they want to mock, or UTBot can automatically detect if it's required to mock those classes and mock them using Makita framework. It's highly important for our customers and for usage. Let's take a look at the example. We have a method with random usage, and we'll have two test suites, one with successful executions and one with error. And those regions are part of our next improvement, that about human readable code. We try to generate code that is easier for people to understand. So we have ML-generated names and method descriptions for functions. We have different regions for successful executions or error suite, and we try to construct objects using only public API without reflection. You can see as an example where we have a region for successful executions. We have method description with unique points on the decision path, a method name with unique information about the execution, and method object construction with public API. Let's move to the results, and we have a big growth compared to the last year, about 20% in line coverage on 30 seconds and 30% on branch coverage, and something similar on 120 seconds. Also, we have many improvements compared to the last year. They bring us new problems, and we have 4 main of them. It's completion errors that happen because of human readable code and avoiding of reflection. It's JVM crashes in generated test cases, since we didn't use concrete executor for UTBot mocks, and it generates code that sometimes crashed JVM. We had performance bug in concrete execution, and that's why we have two versions, UTBot concrete and UTBot mocks separately. We struggled with time and other limitation management because it's quite complicated to do it in the right way, to spend all the resources you have. Sometimes we generated in much less time limit and didn't use all the time we had. But many of these problems are already solved, and now we have concrete and mocks versions in UTBot together. With it, we avoided problems with JVM crashes, and we fixed all the compilation errors we have. We are going to improve further, and our closest goal is to create advanced concoding engine, even more human readable code using code synthesis and SMT solvers, introduce ML-driven path selector to improve performance. So that's all. Thank you for the attention. If you have any question, you can use my email or my tag in any social media. Thank you. Goodbye. Hello, I'm Alexey Mishushin, one of the developers of UTBot.
Okay. Hi, Dmitro.
We cannot hear you. So we will solve the issue with Dimitri will go on with the CBS tools. Let's try now,
So
Dimitro.
in the meantime, I will thank all the participants for the Java Tool competition who helped us in making a very interesting competition with a great number of tools, hoping that the number of tools will increase for the next year competition. And we can move on the CPS part right now. Thank you to everyone.
Thank you, Fiorella. That was a great session. Dimitro is nothing. The first one that should present.
Can you hear me now?
Yes, it's perfect. Yes.
You can hear me. Okay.
Yes. Okay, but the first one would be Ada Frenetic by Songyang Yan and being found from the Jiaotong University in China. The stage is yours.
Can you see my slides?
Yes, perfect.
Okay, great. Sorry, where's the slide? Okay. Hello everyone. I'm Song Yang. I'm a year 1 student from Xi'an Jiaotong University, and now let me introduce our tool, Frenetic. I will introduce how I think of this and how it works and the results it made. So first, from the name, you can see our tool, Frenetic, is based on Frenetic. Frenetic is a genetic approach-based tool that uses Freenet frames to describe road curves. And Frenetic is one of the most effective, one of the best tools last year in the last year's competition, respect. And what I am focusing on is the output of the pipeline, that is a sequence of points. And in the competition, a valid test case requires that all the waypoints, all the road points are in the map area. And Frenetic, after a test case has been generated, it will move it through simple translation to make the road fit in the map area. And if it doesn't fit, then the test case will be ignored. So my idea is that there will be some test cases that are actually available, that can actually fit, but cannot fit through simple translation. They may have a second chance. So I add a transformation step. And the first is to simplify the process. I model the road curve as a progenitor. And the first step is to find 2 points that has the furthest distance away from each other. And this will be the vertex of the progenitor. And connect them, we get a line, and we find the most left point of the line and most right point of the line and connect them to get this progenitor. And then move the geometric center of the progenitor to the center point of the map area. And in the competition, it's a square. And then rotate it to make the vertex on the diagonal of the square. And then judge whether the road now is in the map area. It sounds simple and it sounds reasonable. Let's see how it performed. In the competition, as you can see, the final score it made is absolutely not that positive. And the purpose of this improvement is to improve efficiency and effectiveness, because what we purpose to bring more test cases to valid test cases. That means we expect to see a higher number of generated test cases, a higher number of valid test cases. And let's see, compared to the original method, let's see the chart on the top right. The data is from the experiment I do locally. And we can see that the test cases generated by Frenetic is indeed higher than the original method, is almost triple, but only a small part of the available test cases are turned into valid test cases. And along with that, a huge number of invalid test cases are introduced to test cases. So we will see a improve on efficiency and a drop in effectiveness. And in this competition, among other tools, Fnatic ranked second in terms of the amount of test cases generated, which is efficiency. But due to the huge number of invalid test cases, we get a very low score in effectiveness. So in conclusion, there's a trade-off. We do hope to generate more test cases, but the quality of test cases is also important. And the side effect of the invalid test cases make our tool not that effective. And so that's all. And I gotta say, I'm really a beginner, and but I'm keeping learning to be better. So I do hope maybe next year I'll be here to share with you my new work. And it's my pleasure to share with you, and it's my pleasure to learn from you. Thank you.
Thank you, Song Yang.
Yeah, thank you.
I guess we have a question from Alessio already.
Yeah, so nice presentation and nice work, considering that you are at the very beginning of your career. So we are looking forward next year to the progress. So my question would be the following. So you actually have two questions. So you say that you use Frenetic as your base tool for then developing your work. And my question is, why did you choose that? Because it was very effective in the past edition, or because the representation of the roads that he has?
It's very simple, because I found this competition very late. It's already January, and I think it's a practice. So I gotta research the most effective method and see what I can do with this. So so I choose Frenetic, and I just do some work about this.
Okay, and so you say that your modification, this is my understanding, was not as effective as you expected at the beginning.
Yeah.
You generate a lot of still invalid cases. Did you investigate a bit why that happened, or whether a different, I would say, recovery operator could be applied otherwise to make it, generate more valid test cases?
Yeah, I investigated a bit afterwards. I found that I found that it's about my code. It's not that robust. There's a parameter that is the width of the road, and I set it to a relatively small value, and that makes the final result of the position of the road may still be outside the boundary of the map, and this brings a certain number of invalid cases. And yeah.
Okay, so you were getting too close to the boundary of the map.
Yeah. So it's easy to make mistakes. Yeah.
Okay. Yeah. Thank you.
Thank you.
Thank you. So next year, will you still improve Frenetic, or will you start from scratch?
In fact, I'm working on another approach, and it seems promising. I do my own framework and do my own algorithm next year.
Well, I can tell you that we have here Dimitro that also participated the last year. Last year he did not win, but this year he is the winner. So do your best next year. We expect a lot from you. Thank you.
I will. Yeah. Thank you.
Next one is the winner is Ambiajan from Dimitro Umenyuk, Giuliano Antoniol, and Putsecom from the Polytechnique of Montreal, Canada. Dimitro, the stage is yours now that we have fixed the problems with the mic.
Yeah, hello. Hello, thank you very much for having me. Right now, I'm just trying to share my screen. Can you see the presentation?
Yes.
Yes, so you see the slides, right?
Yes, yes.
Okay, thank you very much. So it's my big pleasure to present to you today our tool, AmbiaGen. And I'm a PhD student at Polytechnique, first year PhD student at Polytechnique Montreal. And this tool was developed with the help and supervision of Professor Futzhomg and Giuliano Antonioli. And actually, as you mentioned before, indeed, last year we presented another tool, which was called SWAT. And this one is an improvement of the previous year tool, where we added some evolutionary search. And I will discuss it in a more detail today. So let's start by formulating the problem for the competition. We need to generate a sequence of 2D coordinates that will be defining the rod spine. And another challenge is that the produced rod should be valid. So it shouldn't go out of the bounds of the map. It shouldn't be too much curved, or it shouldn't intersect. So I'll discuss briefly the most popular approaches to generate the rods based on the rod points. Some of them are Catmull, rhomb cubic splines, Bezier curves, where basically the sequence of points are approximated by a curve using an algorithm. Another quite different approach is based on affine transformations, which was used, for example, in the asphalt paper. And actually, when we were studying the field, we saw that this one should be more promising from the point of view of flexibility we have to generate different flexibility and control we have on generating a particular rod topology. So we decided to go with this strategy, but we slightly modified it. And here is basically how it works. We start with some base vector, and then we can apply 3 types of affine transformations, which are going straight, turning right, or turning left. And they correspond to parallel transition of this vector or a rotation of this vector. So if we go straight, suppose we want to have a straight rod segment, we do a parallel transition of this vector, and we receive a straight rod segment. We want to create a right turn. We turn this rod segment by n degrees, and we receive a turning right curve. The same applies for the left. And basically, it's a rotation, anti-clockwise rotation for the left and clockwise rotation for the right. And then if we want to, again, do a straight one, we just do a parallel transition again. And it was the principle presented by us in the SWAT tool paper, and you can look at the details in that paper. So how do we represent our individual? Actually represented as a 3D matrix where each column corresponds to some segment of the rod, and which you saw in the previous slides, and the rows correspond to the attributes that describe this segment. So it can be a straight rod segment, a turning right rod segment, or turning left rod segment, and also we provide information about how much it should be straight, what should be the turning angle, etc. And as you can see, the length of this chromosome can be variable. We can add these rod segments until the test case becomes invalid or goes out of the bounds. So we use the multi-objective search algorithm, and we defined 2 objectives. Actually, first one is to maximize the misbehavior of our agent, and the second one is maximize the diversity of the test cases. So in our case, the misbehavior would be the deviation of the car from the road lane's center, because ideally a good behaving car should follow the center of the lane, but in the case of a car with a failure, it will deviate immensely from the road center, and that is our objective, to find such a test case that will make it deviate as much as possible from the road lane center. And interestingly, here we decided not to go for the simulation-based evaluation of this fitness function. So we didn't execute the full simulation model in the BMG environment, but because we noticed from the first time that it was quite time-consuming. So intuitively, we saw that if we create a simplified car model based on the first principles, for example, bicycle car model with some co-controlling algorithms, such we chose the Stanley co-controller best tracking. It should provide, if it will be challenging for this simplified model, it will be also challenging for the autonomous agent. And experimentally, we saw that it was indeed true for most of the cases. So to calculate this fitness function, we used the simplified model. We didn't execute the simulation. And this allowed us to actually reduce the time quite a lot. The second function was the diversity of the test cases. Basically, we evaluated it as a Jacquard distance between two test cases, and the Jacquard distance is the inverse of the Jacquard similarity, which is a common metric used to evaluate the difference between some sets. And in our case, we just calculated the shared number of attributes. In our case, the shared attributes are the attributes which are similar to each other, such as if the turning angle is very close, we basically consider it as the same turning angle, or if the rod type is the same, we also consider it as a shared attribute. And we divide it by the total number of attributes. So the more shared attributes there are, the less diversity score will be achieved. And so also we introduced I want to introduce our crossover, our search operators, which is the crossover operator. Basically we use the one-point crossover, and you can see it's simply exchanging the columns between parents. And also we use some mutation operators, which were swap operator, which exchange the column positions, or also we added a random value to the row. So let's look at the big picture of our algorithm. We selected NSG2 as a popular algorithm to be used in the field for the multi-objective optimization. We use the population size of 100 and number of generations 75. We chose it empirically, and basically we start by generating 100 random chromosomes. Then we transform this table, our representation, to the actual rod points using the algorithm I described in the beginning of my presentation. Then we evaluate the fitness function using the simplified model. Also, I want to mention that for the test cases which were invalid, we assigned a very low fitness function, and that's how they were eliminated. Then we perform crossover, mutation, and update the population. We repeat it for the number of generations, and I want to say that using a simplified model allowed us to run this algorithm several times during the competition budget. And I think it was also an important factor because every time we were repopulating our initial test cases, and it allowed to explore a wider search space, I suppose. So in conclusion, using simplified models is very perspective. It allows to reduce the time and actually allows to find the test cases which will be pertinent for the real model. Also, the accounting for the diversity allows to generate a test suite with diverse scenarios. So after each run of the algorithm, we received some Pareto front, and in this Pareto front, we are individuals with the highest test case difficulty and the highest diversity. And you can see more details in our paper, which is called a search-based framework for automatic generation of test environments for cyber physical systems, for a bigger picture about our approach. And of course, you can also refer to the tool competition paper as well. And as a future work, we plan to to study the usage of surrogate models from the data, building them from the data using machine learning and statistical approaches. And also we would like to generate more complicated scenarios. And we'll be looking forward for the next year competition. Thank you for your attention.
Thank you, Dimitro, and congratulations. It was a really nice presentation. So I don't know if we have questions. We can start asking you what changed from SWOT last year?
So SWOT last year, it was basically simply randomly generating the sequences, the sequences of actions, and there was no optimization. So it was randomly choosing to go straight and meters, turn right or left. So it was random. It was random based, and there was no diversity maximization, no evaluation. We didn't even evaluate the test case. It was a random generator, basically.
Okay, but still you were able to build on top of that.
Yeah, and here we just use this random generation and improved them at each step. Like we applied NSG2 algorithm to improve the test case, to perform this.
We have also a question from Alessio that disappeared.
Yeah, but I see also there is a question from Giovanni, and this time I will let you address that question first.
Sorry. Actually, thank you, Giovanni, for your question. Actually, inspiration came also from asphalt paper, because in the asphalt paper, you used, Alessio, the diversity to use Jacquard distance to promote, like also to eliminate very similar, to eliminate similar test cases. And I think we have a slightly different representation of this Jacquard distance, but it was inspired from there, actually.
Okay.
How much do you think the diversity played a part in your good results? You know, what we observed when we were using a single objective function, after we ran the algorithm, for example, after running 75 generations, we had, as a result, a number of similar test cases. Like we had all the test cases were pretty much similar. So that's why we decided that we need some mechanism to promote diversity in the final solution set. And I think by adding the diversity function, it allowed us to have to actually be able to produce a test suite of diverse test cases, not just one test case which will be effective, but a number of test cases which will be effective and different. Thank you for the question.
Nice. Alex, you still want to do your question, or you want to contact Dimitro in private?
Yeah, I mean, I don't know how much time do we have left. So
a quick question.
Okay, a quick question. So you use a simple but not trivial model to simulate the car instead of actually run the simulation. So you are simulating the simulation. And this, I think, is a very, very effective way of doing things, as you show. And I have basically two quick questions. Just pick one. How close was this model that you pick, this bicycle model, to the actual simulation? And how much does it matter to have a very, very accurate model of the car for the test, if you have any evidence or idea about that?
Yeah, thank you for your question. Yeah, we performed some evaluations on comparing with the real simulation. So we basically we collected the paths from executing the real model, we collected the paths from using our simplified model, and we evaluated the Hammond distance between those paths. Like it's a metric which can be used to evaluate the road topologies, how similar are two road topologies. we had we need I would say we would need to perform more thorough evaluation of this, but initial results showed that this metric was not so low. So there was indeed some similarity when the actual car was going out of bounds. For example, our simulated model also was deviating from the road lane. But it's very important because if we evaluate it incorrectly, we receive the incorrect value of fitness function, and it guides us in completely wrong direction. So I think it would be better still to use data from the simulation directly to have a more accurate estimation. And if we have the actual fitness function and a reduced execution time, it would be really great. Because here the biggest disadvantage was that fitness function would sometimes may not be really accurate because of this difference. But still in major part, it could drive it in a correct direction, but it can be improved.
Thank you, Dimitro. Okay, let's go on. We have Frenetic V from Ezequiel Castellano, Stefan Klikovic, Samet Setinkay, and Paolo Arcaini.
Hello everyone,
okay, Giovanni will play the video.
Castellano, and I'm going to present Frenetic V. This is our submission for the SBST competition, second edition. So this work has been done with Stefan Klikovic, Ahmed Setinkaya, and Paolo Arcaini. So the goal of the competition, as we said, is to generate virtual roads that drive the car off the lane. And here, one of the key metrics we use is the OB distance, which measures the distance between the car and the center of the lane. We also submitted our previous version of the tool, which is Frenetic, to the SBST competition last year. And in general, we got like positive feedback. We were one of the best in terms of diversity of sparseness. We got the second place in terms of number of out-of-bound errors. And in general, we were the most consistent results in the different executions. On the negative side, like we generated too many invalid tests. So yeah, in this edition, we try to focus on this aspect. So for this time, we propose Frenetic V, which is like Frenetic plus validation. So Frenetic, like to remember a bit, is just like a simple genetic-like algorithm. Like it first generates an initial population, then mutates the good candidates, and if there is no good candidate, it does some random new generation, random population. So later, after like some frequency that is defined as like 40 times, 40 children, then like we do crossover among the best candidates, and then we go back to this loop of like mutating or random generation. So for us, a good candidate is a candidate that passes some threshold, which is like that minimum OB distance is less than minus 0.5 in some part of the drive, and also it can be pass or fail, and it should be a test that we haven't visited before. So to us, the key is the representation. We use curvature as one representation of a road. So we store curvature values, and then we transform these curvature values into orientations that then are transformed into Cartesian representation by using numerical integration. And the good thing of this is that guarantees like our curves are very smooth. As we mentioned before, we have several invalid roads, like they could be because of out-of-bound boundaries, over the sharp turns, or self-intersecting. Before, for out-of-bound boundaries, we were producing basically short roads and like trying to reframe them into the boundaries of the map. This time we are still doing those two things and also added rotation to ensure that some rows that didn't fit before now fit. Then for overly sharp turns, like we have global bounds for the converted values, and we still have that as our method to avoid overly sharp turn. We just adjusted those values to ensure that like we reduce the number of like overly sharp roads. And in terms of like self-intersecting, before we were not doing anything, and now we are doing a pre-check based on like the lines of the road, the main lines of the road, which are the center line and the two boundaries. So yeah, before, as we said, we were not doing any rotation, so now we are doing rotation plus relocation. For instance, in this case, like this road, the original is the orange one. If we do not rotate this, it wouldn't fit in this like yellow box. So like, in order to make this road a valid road, we rotate it until it fits in the boundaries of the map. To do so, we first calculate the convex hull, and then like we rotate that in polygon in all possible directions to try to see if it fits between the yellow box, the map, the boundary of the map. To avoid self-intersection, as we mentioned, we added a pre-validation step that basically checks if there is intersection between the three main lines of the roads, which are the center lane, the left lane, or the right lane. So based on that, if there is an intersection, we just discard that road. And this, in contrast to the validator, we are doing this on the rough road, which is that means that it doesn't have all the points that has after interpolation. It's just having the points that we obtain after transforming from curved values to Cartesian. Overall, the results on the competition were good, let's say. Like, we were among the best in effectiveness. Then in diversity, we were second or third, depending on the dataset and the agent. And in efficiency, we were the seconds or last because, like, yeah, his point, like, we all got the same score except for Wogan. And as for the final score, like, we are like second in the day 2 and third in the BeamNG AI agent. The good thing is that at least this time we managed to do what we wanted to do. That is like we reduce the number of invalid tests. And for instance, here in the BeamNG AI configuration, which is where we had more invalid, we actually had just very few invalid and much less than other candidates. So Frenetic, as a conclusion, was not as diverse as before. And one of the reasons is that the metric that was used was direction coverage, which is a structural feature that indicates how many directions of the road you have covered. Since we assume that the direction of the road is not very relevant, a road after rotation should produce the same behavior. That's what we thought, but maybe that's not the case, because as we were explained, like the shadows or from the sun or different things could affect how the driving agent behaves, in particular when it's like an agent like Dave 2 that is using images to drive. So in order to exploit more diversity in this regard, like we could explore the rotation of the roads, and instead of like just choosing a random rotation that fits, we could choose a rotation that makes more coverage in terms of direction. So thank you very much. This is it for today. And if you have any questions, please, we'll be happy to answer them. Thank you.
Thank you. That was a nice presentation. I spotted in the audience Ezequiel. if you want to come online.
Hey.
Ciao, Giulia. Hi.
I'm still awake.
Okay. Well, what's Alessio here, and I guess he has some questions. No. Yes.
I don't know why when I press the mic, I disappear. I have. So you also, like Song Yang, identified this issue with the original implementation of Frenetic and try to do something about it. Now this is provocative, but I want to understand the platform that is used to run the test comes with a validation.
Yes.
Right. And you didn't use that validation, you developed your own validation. I'm curious if it was just by chance or there was something wrong with the validation provided, or what was the reason behind that?
Well, actually, that was the reason why we were not validating is not because we had a validator, but because one of the scoring things was like how many valid you have. Like we decided to implement our own validation, which is a simplified version and it's a cheaper version of like the one used in the competition. So it's done before interpolation. So we simply use the lines and check for self-intersection of those lines, which is much cheaper.
Okay, that probably addressed my question. Thanks.
No problem.
Okay, thank you. I cannot see other questions, and I hope we'll see Frenetic also next year.
I hope so.
And let's see what happens. Thank you, Ezekiel.
Thank you.
And we will go on with Gen RL by Luigi Libero, Lucio Starace, Andrea Romdan, and Sergio Di Martino. Unfortunately, they are not here to present, so I will show their video, and then you can send them questions via mail.
Good morning. I'm Andrea Rondana, a PhD student at the University of Genova in collaboration with Fondazione Bruno Kessler, and today I'm presenting General, the tool with which we participated to SBST 2022. General is a tool based on reinforcement learning. But how does reinforcement learning work? At each time step, the agent takes an action on the environment and receives back a state and a reward, that is a feedback signal. This process goes on and on to learn the best behavior to have according to the state that we are observing. Essentially, reinforcement learning is learning by trial and error. If we want to be more precise, we need to define the action space. That is what we can do on the environment. Then we have the state space, that is what we measure about the environment. Then we have the reward function that represents the feedback that the agent uses to learn what actions to do. At last, our goal is to learn a control policy that maximizes the expected total reward. This is an overview of the general approach. The intuition behind General is to train a deep reinforcement learning based agent to transform a given road until it becomes fault inducting for the self-driving car. Now that we have an overview of a tool, we can formalize the reinforcement learning problem. Let's start from the state space. The state is defined as a sequence of points that characterize a certain road that the car must follow. Each point P is defined by its x and y coordinates. The initial state is obtained by randomly generating endpoints. In figure, for example, we can see a road that is generated by using 4 points. Let's speak now about the state space. each action consists in moving one of the points in the current state along one of 4 directions: up, down, left, and right. More in detail, an action is a triple in which the first dimension represents the movement direction, the second dimension represents the point to be moved, and the third dimension represents the extent of the movement, which can be either small, medium, or large. For example, if we want to move down the third point, we can do it by using one action, resulting in this road, this new road. Let's talk about the reward. Intuitively, the reward works in this way. The higher the out-of-bound percentage obtained by the resulting road, the higher the reward. More in detail, we have a strongly positive reward if the road is valid and fault-inducing. Positive, slightly positive if the road is valid but not fault-inducing. And at last, negative if the road is non-valid. Let's talk about the learn policy now. General uses a deep neural network to generate actions that are initially random and observes their outcome. Leveraging the collected information, General trains the deep neural network to maximize the expected total reward. And at last, General uses the deep neural network to generate a policy whose behavior is optimal with respect to the collected data. To conclude, General is the first application of deep reinforcement learning to the generation of test scenarios for lane-keeping assist systems. The results achieved in the SBST 2022 tool competition are promising, and in future works we plan to investigate different reinforcement learning-based formulation of a lane-keeping assist systems test generation problem, trying to improve the efficiency and the diversity of the fault-inducing tests generated by General. Thank you for your attention.
I learned how to pronounce it thanks to this presentation. And the next is Evo MBT by Rayana Ferdouz, Chia Kang Hung, Fitsum Kifetiu, Davide Prandi, and Angelo Susi from Fondazione Bruno Kessler in Italy. Please, any of the authors can come on stage and present. You have to share your video. Anything wrong? Fitsum, are you there? Okay, let's go on with the next one. If Fitsum can contact me on the chat, we can fix it. And we have Vogan by Jarkko Peltomaki, Frankie Spencer, and Ivan Porres for the Obo Academy in Finland. Welcome back, Jarkko.
Thank you very much. You can see something, right? You can see the slides?
Yes, perfect.
Okay. So I presented something today earlier, but maybe I will say something how it fits into this tool competition actually. So for those of you who didn't listen to me earlier, what we propose is a test suite generation algorithm, and we want to use these generative adversarial networks and neural networks in general. So that's the idea. And before I say anything about the details. Maybe just a couple words about the input representation. So really, it was very helpful that this frenetic V people already said something about it. So we really just use this curvature representation. So it's basically, instead of just having, sequences of plane points, we are talking about, directions and angles. And this really helps to make a random search possible. So that's why we took this from Frenetic. It's very useful. And what we actually did in our tool is that we normalized, in a sense that we start all roads from the middle of the bottom of the map, and initial direction is up. And this has some drawbacks, like the Frenetic V presentation. It was mentioned that actually, if you allow rotations and things like this, it's beneficial in this diversity measure or this region coverage thing. But okay, we didn't do it. And in our tool, we really fix our tool to use 5 curvature values. We really need to fix this because we are using a fixed neural network which takes this values as input, so it cannot be variable. And really, this number of points is pretty arbitrary. So if you have a small dimension, it's easier to learn with a neural network. And we don't have much data because the time budget is sort of tight. So this is good for us. But the trade-off is that if you would use more points, then you allow, that they can express more varied roads, right? Frenetic can use something like 25 points and things like this. And the output we use is really this body out of lane percentage, BOLP, as we call it. But yeah, just the amount of area that exits the designated lane. And the simulator, actually, you could take a signal output which tells this BOLP over time, and also distances to the lane edges. I think it was mentioned in some other presentation, but we didn't use this. But we actually think that these would be beneficial to use. But let's see if we do it next year. And briefly about the ideas. So this would be what I told in the other talk. So something about generators. So this set of inputs, this I, is just our roads, the sets of curvature points we're looking, and just consider some subsets of inputs, say A. And a generator on this A would be a model which could sample from the uniform distribution on A. And such a generator model would be trained based on a sample from this A. And what our Wogan really does is that it trains in an online fashion a generator on this set. So this is just the roads such that the body out of lane percentage is high. So really, it's just a means to find a generator which can output high BOLP tests. And the main points of our Wogan algorithm are the following. So, and this is the same as before. So we sample some random tests initially. And while we have budget, it could be execution budget or time budget. So we train a generator on high BOLP samples from this test suite we have obtained so far. And then using actually that data, we can train a neural network which estimates this mapping. So it estimates basically the fitness of the road that's given. So we can train an analyzer. And now that we have a generator which is supposed to be trained on high BOLP samples, it actually should output high BOLP samples, but we sample them and actually estimate their BOLP using this A, and we pick the winner out of these ones, and then we actually execute this selected test on the simulator and add it to our test suite and keep going. So this is the algorithm in broad terms. And why this line here is especially important. So we are training the A to know this mapping, right? So we need to have reliable data for it. So that's why we need to execute this T on the simulator to learn it. Otherwise, it could be garbage. Yeah, and I guess the intuition is that over time, this A here gets more accurate. So this selected T is actually, it's not only estimated good, but it actually is good. And eventually, G should obtain as its training data something that actually is high BOLP. So intuitively, this ought to work. And what else? I don't have the time really to talk about all the details. You need to read the paper, but in the title there is this Wasserstein generative adversarial network, and why we use that one instead of something else. Well, basically the big boys are telling that empirically it's been observed to produce varied samples. So because one of the aims of this competition was to generate diverse roads, we thought that, okay, maybe this Wasserstein thing could help us there. And another point is that this Vogan is really a general purpose algorithm. So the only domain knowledge we use is this input representation from the frenetic, but nothing else. So we don't have any, domain specific mutations or things like this. So this is applicable in other situations as well. And yeah, I guess I'm out of time, but just a brief remark that we are pretty satisfied with our results. So we were one of the best performing entries. Maybe we didn't win. We performed better on this BeamNG thing and not so well on day 2. But this Wasserstein thing enabled us to get diverse tests, and we got good results without much domain knowledge. So we are really satisfied with this performance. Okay, so that's it. Thanks for listening.
Thank you. We are happy that you're satisfied, and we are also very satisfied about this competition here. We heard from you already before in your first presentation. I don't know if there are other questions from the audience, additional ones. Alessio, okay.
Yeah, I have one simple question. Is among the 6 competitors, you were the only one not to share your tool open source. Do you plan to release it at some point?
Yes. So the thing is that we are funded by this EU project, and one of the aims of the project in the end is to provide this tool for generating test suites. So it's a big tool. It's a work in progress, and we are not ready to share it at the moment. But for sure, it's going to be available, and the tool is going to offer lots of features not relevant to this competition, and we hope it's going to be great, but we are going to share it, so don't worry.
Yeah, because I think it's a very strong contribution to the community, so it should. I'm always for open science. That's why. Okay.
Yeah, me too, and thank you very much if you liked it, and maybe if someone is really interested in getting a peek at the code, like maybe we can figure something out, please contact. It's this is not a Manhattan project, so it's all right.
Okay, so last question, very quick. So you say that the result shows that Bogan was better on one test subject, but not the other. And by chance, this test subject is the one that me and Vincenzo released before the submission. So the provocative question is, did you pre-train your Bogan on that when you made the final submission? Or it just happened that it was better?
So while we developed our ideas, we used this BeamNG AI thing and not this Dave one. So I guess it means that, well, we didn't tune the hyperparameters, but I guess that during the development, whatever arbitrary decisions we made favors us in this one. Yeah.
Thanks.
Okay, thank you for your presentation. And I guess that Fitzum is back and solved these issues with Mike. Have you? Yes.
Let me share my screen. Sorry for the mishap. I failed to test my. Okay, let me. Oh, I don't.
You're muted.
Okay. Can you hear me now?
Yes, now we can.
Okay, okay. Okay, thank you. My name is Fitzum. I'm a researcher at the Bruno Kessler Foundation. And so today I'm going to share a couple of slides on the tool that we submitted to the competition, which is called EvoMBT, and it's developed under the European project IV4XR, which is a project for testing virtual reality and extended reality based applications. The tool was not meant, let's say, to be applied for testing cyber physical self-driving cars and so on, but it's somehow related, and the idea behind is quite generic. So we said, why not we try to apply to this new system under test, let's call it. I'm just trying to say a couple of words on that. EvoMBT basically is a very generic tool for test generation from FSM models. FSM, so I'll not go into the details. FSM models are finite state machines with additional variables, state variables, and the transition from state to state is guarded by some condition. And every transition, once activated, could have possibly some effects that change the internal state of the machine. So given an FSM model, the tool applies different algorithms based on different criteria to generate tests. And these tests, so abstract tests, these are basically sequences of transitions. So it's like a path in the model. Currently we have implemented some coverage criteria to drive the generation of the tests. So state coverage, transition coverage, and K-transition coverage, which has been added after this competition. So in this, the tools that we used in this edition didn't have this K-transition, should have been better in my opinion. To generate the test cases, it uses different algorithms. So the way we implemented it, it's compatible with EvoSuite, so that the algorithms implemented in EvoSuite could be applied. So EvoSuite is a library that we use as a provider for algorithms. There is a lightweight model checking based approach and also an interface to integrate planners, but this is not released in the tool, but there are some works in there. So it's a general tool that given any FSM generates tests. So as I said before, we have applied this tool to generate some test cases for 3D games. So in the context of virtual reality, where we model the gameplay itself. So there the model represents an abstraction of some scenarios in the game. Whereas in the SBST competition, so we don't actually model the game, but we, let's say the application, but with an environment of the application, which is a road. So for us, as I said before, it's a different application of the tool. So briefly, so basically, EvoMBT instantiates, let's say, the typical model-based testing approach. So we have the system under test or whatever behaviors that we want to capture. In this case, we have the driving environment, from which we abstract a model. So the model, in this case, is manually crafted, but it could be also inferred in a number of ways. On the model, we generate abstract test cases, so some transitions and sequence of transitions, and these are concretized into some executable test cases, which are then executed through the execution environment on the system under test. So basically, this is a process that we apply using the tool, and what we applied also in this case. So given the MBT, the EvoMBT tool, for this competition, all we needed to do was to provide a model that models the road, basically, because in this competition, the target is to generate different roads on which to try the car. So there could be different ways to model to build the model. For this case, we applied an intuitive one. So we represent as states, let's say, the directions like north, east, and so on and so forth. And the transition could be considered as a movement from in these directions, from one direction to the other. Like, okay, I came from this direction, now I go towards this direction. And here we introduce some parameters. So every direction is controlled by an angle, and how much to move in that direction is controlled by a parameter. And then we introduce in the guards of the FSM some controls, for example, on the validity, for example, like to avoid a sharp turn back to the direction that it came from, or to avoid some strict angles. Or to avoid that the movement goes out of the map boundary, and so on and so forth. So we use the AFSM guards to control these aspects. And so the model itself is like a meta model, so it has some parameters that can be used to configure, and based on some preliminary experiments, we fix some parameters, but this can be changed, and different models could be generated. So as I said before, so we use the EvoMBT to generate test suites driven by transition coverage of this model. And of course, the generator itself has a given budget. So given like maybe 5 minutes or 10 minutes or whatever, it will generate tests to cover, let's say, the model in terms of transition coverage. And then we do also further checks in Python, because the tool EvoMBT is a Java tool actually. And in this competition, one of the challenges was to how to let's say, make it interact with the Python environment, and were some problems then, but in the end we were able to make it work. So the bulk of the tool is implemented in Java. So there is some wrapper for the competition, which is in Python. And once the points are generated, we do also some checks on the points there, but that's as a further check for validity. So as I said, so the tool was not made for having this kind of applications in mind. So it was a casual application, and it's the first entry this year. One thing that we didn't notice, we noticed, is that it didn't generate many tests. One could be that it was ineffective, simply it was slow in generating them, and the other could be the way we partitioned the generation and the execution time budget. This can be further improved. So it didn't generate invalid tests, but the efficiency and the diversity were quite poor, but Okay, so our heuristic, so the generator does not have any direct feedback from the environment, so we generated it offline, so a priori, and then we executed it. So in this regard, this was to expect somehow. But as I said before, now after this competition, we have the K transition, so which allows us to generate more interesting paths, because we can, with K set to 3 or 4, for example, we are able to generate interesting paths that traverse 3 or 4 transitions at a time, and not a composition of single transitions. So that would probably help eventually if we decide to participate in the next competition, let's say. Overall, let's say we are happy that we participated, even though the result is not brilliant, but we also somehow anticipated that as well. It was a nice experience, and it was a nice use case for our tool. Based on the feedback of this year, eventually in the next one, we'll try to make it better, let's say. So if you would like to try the tool MBT, you can find it on GitHub. There is a specific branch, SBST 22, so which adds an interface, an iterator interface on the original tool. But anyways, the tool itself is generic enough, so maybe someone could implement a better model for the rods, and they can try it as well. So thank you for listening. That's my talk.
Thank you for your presentation, Fitzo. So you said that this was the first time that you participated, and you didn't expect it to consider this kind of agent to test. And one thing that could motivate the other participants to join next year, what could you tell? How difficult it was to address this new case study?
Not so much, because we, well, actually, so the test generation could be complex, but at least the side of the problem that this competition is looking at is particularly not complex. So you just have to generate a sequence of points, basically, in a two-dimensional space. So it's, in principle, you can generate quite easily these points. But the difficulty is in actually achieving the so-called out of bounds. No? So it's easy to participate, but challenging to do something effective, let's say, in terms of the criteria. So in order to participate, I think it's fairly enough, fairly easy, I would say.
Okay, that's good. Thank you for your words, and we are looking forward to have you next year. So we concluded the presentation of the tools, and I can give back the mic to Giovanni.
This SBST 2022, which was a great success. Okay, you've heard it first. It was a great success. Okay, we were not expecting to have so many attendees, such a good feedback from everyone. So thanks everyone for joining. Thanks our PC for the support in reviewing the papers, the steering committee on their support for moving the workshop online, our sponsor Google for sponsoring the cloud credits for executing the tool competition. And just a few numbers for you: 143 people registered for SBST this year, out of which 115 attended throughout the day. I guess 30 people forgot to see their spam inbox for the link to Meetspace. At some point, we had 80 people attending via Meetspace. We had 40 people attending via Twitch, and the best attendance throughout those two platforms was 110 people watching. So this is very impressive. Thank you everyone for participating. Sebastiano?
Yeah, I mean, but of course, the success of a workshop really depends on the people. And core part of the SBST is really the tool competition. Here, we want to thank the other organizer of the workshop, Alessio, Gunel, Vincenzo, and Fiorella, which made the tool competition a record as well. And not only we made a good amount of attendees, but we also get probably the most participated competition ever. And this happened also last year. Hopefully also next year we managed to do so. Thank you guys. Of course, you have seen a lot of data shared, from slides, from video. You will have, for example, from this workshop. And if you had this impression that all was always easy and available, is thanks to Rebecca, which was always there answering our demands, requests. She was always on the page on that. So thank you very much for your effort, and both me and Giovanni. And of course, that means to be successful, receiving a lot of paper, but that was also a huge effort from the PC members. So the PC member, a lot of load compared to previous years to reviewing papers. So that's really quite important. And this allowed us to have good papers, well reviewed, so that the authors, whether they were accepted or not, would receive good feedback for improving their work and go forward with their research. So thank you all, guys.
Yeah, and another thing that we will try to keep is the good balance between females and males in the program committee. This year we got almost 50-50, which is a good thing.
What was not expected, not only the numbers, but also the level of participation. We had people on Meetspace, Twitch, but it was not only just people that were really there, just silently following the workshop. We had really many questions. It was sometimes very difficult to stay on time. Indeed, we are a bit late. Sorry for that. But I think that's mostly what has to be a workshop, especially a workshop on this topic. And I think we expect to grow more thanks to your participation, pretty much to your contributions. Thank you very much.
Okay, and so with that, let's go to the what's next for SBST. So currently we have an open issue for an open call for the special issue at the Science of Computer Programming. This call is for software. So basically, the format is a short paper followed by mostly software repositories, software code, data, everything that comes with SBST software. That's the focus of this special issue. So if you have your tool and you want to publish it, focusing mainly on how it works, the data you used, maybe some results as well, this is the place to submit your tool. So it's an open call as well. So if you haven't presented your tool at SBST 2022, you can still submit the paper to the Science of Computer Programming. The submissions start on the 1st of June and they go until the 1st of October. And that's it. Also, we are going to make the recordings of workshop available on Twitch, on the Twitch link that we live streamed. We will also upload the videos on YouTube and share with you through Twitter. So if you want to stay in touch and see all the material that we're gonna make available, follow us on Twitter. and we will also put those supplementary material on our webpage. So check it if you want to watch the keynotes again, the discussion panel again, and so on. And also, we are planning to write a newsletter for the SIGSOFT quarterly newsletter, and with all the notes from our discussion panel, because we truly believe that these kind of discussion panels are really needed in our community to advance science. And I think all the comments from our panelists were very on point and very interesting, and lots of insights there. And thanks once again for our panelists to our panelists for attending that long discussion panel. It was very, very interesting. And what's next for the tool competition? Well, this year we got one sponsor for the cloud credits. However, for next year, we are going to try to get a cash prize for the winners. So we're looking for sponsors. We're going to keep looking for sponsors. Get cash prize, one cash prize, or maybe one cash prize per topic, and then give it away to the winners. So stay tuned. That's another incentive for you to submit your tool next year. So I hope you will appreciate a cash prize. Also, on the topic of fuzzing, one of the things we discussed is how to integrate the two communities, and perhaps we can create a fuzzing competition as well. So we can maybe can have a Java competition, the traditional CPS competition, and perhaps a fuzzing. It's not a promise. It's a promise we're gonna try. Okay. And also we plan to coordinate SBST with fuzzing workshops, fuzzing conferences, and get those two communities closer together. Try to improve science as it should be, like by joining forces and focusing on the overlaps, focusing on the intersection of both communities instead of the differences. So yeah. Sebastiano?
Of course, we are up to take this challenge with Giovanni and the other tool competition chairs. Of course, that's not that, which is not just the end of SBST, it's actually beyond that. So there's been a lot of focus during the talk about testing complex systems. So next year, SBST will, as every year, there will be a team, a very focused topic, which for us I think is emerging, important, and not yet addressed, or fully addressed, which is testing superficial system. So for sure, as this year, we plan to have a great keynote from expert on superficial system development testing, followed by complementary panel, which will make it more, interesting, as has been interesting this year. We already try to target the right people already, even though it's some time upfront from big players. They are really doing or making superficial system used, and maybe moving forward, for example, transportation system. Think about Tesla, Google, and even many drones delivery. You have maybe never heard about it. It's an Irish company which already exists and deliver food via drones. You can even receive very small things, big things, even a beer directly delivered to your house. So quite interesting. Never seen this before. Try to have the challenge to involve them on our workshop. And of course, finally, you don't just want to involve them. We want to have tools that are usable, foster again to have tools available, whether they are in fuzzing, whether they are in search-based or search-based fuzzing, or whether it is about superficial system. That's the key aspects of this workshop that will be stand on the long term. So with that, I want to thank Giovanni for the great effort. It was really fun working with you. Really, I didn't know you before, but next year I'm looking forward to co-organizing again this workshop. Very, very fun, successful, I think, even.
Thank you very much, Sebastiano. You did a great job as well. Thank you for helping with the organization. I think the success of this workshop is due to all the people involved, and certainly you're one of the most important here to make it happen. Thank you.
Thank you.
And I think with that, we finish our workshop. Thank you all for participating, and I hope you see you next year in Melbourne, hopefully in person, finally, okay? I'm sure SBST 2023 is going to be as good as 2022, and I hope to see you all there. Thank you very much.
Thank you, and see you all soon, hopefully.